Hello. Hi, everyone. Hel- Give me a hoot. Okay. A lot of events today, but this talk is my favorite. Okay. The talk's title is What I Wish I Knew About Container Security, and I really wish I knew. So, welcome the speakers, Duffy Cooley and Jed Salazar. And yeah,
Good morning. I'm so
Morning.
glad you're all here. I'm super excited to be here with my friend Jed and all of you.
Yeah, I'm really excited to be here. I love Rejekts. This has become quickly my favorite conference. Yeah.
Absolute favorite. So what we both wish we knew about container security starts off with everything. But what we do know is a little different, right? Like sorry, I think I just went a little too far forward. So what I do know about container security is summed up in a couple of other things, right? Like one of the things that I'm going to start with is this really awesome idea of a cognitive bias that is the law of the instrument, right? Where it's like if you have a hammer, then everything looks like a nail. Frequently in our industry, that hammer is Linux, right? And when we think about containers as a thing that has evolved over time, that hammer, that Linux hammer, has come in very handy. And we've done a lot to improve that hammer, but it is very much leveraging Linux as that hammer. Some of the other things I know are that containers aren't real. Containers are just Linux processes. In that, like every Linux process, if you were to log into a Linux system today and look at all of those processes and look at the proc file system, you'd find that all processes in Linux today, as it is today, are associated with a bunch of namespaces. For the most part, if they're all under the same, if they're all like operating at the same layer of the Linux kernel, then they may agree on what all of those namespaces are. But if they're a container, then some of those namespaces will be different. But fundamentally, containers are just processes. You can't have a container that exists without a process inside of it. Another thing I know is that IP tables is complicated, and it's one of my absolute favorite quotes. You know, in any team, you need a tank, a healer, a damage dealer, and somebody who knows IP tables really, really well. A shared kernel is another thing about this, right? So when we talk about containers, containers actually have a lot of primitives, and we're going to talk about some of them in this talk that allow for better isolation between processes, but not necessarily better isolation between those processes and the Linux kernel. We rely on different technologies for that part of for that part of container security, right? For the most part, when we talk about container security, all of the primitives that we run into more often, like these namespaces and all of that stuff, that's really just better isolation between applications, not between those applications and the Linux kernel.
Yeah, and I wanted to touch on that as well. The shared kernel is a big deal because the kernel is carrying a lot of weight in Linux, right? It's now kind of the de facto security boundary as well, and we'll kind of talk today and point out like why that has kind of become problematic.
It's a risky one because of things like file systems are complicated. So back in the day when we were running applications directly on a server, we had one file system. We might have we might jail particular file systems so that access via some like web interface, et cetera, or like a web server would hit a specific file system that was somewhat contained at the time. But fundamentally, like file systems are complicated. And containers that you're making use of today can actually not only make use of a file system that is specific to that process, but also make use of file systems that are in the underlying host. And it's actually very easy to create a container that has access to things that you may not actually think it has access to. And that's where I say file systems are complicated. Another one is that soft links are hard. It's a funny thing. A soft link basically points to a file path. A hard link actually points to an inode. So when you have something like a soft link that points to a file path, you introduce one of the ways to exploit containers. Actually, a pretty common way is to leverage a soft link and do what's called a talk-to attack, where basically you have the ability to change the link that is being represented and allow for access that you maybe didn't intend. But these are all things, all of the things that we've mentioned so far are things that you can find on modder.org that have had to evolve in the Linux kernel because of exploits, real exploits that exist in container security today. So as a high level, those are all just things that exist that like really represent some significant challenges as it relates to containers. So let's go back a second. Let's do a little time traveling. Let's talk about like where Linux came from, because we're using that Linux hammer for everything. Let's just jump back for a minute and kind of talk about the history.
So even before Linux, we can talk about Unix, right? Unix is basically the grandfather of modern computer, grandparent. Linux, as we know it today, took inspiration from Unix, and as you can see, here we have Ken Thompson and Dennis Ritchie huddling over the first Kubernetes cluster way back in 1972, right? But a lot of the core Unix developer philosophies that are discussed in where this book or where this image came from, the art of Unix programming, are carried over to today's cloud native landscape, right? Fail fast, a bunch of the philosophical attributes, but not just the philosophy, right? Like the technology, the foundation of TCP/IP, file systems, the concept of portable applications. These were all developed in the 1970s. It might blow your mind, but tools like cat, chmod, chown, cp, et cetera, those were developed in the first edition of Unix back in 1971. And they remain in our toolbox every single day, right? So not much has changed, but the hyper-scaled distributed compute systems that we know and love today, like Kubernetes, are basically just leaky abstractions for what would become Linux.
When Linux was introduced, it was actually introduced as a way of developing another operating system for desktop computers. It wasn't initially meant to be the thing that we literally operate the entire internet on top of today, right? And just think about that for a minute. Like, this was a multi-processor system. I mean, it was a multi-process system. It was like trying to solve things like time sharing between processes and the existing hardware and that sort of stuff. But fundamentally, it was not like the original idea for all of this was not to create like this abstraction that would be the way that we think about hosting everything on the planet today, let alone getting to the point where containers are a thing. That's a lot of growth over the number of years, and there's a lot of lines of code involved in that. And one of the big takeaways for me when I think about container security is that all of that work represents areas where like perhaps things didn't actually evolve perfectly into things like containers, right? So we're highlighting so far, like with things like file systems and soft links and those sorts of things, these are things that have had to evolve over time because when we introduced the idea of file system namespaces, when we introduced the ability to actually mount things back and forth between them, we also introduced ways to exploit those things that didn't quite evolve perfectly over time. So it becomes an interesting thing. When we think about the history of that, so like back in the beginning of this, we didn't really have any of the primitives of containers. Really, I mean, the first thing that really existed that we play with today are things like IP tables. It was introduced in the late 90s. That was a rewrite of the original port from BSD for the, that was, I think it was like IP chains or something like that. It was an early version of this, but like IP tables were like the first like real thing that we kind of introduced, that we play with every day that was introduced back in like 2000. In the 2.4 kernel series.
Which also highlights looking at something like a BSD, a Unix derivative, right? So like we're taking from the past and then bringing it to the future.
Yeah. The next thing that came along was the mount namespace. And this is where we're actually making use of all of those file systems. After that, a few years later, we kind of started getting into a bunch of the other namespaces, things like the PID namespace, the network namespace, all of that came later. And think about like the work that had to go into those base subsystems when these new ideas of container namespaces came along. So now you have the ability to create a new network namespace. How would IP tables work in that new construct, right? This represents a whole nother level of development against a relatively mature and well-known technology, right? Like we've got IP tables, it's working for us, there's no problems with it. Now we're going to introduce the ability to implement IP tables multiple times on the same host, just for funsies, right? And what things can we do to actually relate back and forth between those two different implementations? Like what happens inside the network namespace versus what happens in the host namespace. Represents a lot of complexity.
Another example of that is the user namespace, which was added to the Linux kernel in 2013, and will officially land in the next 1.33 Kubernetes release. So
Finally.
These things have been around a while.
Yeah.
They're not purpose-built. They're kind of, added and then patched and then, basically bolted on after the fact.
And iterated and iterated and iterated on, yeah. So containers are introduced kind of as a thing by Alex C. in 2008. This is before Docker, but it was the idea of actually they finally had enough of the pieces and parts to actually make the puzzle happen. We could create containers. Docker came along and really changed the game because of the user interface, right? The ability to create those container images, the ability to ship those container images, the ability to start them up. That actually happened in 2013. So when we think about the overall timeline of all of this, it's just kind of wild. And one of the great points about when it comes to container security is go back and look at what had to change to be able to support what we're using for containers today. And you're going to find those bodies in the closet. You know what I mean? You're going to find all those little sharp edges that you're not expecting, and likely you're going to find some things that might either fascinate you or frighten you, depending on which part of the puzzle you're looking at.
Yeah, and so far we've been looking at the history, but let's kind of put this back into context and think about this in the modern day, where this is applicable, right? So containers, basically a lot of patches and, iterations. They were never purpose-built for running untrusted code securely in a multi-tenant environment. But here we are, right? That's today's challenge.
That's what we asked them for. But the idea of containers as a security boundary isn't necessarily new. As you mentioned, right? One of my favorite terms for describing this, and actually it appears in a variety of different verticals within our space, not just within container security, but also within browser security and other things like WASM and all of that stuff, is this idea of sandboxes. And I think it's an almost perfect and infamous analogy, right? Because if anybody's ever seen a sandbox, it's not great at containing things. The sand is everywhere. It's not staying inside the sandbox. And so I think it's a really good way of kind of conceptualizing it.
Yeah, there's prior art here in terms of sandboxing. It's not a uniquely containerized phenomenon. Things like the web browser, Chromium has had, different types of sandboxing like site isolation. I was looking up the documentation for it yesterday, and the definition is browsers must defend against untrustworthy web pages that try to attack other sites or access a user's machine. So they basically solve that problem by breaking up subcomponents into their own isolated OS process. But to me, this sure sounds like the same threat model as containers, right? Now we have to protect against untrusted code and protect adjacent processes or containers from the unknown. So we've been thinking about this in terms of the browser for a long time, and those same concepts are coming into the world of security, into the world of containers. There's a couple other examples that folks in this room will probably be familiar with. Bubble Wrap is a container sandbox. We actually at Adara just released our own Rust-based implementation of Bubble Wrap called Styrolite. One thing that I did want to call out is there's an individual named Chris Palmer, and he had a really great talk on sandboxing and its limitations. And there he basically advocates for, sandboxing is great, but it can only get you so far. He worked on the Chromium team. He basically pushed sandboxing to its extreme, limit. And what they kind of realized is that, you need to really rethink fundamentally how you protect your, your applications. And in his talk, he kind of advocated toward moving, toward memory safety. And in this talk, we're kind of advocating towards, much stronger forms of isolation rather than taking something that's inherently insecure and just putting it in a sandbox.
Yeah. One of the benefits of the work that happened in the browser is that they were able to be a lot more opinionated. Right? They were in a position where they could say these are the constraints that an application, a website must live within to be hosted within this web browser, right? Where I think in the Linux container space, we have not been in that position necessarily, right? we're I think it seems to me like we've been more focused on adoption and less on security. So getting back into the container security, the Linux container side of things, I do want to give a shout out to Julia Evans. If you have not seen the work that Julia does, definitely check it out. They wrote an entire magazine that actually gets into a lot of the detail around containers. This is a great example of it because it talks about all of those namespaces that I mentioned that we were talking about before, the mount namespace, the net namespace, UTS, IPC, all of these things represent, as I mentioned before, like the actual namespaces that are going to be associated with a running process.
Yeah, so even though these are namespaces providing this isolation, the key thing to call out here is that they're all using the same shared kernel, and that's the theme that we talked through throughout this talk.
Yep. Yeah, and so just because they're better at isolating between processes does not mean that they're necessarily good at isolating between the kernel. And so one of the early ways to solve this problem was actually to create a virtual machine that has its own kernel, but it comes at a pretty high cost, right? So an example, like this diagram kind of shows, like from the container perspective, all of those containers you're running up against the same Linux kernel. But if you wanted more isolation, then having some level of virtualization would probably be a better model. Yeah, and when we talk about what this model looks like on the container side, it's really that we've kind of turned the Linux kernel into a security boundary, when it never was really meant to be a security boundary, but we all just kind of keep acting like it is. So if you think about it, like, at its core, from a process perspective in Linux, the process has to request, everything from the kernel. If it needs to create another process, if it needs to be able to communicate with another process, this is all mediated from the shared kernel, which basically means that a compromise to the kernel is a compromise to all containers, right? Since it's that shared system. And one thing that I wanted to quickly call out here is that we're talking about asymmetric attack surfaces here. So if you think about the difference between containers and virtual machines, the container's main API or user interface is that kernel. The Linux kernel today is about 40 million lines of code, so there'd be some bugs there, right? It's not memory safe, it's got some issues. Whereas if you have a hypervisor and you're using a virtual machine model, you can use an example like Zen, which is a hypervisor that has about 150,000 lines of code. Are there bugs in there? Absolutely. But that's a much lesser attack surface than something that's constantly evolving and moving and as complex as the Linux kernel. Okay. So we've said that the kernel isn't a particularly great security boundary. Containers aren't particularly good at this. So what can we do about it? So one of the things that was developed relatively early on was this thing called secure computing. And secure computing also ties into that whole namespace component, as we talked about in the browser and all of this stuff, this idea of being able to create a better boundary between a process and that shared resource that is the kernel. So seccomp actually introduces this idea of being able to say, if we think about the Linux kernel as an event-driven API, and I know what all of the API calls an application might need to make are, then I can create a list of the ones that I would allow for that application to make and enforce it to live within those means. And if that list needs to change, that's where we start getting into some of the sharp edges around things like secure computing, because most of the time, the way that people leverage secure computing today is that you kind of need to know that list ahead of time, and you need to apply that list before the process starts, and then the process starts, transitions, and lives within the list that you've given it. And if it needs to iterate, if you need to change that list, you need to restart the process. There's no dynamic changing that. Now, a lot of that world has changed over time. It's another one of those areas where we're evolving. Like eBPF is one of those areas where we're starting to kind of change the way that this stuff works. And we'll talk a little bit more about that in a minute.
Yeah, and on the other kind of extreme side here of, isolation is like this concept of full virtualization, right? So if you've been familiar with things like VMware or, other virtualization solutions, that's the heavyweight approach. And a little bit of backstory here, just from my personal life. Back in the day, I was a SRE at Google, and that was pretty early on. This was before Kubernetes was a thing. One of the things that really blew my mind when I started in that role was I kind of realized that the workloads that were running weren't running under virtual machines. Google was deploying, obviously Gmail and search and all these things, but they weren't isolating them using something like VMware, and I was really surprised to hear that. But Google's goal at that point was to move fast, and it wasn't security, right? If you think about Google, like they famously own their entire stack from like silicon and their data centers all the way up to like, the software, they have a custom kernel, all that good stuff. So they were able to prioritize speed instead of security because they didn't have to worry about it at the time. Outside of Google though, in the real world, containers look very different, right? They typically run in cloud environments where you're not running on your own hardware. You're typically running alongside other folks' workloads. That old adage, like the cloud is just someone else's computer, that very much applies for the vast majority of container users today. So the kind of middle happy ground here is something like what we call paravirtualization. So if you're not familiar with this concept, this is a concept that virtualization has been around for a long time, well before cloud providers or hardware enabled you to have hardware virtualization, but you can still get the same isolation out of paravirtualization. And as we kind of mentioned here is that the way that this works is the applications that run inside of a paravirtualized environment, they don't make a system call to a shared kernel, they make a hyper call to the hypervisor. And then the hypervisor is responsible for isolating and providing resources to those workloads.
And it's referred to as the Goldilocks zone because it represents, why are containers a thing? Does anybody, what is the thing that makes containers so popular out there in the world? It's speed, it's portability. A container image is small, it's easy to deploy, it's very, very fast, right? VMs suffer from all of those things. Longer startup times, harder to get the VM image to where it's going to go. You kind of need to have a full operating system to be able to support those applications you're hosting. Paravirtualization sits in the middle. You actually get all of the security boundaries for all of those things. You get all of the security benefits, but you don't necessarily need a full operating system, right? You can actually you can start these processes in a way that actually gives you a better security model without needing all of the overhead of an entire virtualization stack. Really interesting space when it comes to the security model of it.
So we're going to kind of dive into a couple technologies that Duffy and I have looked at, with all of this in mind, right? That containers aren't real, they're just, patches that have been made over time, and they weren't really purpose-built to, provide us with the type of security that we're interested in. So the things that we're excited about, not really surprising that we both work on them, is, in my case, I mentioned here that past is prologue, right? So technologies from the past are basically being adapted for the future so that we can, make the world a better place. And one of those things that, we're working on here at Adara is basically something called, Adara Protect, but really at the end of the day, we're a container native hypervisor. So we can run really, in any environment. We don't require that you have, hardware virtualization from your cloud provider, but we can still give you that same degree of VM-based isolation. So it's really taking the best of both worlds, where you have the developer ergonomics of running containers. You can still go fast. Your developer teams can, package things up and not worry about portability or where workload lands. But we're trying to really deliver on that key promise that Kubernetes made, which is I don't have to think about my infrastructure as a developer. I can write an untrusted application or a trusted application, or maybe I'm running one with vulnerabilities, or maybe it's multi-tenant, and I just don't have to think about isolation. I just essentially run that container, and my platform handles all the heavy lifting of isolation and providing security for it. And then just a quick shout out to another thing that we recently released. I just briefly mentioned it, which is we open sourced prior to KubeCon Styrolite, which is basically a Rust-based container runtime, or sandbox. And that's essentially what we use. It's programmatic. It has some interesting benefits. And that's what we use to actually sandbox the containers that run within our isolated virtual machine environment. So it's kind of like layers. We're not just putting things into an isolated box and then say, well, you can do whatever you want. We're looking at this from a security in depth and a Swiss cheese model, where not only are we providing isolation, we're also giving you a sandbox inside of that isolation environment to run containers in a secure way.
Without breaking adoption, without breaking the ability for people to actually make use of this stuff, which I think is exciting. So stuff I'm excited about things like eBPF. eBPF gives us the ability to, I was talking about like the kernel as an event-driven API. eBPF gives us the ability to hook into any part of that event-driven API and pull out things like context. So one of the major use cases for eBPF today are things like observability. Just give me better context for what's happening at runtime, right? I want to understand at the socket level what connections are being made. I want to understand at the file system level, whether it's the root file system or the container file system. I want to be able to understand when that file is being opened, where does it actually exist, right? I want to be able to look for behaviors that I consider to be behaviors that would match like a threat actor. And like, how can I fingerprint things in a way that can be determined to be normal when I don't have enough context to even understand at any real depth what normal means? eBPF gives me that ability to have the context necessary to do that. One of the other ones I'm really excited about is Tetragon. So eBPF fundamentally is actually pretty hard to implement. Like when it comes to like writing eBPF programs, it's actually pretty tough to do. And that's actually why I'm very excited about Tetragon. It's a framework that allows you to it provides a better abstraction for a lot of the stuff that I was just talking about. So Tetragon is a framework in that, like if you go to tetragon.io, you can see all the use cases that the open source Tetragon project actually supports. And there are a lot of really great examples, like say, for example, whether you want to deploy Tetragon on just a server that has a Linux kernel or whether you want to deploy it inside of Kubernetes. There's a lot of really great use cases around things like observability and being able to see exactly what's happening in the application stack, and also anything that you can observe in eBPF with Tetragon, you can also enforce. So if you saw a behavior that said, you know what, this guy is actually within this series, within this set of Kubernetes nodes where I'm running untrusted code, I never want a process to be able to access the file system of the underlying root file system, right? How would you write that rule today leveraging tools that you know about? So that you could enforce that. You could say like, on this set of nodes, nobody touches the root file system unless you're already there. Can't start a container that does it. How would you enforce that rule? And eBPF, in Tetragon, that's actually a pretty easy one to write. And there's a great example of that in the website.
Yeah, I was lucky enough to work on Tetragon with Duffy before it became 1.0, and I will say that we built it to be container native from the ground up.
Yep. So at the end of the day, we're better together, right? There's no single solution to things like container security. It's too wide a space. When I say container security, the first thing that should pop into your mind is like, which part? We're talking about the network? Is it the process part? Like, which part are we talking about, right? There's no perfect solution. One of the things that I want to be able to see this a little better so I can actually read it. So one of the things that all of us learn at events like this one is that every complex topic is better learned together, right? When we're out there in the hallway, we're talking about stuff. It gives us the ability to broaden our own perspective and understand more of the problem than we could ever understand in isolation, only entirely on our own. So while we're here, get out there, meet people, come meet people at KubeCon, exercise the hall track. That's the most valuable part of an event like this, right? I say often that I can only learn things through my own perspective until you ask me questions. And that unlocks a whole nother level of learning that I would never have had access to without you. So thank you for being here.
Amazing talk. So a couple of questions if you really have some doubts. We have time.
Thank you for the talk. It's actually more about the product you mentioned and the virtualization. Is it hooking into something like KVM on the kernel and use the paravirtualized devices then?
Yeah, that's a great question. Yeah, so we are not using KVM. Most virtualization systems are. The key caveat with KVM is, if we're talking about it from a security perspective, it still exists in the Linux kernel, so you still have that 45 million lines of code that you have to worry about. But the key thing is that KVM requires hardware virtualization support. So if you're running Kubernetes on a standard EC2 environment and you don't pay for bare metal, then you don't get the luxury of having isolation that's provided by the hardware. So we're utilizing Zen, which is a previous implementation of a hypervisor. It's what AWS was built on. And as a result, you can essentially run anywhere and have nested virtualization, even on a standard EC2 instance that doesn't have the hardware virtualization support.
But couldn't you also use nested virtualization with KVM?
As long as the hardware provides and supports it. There is nested virtualization support in KVM. I've heard that it's not production ready, but I don't have any personal experience with it.
I only know it exists, but I don't know how it's graded.
Yeah, I'm not sure.
Yeah.
Any more questions?
What do you think about WASM as a security boundary?
I think it's, in my opinion, it's actually a very interesting space. We were talking about like the curve of adoption versus security and like some of the trade-offs there, right? Like if you're in a position where you can actually define the constraints of an application the way that WASM does, you're going to start from a better model. You're going to start from a better security model, but you're also going to start from a harder adoption model, right? Because it means that like to be able to like. If you think about WASM just as a packaging technology, to get to the place where you can package anything that you would build inside of a Linux container into WASM, it's still pretty hard to do today because you have to live within the constraints of a WASM environment, or a WebAssembly environment, I should say. So I think it's actually a really good new technology. I wish that it were easier to adopt and it would see more adoption. I'm actually very excited about it, but I worry because of that adoption part of it.
Any more questions? No. Okay, I had one. So, what are your views on Firecracker versus containers? Okay, because Firecracker offers sandbox. They're lightweight. They're fast. So, what are your views in terms of security in using Firecracker versus normal containers? Because we are heavily relying on Firecrackers. 80% of our infrastructure is on Firecracker. So what are your views?
Yeah, I'm going to repeat what Duffy said about ease of adoption. We're bullish on containers. It is really the easiest way to get started. And Firecracker does require some additional work and has some requirements around hardware being available, hardware virtualization. So that adoption, if you think about it from a friction perspective, it's just enough friction where we, think that the adoption might slow a little bit as a result of that. But Firecracker is great. Our position is that if you run containers just generally, you should be able to get the same type of security benefits without having that additional hump of making things custom and getting things working with Firecracker.
Want to learn more about the things we're excited about? Come chat us up anytime during the conference, and we look forward to speaking more with you.
One more question. What would you consider the best network fabric and policy engine across functions, micro VMs, containers, VMs, and even physical? Yeah, and this is not an opinion. I mean, your opinion's fine, but I'm just like kind of interested to know what would be the right approach here.
Yeah, today I don't think there is one. I don't think there is one product that tries to solve that problem across the whole set. The closest is probably something like Tetragon, because Tetragon is basically something that just operates at the Linux kernel layer. So there are elements of network policy that you can enforce leveraging Tetragon that would apply regardless of like what you were doing underneath that Linux kernel. But there's no, as a sense today, I don't know of a single product that's trying to like solve that problem holistically across all the things.
Great. Thank you. A round of applause.
Thank you. Thank you.
So you have to go there. They will give you their mics. Can you give me the mic? Oh, yeah. Okay, we are starting in a couple of minutes. So we are going to start with our second presentation or session of this event. And the topic is evaluating global load balancing options for Kubernetes in practice by Nikolai and Tobias. They are going to use Cilium and K8GB, and they are going to hopefully give us a demo, right, guys?
Yeah, of course.
So, round of applause.
All right. Thank you for coming. Today we want to report a little bit about our project, what we had together, where we evaluated a global load balancing use case. So basically our target was we want to build up like an infrastructure layer that we can behind host stateless services to be available on different clouds or different data centers. In direct, we was hosting it on AWS, Azure, and on-premise OpenStack environment, and want to have it reachable over one DNS name or one global entry. So, from my side, I'm working for Kubernetes as a principal architect, supporting customers since multiple years, and working with containers already 10 years. And then handing over to Nico.
Hi, I'm Nico. I work at Dativ in Germany, and I'm a cloud platform engineer, mostly working on our internal Kubernetes platforms.
All right. So what first, maybe a few things about load balancing. So the basics. So who is aware about load balancing in a bigger picture, who worked with this in projects? Are there some? Okay, not too much people. I expected more, to be honest. But yeah, normally everybody says, oh, load balancing, no. But really working with it is often not as common because you're getting often it provided from a platform. If you're on a cloud, you just say, hey, service type, load balancer, and here we go. But if you are on-premise, maybe it's getting already a little bit tricky. So what is the target of a load balancer? Basically, you have several users, and you have one machine. It could be a physical machine or it could be VMs where you're load balancing the traffic to different servers. So servers are basically independent from each other, but serving different requests, and there you have different strategies how you get served the request to it. Next, in Kubernetes itself, you also have load balancing. A lot of people know the service type, normal service type is cluster. So basically here, you deploy say your application, you have a deployment, then you get a replica set, and you have n replicas of pods. They have own each IPs. And inside of this cluster, basically it's mostly in a namespace, you have a service created, and this service then is reachable inside of the cluster. And this basically gives you a stable IP or a stable DNS name inside of your namespace to reach basically your pods. And then you can add something like an ingress spec. I think most of people know ingress specs. So it's basically giving you then something like, okay, that's the DNS name. Maybe I want to create a TLS certificate around, and basically then my application get reachable. But this is still inside a namespace or inside your cluster. But how you came to something outside, so the traffic must come into your cluster. That's basically the load balancers. And you can create such things also inside of Kubernetes with the service type load balancer. But what happens then? Normally, I think 99% of the clusters have an ingress for layer 7 traffic. If you want to have layer 4 traffic, that means plain TCP, UDP, you need basically a service type load balancer. And this one is mostly in front of an ingress. And this creates then on the external side of your cluster a load balancer. So it's every time external. You basically say here a component what called Cloud Controller Manager observe the object of service type load balancer says, okay, that's my backends, and the backends are node ports. So they go, if you take a look in the Kubernetes node, you see the node ports open now after you open the service type load balancer. And then the load balancer basically getting the IP of the nodes to the target node ports and forwarding the traffic maybe to your ingress Nginx. And here you know then, hey, that's my app.example.com, so the traffic gets forwarded then to the service, and the service knows what ports can be reached. So that's basically how a normal Kubernetes cluster works. Maybe there are different solutions, but it's like the 90% use case, I would say. So what is load balancing about is we want to distribute traffic, for sure. But we want to also preventing overloading of backends. So basically that we don't say, hey, my backends go down, I can limit requests or I can do other filters. What is often important is health check. So check your load balancer implementation if they're supporting health check, because not all are doing it. So health checks means if a backend fails, in this case it would be the node of a cluster fails, is not reachable anymore, it needs to get moved away from the load balancer. And that's basically a pre-requirement if you want to go really in something like a high availability service or zero downtime deployments. Without load balancers, you cannot implement such things really easy, because if some pod or something goes down or you want to update, you need to switch. And this switching is basically abstracted by a load balancer in front of. Also, in kind of network security design, it's often protecting the backends so that you don't have access outside of your VLAN or your private network. It's the only way out, way in is the load balancer. And this is protected by firewalls and WAFs. So what is the difference between firewalls and web application firewalls? Normal firewalls just do TCP, UDP, IP port mapping, and WAFs are mostly doing layer 7 inspection and see, okay, what is the traffic about? So see headers and checking something like that. Okay, but keep in mind also load balancer is a single point of failure, because every traffic that reach my applications goes through this component. So it's critical, and we need to be careful what we choose there, and especially on the on-premise world, it's maybe not so easy to get things. Okay, how this looks like on an on-premise data center. Basically, you have not just one Kubernetes cluster, you maybe have multiple ones. And they communicate to each other, and basically, let's say we have 2 clusters, and they have inner communication node to node. That's basically the east-west traffic. And then you need to get workload to your cluster. Basically, you're starting here, you have maybe a client going over the internet, then you have something like a FortiGate router where it comes in, and there maybe behind the scenes you have a load balancer, and the load balancer then forwards it to different switches where the nodes are behind it. For sure, there's maybe a layer of virtualized network in between something, but for simplicity, we keep it out. And then basically you serve hitting the node port goes to your service, and then reaching the container. And just the way up, we call it north-south bound. So, and this is basically what we want to talk about. And why a load balancer on the data center is not enough. Because of exactly this one, like OVH had a major incident where a whole data center burned down. I mean, it must not be like that, but if you are also in the hyperscalers, you get sometimes, okay, availability zones are down, okay, that's maybe you can handle, but sometimes it also happens on their side that the whole data center is not reachable. I mean, if you're hosting your own data center, it could be likely that a digger cut a cable or something like that happens, or you have a full electricity outage over multiple days, you are basically not reachable. So, but when do I need it? I mean, well, it depends. Everything costs money, and it must be a business case behind it. So if you just say, hey, I'm pretty cool in this tech stuff and I want to do it, you can do it, but it costs you. And normally business cases are, maybe you are forced to by regulations. So for example, banking applications, banking payment services need to be like fulfilling that they have multiple data centers approaches, or something like, let's say you're building a web shop and you have multiple locations like Europe, USA, Australia or something like that, and you want to have it reachable over one DNS entry, and this is basically where you say, okay, I need something around it, and that's the global load balancers. Okay, and in the target of the project, we want to see what options we have, and the first thing we came across was cluster mesh. So cluster mesh is basically connecting different Kubernetes clusters and then making it high available. So basically this was the first idea. So we placed one cluster in AWS, one in Azure, and one in the OpenStack DC. Then what is cluster mesh? So don't see it with service mesh. So service mesh is basically around service functionality and so on. Cluster mesh is more connecting two clusters together to achieve pod-to-pod communication. So basically you could, if you is allowed by rules, you can have here a pod what can then communicate with a pod there. That's basically what you reach with a cluster mesh. And you can there define some kind of global services. Then basically you have here a service and this can serve traffic from this pod of this site. How they connect is basically you need a direct layer 4 connectivity between the nodes. So this is one thing what is keep in mind. So cluster mesh is not like building a tunnel or something like that. You need basically node-to-node connection. And then you have an extended cluster mesh API server where you basically are connecting to each other and say, hey, I'm cluster A, and here I'm cluster B, and they get connected. How it looks in detail, we will see later. And then basically the cluster mesh is able to create resources, to manage resources in the vice versa cluster. So, and basically so they handle it out that one service can distribute workload to another service by routing. I mean, eBPF experts are around here, so don't ask me. And the target is to make it reachable. Yes, so that's basically it. The cluster mesh API server is normally exposed by a type node port or load balancer. Why? To be accessible outside of your cluster. So it must be outside of your cluster and talk to each other. Now, how we set it up. Basically, we set it up multiple clusters, and then we basically added the Cilium CNI, where basically Cilium brings this capability already with it, and you can modify it in the way to get it running. You find the code on the GitHub. It's not published right now, but we will do it after the event, and then you can see the configurations and so on, how we set it up. So first step, bootstrapping. So basically two clusters, and then you need kind of a network connectivity between them. You can use a WireGuard network, you can use VPN or side-to-side, it doesn't matter. At least the only thing what you need is really a layer 4, and it's important, means TCP and UDP traffic between the nodes. And then first step is you need to ensure that the CIDRs doesn't match. So the node CIDRs of cluster A and cluster B does not be the same. Normally, if you're creating like 5 clusters on a hypervisor or other Kubernetes, you see that the node CIDR internally for the pods have the same pod IP. So if you have cluster A, the pod can have the same IP as in the cluster B. To avoid this and to make the pod-to-pod communication workable, you need different CIDR locations. What you basically, it's nice, it's just a configuration in the IPAM, so in the IP pool, where you can say basically, okay, give me this part. Step 1 or step 0 basically before you're starting even with the cluster mesh setup. Then first step is in the first cluster you need to get the cluster mesh API server up and running. So you creating that by a configuration, and then you get a service type load balancer for the API and a pod what is cluster mesh API. So this one is basically the config for it. So you say, okay, I'm basically cluster 1. I want to get exposed over a load balancer, and I get these annotations because I wanted to have an NLP in AWS. I added these annotations, and then I say TLS auto method, so then it creates certificates. There are for sure multiple ways to set this up, this handshake and so on. Just showing you one way. If you need more, go to the Cilium guys and ask them in detail. And that's mostly how deep are we going here. Then, second step is, now we have the cluster mesh here running. The second step is that this Cilium daemon set pods need to talk to the cluster mesh API of cluster 1. And then we need to configure this one. So basically it looks the same, plus cluster ID 2, service type load balancer to also exposing a load balancer on my cluster 2. And then we're adding here, first step is the CA of the cluster 1. So we're copying the details over. There is a one command you're getting printed out, and there's a secret, and then you're copying it over. And then basically they can at least share the CA. Next step is that you need to basically configure the connection. You say, please connect to cluster 1 in this port and this IP. Here, because I'm falling into this trap, you need to really get the IPs here. And this must be a stable IP. Not CNAME, does not work, it's IP. And then basically for authentication, you're adding the TLS cert and key. And then basically the cluster 2 can now talk to the cluster mesh 1 API server. Next step, step 3, is the vice versa from cluster 1 to cluster 2. So basically also saying, hey, this way connection is also possible. This is then last step. So basically in cluster 1, we configure the same CA, and then cluster 2, the certificates of the cluster 2 copied to it, and the IP also from the cluster 2 load balancer. Sound complex? I must say it's also complex. You can do a lot of things wrong with copy pasting and so on. So you find it also in our documentation, but like this is basically how the bootstrapping works. So what then we achieved is basically we have then a connection between, and then I can really talk pod-to-pod communication and can then build services around. So there's also a health check where you can see, okay, here's connections, say testing all nodes to each other if everything is okay and if the connection is fine, and if you're fine, you can go next, and then building like routing strategies. So basically, what is cool, you just need to add some annotation and say global service, and then you're giving some strategies, and on the left side you see some different strategies. Basically, you can say, okay, I want to just have a local failover, so it means, hey, I have a service here and I want to reach this port, or another way around, so you need to see from the direction where you're applying the service to make it sensible. And then you can make, what we choose mostly was then we say local first. So if you are reachable, then use the local one. If it fails the local one, go to the remote one. And this you do vice versa, and then you basically are reachable. So what happens then in our case? So basically our case was not really to have workload inside of the cluster failover. We want to have really a data center outage scenario. In this case, we have here two services, what are basically DC1 and DC2, and maybe you have a DNS entry on top of it, what is app.example.com, where basically points to these two CNAMEs. And then you have the front end, traditional service, back end to the back end ports. Then on the DC failure, first we simulated basically that here the pods are failing, the failover works great, and the back end pods here get addressed also from this side. So basically the traffic get here into this ingress and then basically get forwarded to this side. But then we shut it down the complete worker nodes, and then also the cluster API server, cluster mesh API server was down. And then basically the problem is this is not a covering case. So there we find that this basically is not functional anymore. So basically if someone hits then DC2, it does get nothing back. And that was for us the reason to go further and go to the next step, what is now Nico is explaining, what is then a global status load balancing.
So basically we start with one idea. What if we treated the whole world as our one availability zone? No more telling users to hit traffic in either one of those data centers or treating even data centers as single units, but stretching. Well, the first option, as always, is just Google Global Service Load Balancing and pay your favorite cloud provider or CDN provider. They all have offerings, but we are techies. We like to build stuff. To be completely honest, I wouldn't recommend building this solution I'm going to show you alone if you're the only one that will be on call, but it's a pretty cool solution. So, not unlike your last incident during on-call, the solution is DNS, because it's almost always DNS. And quick reminder, I think everyone knows how DNS works. We basically go ahead, our client asks the DNS system, hey, where's example.com, DNS answers, and now we know which server we have to talk to. It's only built because humans don't like numbers, we like names. Pretty simple. Then there's an option we could maybe expand it a little bit. So same basic principle, we ask the DNS, hey, how is stuff going? Where's example.com? And we combine our classic DNS server, which is pretty much a stupid text file, with some kind of health check logic. So our DNS server has some health checks and asks the servers, hey, are you healthy? In our example, the first server, not very healthy, it's currently burning, so the DNS server automatically only answers with the IP address for the healthy server, and we connect to the healthy server. This is the entire baseline idea. It's not that complicated. Implementing it can be complicated, but there's always a CNCF project that comes to the rescue. In our case, it's KHAB. It's the Kubernetes native global service load balancing solution. And it handles all of those DNS and health check things for us. The basic ideas, we have KHAB. KHAB includes its own DNS server, Core DNS, probably all know Core DNS. And Core DNS handles all of the, okay, you can find the website at this address. It also includes another CNCF project, external DNS. This is used to tell our upstream DNS server, hey, please look at this core DNS for this subzone. So if you all remember, DNS basically is just a bunch of zones, starting at the top level domain, then our second level domain, example.com, third level domain, app.example.com, and so on. And for every level of this domain, another server could answer the question, where is it actually? To know how to set the right records, KGB just looks out for ingresses and services related to ingresses. You can also manually configure it, but it's the simplest way. So you just tell it, hey, look over there, that's my ingress for example.com. Please create a DNS record. But one instance of core DNS isn't really global, so like Toby said, we started with a couple of clusters. For this demo, we choose a Kubernetes cluster, a GCP cluster, and a cluster from Dativ. And they are all configured exactly the same. Well, kind of exactly the same. But the main thing is there's KGB running on all those, the same stateless echo service is running on all those, and the same core DNS included. So like we said, we just add our upstream DNS. So KGB handles telling the upstream DNS server, we just used Cloudflare, to redirect all questions regarding where is our example app to the core DNS servers. And by default, it just tells them, hey, look at one of those three servers. So most clients will just round robin and ask the first server, the next server. They will handle it. One of the servers will probably always answer. But right now, these core DNS servers here can only tell you about their own IPs. So we need some additional communication. This is also handled by KGB. So basically, the KGB in cluster 1 checks the core DNS in cluster 2 and asks, hey, which records are available? It does the same for cluster 3 and so on. So we had our user. The user just goes to DNS. DNS tells him, hey, please ask the first cluster. And the cluster says, hey, go to Dativ. Pretty simple. Let's try it out. And I really, really hope the demo gods are on my side still. Yeah, of course they aren't. Why wouldn't they be? There they are. Nice. So setup is pretty simple for KGB. It's a Helm chart. You just install it, provide some basic values. the values are pretty simple. You just tell them, hey, I'm cluster 1. These are my friends, cluster 2 and 3, and we all serve DNS for a specific domain. In our case, the top-level domain we chose, or the DNS edge zone it's called, it's nig.gl, one of my domains. And we tell it, hey, don't serve traffic for all of nig.gl, only serve traffic for everything that comes after KHEB nig.gl. And to make things a bit faster, we tell it, hey, to communicate across each other, please look at the upstream DNS. There are some additional settings for Cloudflare, because I use Cloudflare as DNS, and for AWS, because the standard AWS load balancers don't support UDP. By the way, your load balancers have to support UDP. That's one fun fact. And then we just deploy the typical dumb echo service, just answers hello from, and then a name, and nothing special here, just the normal ingress, nothing configured. On the right side, you can currently see, hey, these are the answers I get when I call dig for demo KGB NICGL, and the answer when I curl it just runs a watch. These are the pods in my primary cluster, and these are the nodes in my primary cluster. They will come in handy soon. So let's start with the basic example as failover. This is currently happening, so we say my primary target is cluster 1, but we can also go ahead and switch to round robin. So this will just apply the same config to all clusters. The config is pretty simple. Please look at this ingress resource to get the IP and DNS, and use the strategy round robin. You can even do weighted round robin, so not only will it answer 30% this, 30%, 30% over there, but you can set it. It isn't magical. If you query it 10 times, you might get the right response distribution. If you query it over 1,000 times, you definitely will. So this is pretty simple. We get pretty much randomly answers from cluster, but this isn't the more destructive use case. So let's destroy some shit. So I just set it back to primary. By the way, to set stuff to primary, you just say failover and primary. This is all it takes. And let's stop our service in cluster 1. Let's just scale it to 0 replicas. You can see the replicas are started dying, and there we have it. Cluster 1 is obviously down. It will take a couple of seconds. You can configure that, because a lot of DNS queries will potentially get a rough message from your admins. And let's see, and pray a bit to the gods, that it will actually fail over, because that's the one thing about DNS. DNS likes to cache on the client. Hey, there we are. Failed over to cluster 2, and if we switch it over again, everything will be fine. There's a longer version of this demo in the GitHub, but I think we don't really have time for that. So let's switch over to the lessons learned. As we saw, cluster mesh is pretty cool if you want to do some fine-grained traffic management, MTLS, pod-to-pod communication across data centers and all that, but it fails as soon as you want to do a real failover where one of the clusters just goes ahead and dies. On the other hand, global load balancing, DNS, it's a core technology. It has always worked. It will probably always work. You can just manually overwrite stuff in your DNS if you don't trust it. And you don't need any kind of node-of-node communication. Only the DNS servers have to talk to each other. On the other hand side, you don't have any traffic management across pods. And DNS TTL caching on some clients can be a real bitch. It happened to me before. It probably happened to everyone before. That's the part of it always being DNS. And you can combine them, of course. Good luck with that. We tried it. It works. It's awesome, but it's a bunch of work. And you can also use some of these nice CNCF projects to schedule stuff across clusters. We had a talk yesterday, and there will be another talk today, I think. So you can say, hey, only schedule my workload in cluster 2 if cluster 1 is full and I can't scale the nodes anymore. Stuff like that. And with that, thank you very much. We will share the slides and code afterwards.
How many of you knew about K8GB before this talk? Pretty less. Okay. Great talk.
Thank you. Great talk. I will definitely try it out because I do run into these problems all the time. So my first question is, usually I do very similar things with just Cloudflare. You know, they can do this on a global scale, poll the regions, and then, you know, like route the users to the closest, you know, healthy endpoint. And then, you know, a couple other things can do the same, like Azure Traffic Manager, I believe we also use that. So can you compare that, you know, this solution to those? And this is the first question. The other one is that we do use, there are like global load balancers on the same cloud, like I think AWS Traffic Accelerator. You do get like one IP for all of the regions, although that's, you know, like one specific to those that provider, so you cannot use multi-cloud and stuff. And then everything happens in the same, you know, like cloud provider. So can you do just a comparison in this?
Good.
Yeah, the quick answer is pretty much it's the way of buying a solution or building it yourself, because of course Cloudflare does the same stuff. This isn't a new invention by KGB, this wasn't a new invention by Cloudflare. It's pretty much a question of, do you want to offload it or do you want to do it yourself? And it's the same for the global load balancers provided by your favorite cloud provider. You have to trust your favorite cloud provider. And my company, for example, has some finance regulation stuff where we are not allowed to deploy the full workload to one cloud provider. So we have to do some DNS-based stuff because one IP address would also always be related to one cloud provider.
Maybe one addition. What I like there, it's basically simple DNS. So if something fails, you still can override DNS entries and you get away from it. So you basically don't rely on a global service of a hyperscaler or something like that. Basically, it's a DNS entry where you rely on. And if the DNS is something what you can easily fix, because it's just like, okay, now update the record to something else, I think you are much quicker up in this disaster case. And for me, it was like that. Think about data center is down. You don't care if the service switch over takes 10 seconds or 1 minute or 20 minutes because your data center is down. But what you care is maybe you don't want to debug hard stuff. DNS is simple. You can just override and say, if it's not working, KHP, okay, keep it out of the picture, override the DNS record. And that's what I liked. And I think also from the use case, if you maybe have not this budget for paying such global load balancers, it's also cool for kind of edge setups where you have small clusters somewhere. Basically, you just need a DNS server as external dependency. And that's basically works really stable. So we tested it quite heavily, so it was every time stable, and it's not as complex. And also shout out to the KHGP maintainers, the documentation is great, so it's also working right off the box how they described it. And I also think implementations, for example, F5 are implementing that in the same way.
You mentioned that the project uses external DNS. Do you have to deploy it on your own, or is it in the same Helm chart? Or?
It's just deployed via the KGP Helm chart, and they only use external DNS in order to support the wide range of upstream DNS providers. They have a built-in support for info blocks, but for example, Cloudflare, why build your own logic to tell Cloudflare to create a new NS record if you can just use external DNS?
And you can also inject those external DNS plugins, or do you?
Yes, you can.
Okay.
You can also choose to not install external DNS together with KGP and run your own.
Okay, thank you.
Okay, last question.
Thanks for the talk, it was great. With KGB, can you do geographic load balancing? So can you say there are these clusters available, and if I'm in Europe, I go to the closest one in Europe. If I'm North America, I go to the North American one.
Well, by default, the configuration itself doesn't allow it, but because it's just using core DNS under the hood, you can use the core DNS plugins for geographical resolving of IP addresses.
So you basically need to add their a database, basically where...
The good old MaxMind GeoDB database. I think everyone who's ever had to do stuff like that knows it. And then you can do it, but not by default. You have to do a little bit of work.
It's also not too hard.
Not too hard, yeah, not too hard.
Not be scared.
Thank you, guys. A round of applause.
Thanks.
Time for a break. So make
unsere
sure
Zeit
to get a
wegnehmen.
coffee and head back to the room by 10:55.
It's just like, yeah, the mirror is too much. I don't want to see myself live. You just need to flex.
Go for it.
Welcome back. Okay, very interesting talk. Simplifying cross-cloud, cross-cluster connectivity with Dapper and Cilium. Very interesting talk by Manuel and Alice. Please welcome them with a good round of applause.
Okay, is this on now?
I think yes,
I think
that sounds
yes.
like it.
Awesome. Thanks so much for coming, everyone. My name is Alice Gibbons. I'm head of customer success at Diagrid. It is a company that's backing the open source Dapper project. Just a quick show of hands. Has anyone here heard of Dapper? Okay, cool. That's pretty
Anyone?
It's a graduated CNCF project now. And yeah, we're here to talk about cross-cluster, cross-cloud communication with Dapper and Cilium.
Hi everyone, my name is Manuel Sapp. I'm a solution architect for a German consulting company called Concentric. We are focusing on cloud native software development and whatever that kind means, but therefore we're also making heavy use of Dapper in various customer projects. Hence, that's why we're here today.
Yeah, I forced him to use Dapper in all of his projects. Awesome. So since a lot of you have heard of Dapper, I'm not going to go super deep into the overview, but just a quick high-level 10,000-foot view for those of you that have not heard of it. Essentially, it is a set of APIs for building distributed systems. So, if you were writing your application in choose your favorite language on the top here, you can reach out to a Dapper sidecar or a process, which can run any of these different APIs or these building blocks. So essentially, if you wanted to take advantage of like asynchronous message communication with a message broker, you could use the Dapper PubSub API. If you wanted to do like durable execution with workflows, which is like super hot right now, you could use our workflow API and built-in workflow engine. You also get a number of cross-cutting concerns that are built in to the Dapper runtime. So things like security, like observability and resiliency. So you get MTLS built in, you get things like distributed tracing with built-in OTel, and like resiliency policy is built into your Dapper system. So instead of having to write resiliency within your application code, you can apply that at a higher level using like all of the configuration that Dapper gives you. It runs 99% of the time on Kubernetes in production, but you can also run on VMs or a ton of other hosting platforms listed on the bottom here. A quick note on components. So in order to add to this abstraction, we have the idea of what's called a Dapper component. And essentially what this is an abstraction on top of any of the infrastructure you might be reaching out to within your application. So if you wanted to reach out to, AWS DynamoDB for a state management or a key value API, you could use a Dapper component configuration file, and then instead of, putting the AWS Dynamo SDK within your application, you would use the Dapper APIs via a native gRPC or HTTP client, or use the Dapper SDK. And this allows you like some really nice, like a lot of niceties for like application development. We've had developers say that it saved them like 30% developer time across, I think that was a survey of over like 200 or 300 developers that we did, and that's like greenfield and brownfield applications. Typically, it runs as a sidecar. So, you're invoking the Dapper APIs via localhost, but it can also run as like a daemon set or just a deployment, depending if you're not sidecar people. So a lot of people aren't sidecar people these days. That's okay. So if you were going to reach out to one of these APIs, for example, the service invocation one, you could use like the invoke endpoint, and then like in this case, call the cart service on the method order. And Dapper will do the service discovery and the invocation for you. This makes swapping the underlying implementations of the infrastructure super, super, super easy. So, for example, if I'm running in local development and I have this kind of super simple microservices architecture here. I have 3 services, one's doing like a service invocation, one's doing a PubSub communication, and one's doing a writing a secret to a local file. I do not have to change any of the code from going from local to, let's say, on AWS. All I'm really swapping there is those things I was talking about, which are components. So I can swap to AWS Secrets Manager or AWS SQS and DynamoDB without actually changing any of that code. Really nice for going cross clouds, which we're talking about today, or going cross environment. Quick note, what we're going to show for service invocation. I'm going to go over here because I'm really over there on that side. Yeah, for service invocation, say if you have to applications here, and you are like doing an invocation between your services, of course, you're gonna have those Dapper sidecars living in between the services, and then again, built-in MTLS. There's a name resolution component, which again will invoke like kubedns if you're running on Kubernetes, or if you're running on something like virtual machines, you can use like console DNS. It has built-in MTLS and then observability for whatever your observability backend is. And yeah, that's pretty much it. And then publish and subscribe, which we're also going to show in a quick demo here. But if you have, again, two services wanting to communicate via like async communication using like whatever message broker you want, I believe we support over 20 message brokers these days. So there's a lot of these open source components, again, all written in Go, all available on GitHub. You can totally check out the source code. But this would be invoking the sidecar on the publisher side, and then it would go to the message broker. It's using the cloud events specification. So it's kind of, you can enable or disable cloud events if you want to. And then, again, still getting that full, complete end-to-end distributed tracing and observability. And then, yeah, this is all kind of wired together using what's called a component, right? So I have this component, which is just a Kubernetes CRD, and this is going to have, in this case, talk to pub/sub Redis. And again, in this case, this is running on a Redis host that's running on my local machine, but this could be running anywhere, right? Your Redis cluster could be in Azure, in AWS, on Kubernetes, whatever. So again, you would just put those connection details into this component, and then Dapper completely abstracts the Redis SDK. Like, you don't need any of that within your code. You just use the Dapper APIs. So how does this relate to anything for cross-cloud communication? Good question. So Dapper versus Service Mesh is something that comes up a lot. I think I mentioned MTLS, which is something that you get built in with Dapper, and a lot of people are like, wait, I already have MTLS that's in my Service Mesh. So that's definitely, there are some overlapping concerns, and this is a question that we get all the time. So things, for example, like MTLS, distributed tracing, metrics, resiliency, those are all things you can also do with, choose your favorite service mesh. Now, if you want this more at the application layer, Dapper is definitely the right call for you, or you can use these things together, which is what we're talking about today. So for example, the things that Dapper does absolutely not do is like any sort of traffic routing or traffic splitting. So if you wanted to do like A/B testing or canary deployments with a service mesh, that's like not necessarily what you can do with Dapper. Again, it's not running at that network layer. It's like much more, think of it as an application developer tool. Yeah, but instead, right, you're gonna get all those different application APIs that I was talking about. So things for building workflow, things for building state, etc. And so with that, I'm going to pass it over to our service mesh guy, Manuel, and he's going to talk about Cilium.
Thank you. I'm not so sure about the term service mesh guy, but let's see about that. As you can, if you know me from like some previous talks, for example, I did at KCD Denmark, you know that there are like two hearts beating in my chest, right? On the one hand, it's kind of like the Dapper heart, which is why we're here. And on the other hand, it's also like the Cilium heart. Given the current situation, I think Cilium is riding the hype cycle quite well, and I think there was at least two talks mentioning Cilium today, at least here already, so you can see where we are. But just for the super quick one-on-one on what Cilium is and why are we here. Cilium by itself has an implementation of a service mesh, no surprise here. And what they did very early is they built on the sidecar-less service mesh, right? So back in the days with like traditional Istio, Linkerd, whatever, it was everything about sidecar. And as Alice said already, the sidecar train is coming to an end, at least for now, potentially, who knows? And they started super early on providing this sidecar-less service mesh experience. They do this because they use eBPF for like kernel extension in the user space, right? So we heard about it, I think, twice today as well already. So there is a reason for it. And therefore, Raymond from Isovalent, which is like the EMEA field CTO, likes to call it, Cilium is like the Swiss Army knife for Kubernetes networking. And it really is at that point in time. Because based on all the functions and all the capabilities they add, and there's like this shiny image on the right, which I'm not going to read because you can do this by yourself. It can do a lot of things, like really a lot of things. Not only can it do all the lower level networking, layer 3, layer 4, whatever you name it, but you also can use this with like extra capabilities for like layer 7 if you want to do like traditional HTTP routing, for example. So it really is the foundation for modern networking. What we focus on today for this talk is the Cilium multi-cluster mesh, or Cilium cluster mesh, whatever you want to call this. And this is basically this is basically the possibility to combine clusters together to let them act as one, right? Like as shiny and as fancy as this sounds, that's what it eventually comes down to. How this works is, since Cilium in itself is shipped as a CNI, right? So it's a container network interface, it can do all the crazy things on the networking level. And since it's using eBPF, it's really low in doing this. And how this works is they introduced a concept for like once you wired clusters together, they introduced a concept called global service. So you can take one of your Kubernetes services, put an annotation on it, right? Kind of patch the service with this annotation, mark it as a global service, and once it's a global service, the magic starts to happen. What happens in that scenario is, and I took this image from the source here, if you have two clusters for this example, they could both be running on AWS or whatever. You have the Cilium agent running on each, which is the CNI at that point. And for the truth, there's a second component called the API mesh server, if I remember correctly. Those guys start synchronizing information about those exposed services, right? And if then one of the pods here wants to reach a pod on cluster B, the agent will intercept the HTTP request, rewrite it to the private IPs that you have in this cluster, and put it over either in tunneling mode through a VXLAN or per direct routing, depends on the case, puts it over to the cluster, and there the agent sees it again and can forward it to the actual destination. And this is pretty cool, because since it's following the normal way of traffic forwarding within a Cilium cluster, you get all the other benefits that you have at the same time, right? Like you still can enforce network policies, for example, or cluster-wide policies or whatever, just like everything. So it's really in the middle of communication and allows for cases like the multi-cluster model. If we look at the service invocation as like an example from what Alice already explained, from the data perspective, there doesn't really change much or anything. Like previously, the data sidecars would have communicated directly. Now there's the Cilium CNI in the middle, which enforces communication in either way, but it's totally transparent to Dapr at that point, right? So at that point, Cilium is more like an add-in that you put in the middle, and that magically does things, and Dapr doesn't even know about it. So because this was a lot of theory at that point in time, let's pray to demo gods and hope that things don't completely break up. So for this one, what we want to showcase today is we took an example architecture having one application front end running on Google Cloud, which then calls through a gateway on two AWS clusters, where there is a gateway, which then pushes things forward through a message broker eventually, and there are subscribers on this message broker that is responsible of ditching the messages, which eventually is a Redis store. But as you can see, all services, no matter what, they all go to this one Redis on this one cluster because they can act as one. With that being said, let's look up some code. Oh, well, not some code, some structure. Here we go. I make this a bit bigger. Yeah, this is just chaos.
Yikes.
So is this big enough? I think it is. I think it is. All right. Do you want to show before the application? And then I can do it? OK. There we go with the good desktop. So we did a dummy application at this point in time. And you can select two communication types, right? We can either do service invocation or publish subscribe. We're going to start with service invocation. We just have some message types here, which are totally irrelevant, like it's just a type. And we can do some messaging. So we could do service invocation at that point in time. We just go for hello rejects.
I almost spelled that in German.
Almost, but I fixed it on the fly.
And then if you press submit manual,
yeah,
I will just walk it through. But so yeah, hopefully the Wi-Fi is working. But essentially what this is doing, right, is using the Dapper service invocation APIs to call into the, this is running on GKE right now, calling into the AWS, in this case, they're K3S clusters, calling into the first one. And so this like invoke endpoint is specific to Dapper. And then we're invoking what's called, in this case, the C# service on the method A based on the message type. So this is like completely normal Dapper. I didn't do anything here to change Dapper. I just am getting the cross-cluster from the Cilium multi-cluster mesh, is my point. And then similarly on the PubSub side. So if we switch to PubSub, again, I'm going to be routing from GKE into one of my AWS clusters. In this case, the message type defines the topic. So I'm publishing on topic C in this case, and then I am sending this to AWS, and I should see, again, a similar message where I'm invoking that publish endpoint. Perfect, yeah, so PubSub is the name of the PubSub. In this case, we're denoting a Redis message broker, which Manuel talked about on that architecture, and then we are publishing on topic C.
So far, so good?
So far, so good.
So far, so good. All right. But how can we actually prove that what we all said, or what we both said is actually true? So there's multiple ways to do that, and I'll try to walk you through it, and hopefully it will make sense eventually. So this is K9S. I'm pretty sure you all know it. On the left side, there's the one cluster in AWS. On the right side, there's the second cluster in AWS, you could have guessed. And if we look at the front end or at the gateway, we already see those events coming in, right? So this is the service invocation. We called it with the message hello reject. So it's here. On the other hand, there is the publish, so the PubSub to topic C, as Alice said, and there is the message hi GKE to AWS. So the request has reached at least one of the clusters already, right? But how did things come from here, and how did this actually work?
And these are both the AWS clusters.
Yes.
Not the GKE ones. These are both the AWS clusters.
Yes, correct. So if we want to look at a tool I learned about yesterday, which is called Redis Insights, port forward. Typical. Let's quickly. Well, actually, I show you like this. If we look at what Alice said, there is the components in Dapper, right, which control where data is persisted or where times of things are loaded. If we look at the ones, here's PubSub and state store, right? If we look into one of those components in detail, we see that it's looking up a local resource, right? Like it's always looking up, in this scenario, Redis master, Redis service cluster local. It's a local endpoint. So this means we need to have a local service, right? If we look at the services, in here, we see that indeed there is a service, but if we look at the selector, this is like bogus, right? Like no, there will nothing matching on this key pair. What is important though is the annotations, right? So you can see there it is marked as a global service, and it is marked as a global service on both clusters, which I'm pretty sure will not surprise you. Here we go. It's also marked a global service here. What changes, though, is the way how we split traffic. So on the one cluster, I give it an affinity and tell it, all right, please always use a remote cluster, because I tell it it's not preferred, but we use it to force it, right? So this one will always go to a Redis on a remote, while on the cluster where it actually has the Redis running, it only has the global service annotation. So traffic will always be split or forwarded in terms of Redis connections from this cluster, from this little shiny cluster, to this little shiny cluster. But did it actually work? Like, do we have data in our Redis? As you can see, I just did a port forward to the second cluster for Redis Insights. So let's hope we do see something now. What we learned today is that sometimes rebooting this thing is the best idea. There we go. And there we go. So there is the data. I'm not sure if you can actually see this. And I'm not sure how I can zoom in here.
So essentially what's happening there, right, is like this is just connecting to the Redis clusters, or one of the Redis clusters, which is running both the message broker as well as the state store in this case. And then Dapper has the idea of what's called an application ID. So it has an inherent built-in identity. And that's why you see C# service in there, because that is the service that's being invoked by GKE in this case, as well as we have Python subscriber, which is a subscriber application to the PubSub, in this case written in Python. Again, Dapper is super polyglot, so it doesn't actually matter what languages we're written in. We just had written that as an example, and then each of the streams is specific to those topics within Redis streams.
Correct.
Cool.
And as for the state store, as Alice said already, if we check the actual state store component on one of the clusters, just as an example, right, doesn't matter at that point, and we look at this, we also see the same. So like from the Dapper perspective, Dapper really thinks it's a local endpoint, it's his Redis running on his cluster, and Cilium takes care of forwarding all the things to the other cluster as we thought. But there's another cool way how you can actually show this. And I'm pretty sure that for those of you who use Cilium already, you know about Hubble, right? Hubble is like a shiny little, well, not really little, but a shiny UI to illustrate traffic flow. So if we look into this and we select the namespace of our applications, we can see, now comes the fun part that we practiced yesterday, how to zoom in properly and not screw everything, that we have those services that we talked about, right? You can see on this little dot here that those are running on one of the clusters, so ECS, K3S, doesn't matter, and that there is the sidecars, on the other hand, which facilitate communication, right? And if we pick one of those on those lines and we scroll way down, we see that those sidecars go to the Redis, right? And as you can see here, it also detected that this is running on the second cluster. So Cilium is really taking care of all those moving bits and pieces by rewriting the packages and all the things to move things here. Why would you do that? I mean, this was kind of like a fun example, right? But you could also utilize this for fault tolerance, for example. Like if you mark a service, if you take a service, mark as a service, but don't screw with the traffic affinity as I did, then you could do you could use it to improve visibility, make it more fault tolerant, right? Because Cilium will see if one of the services, one of the clusters is down, it will forward all the traffic to the running replicas in the other clusters and things like that. So there's really a lot of ways how you can interact and how you can leverage these capabilities. And since it's so transparent from the Dapper point of view, your application developer won't have to care, right? Like your typical application developer just develops against the Dapper SDKs. And for like those ops guys, platform engineers, I mean, it doesn't matter what tech you put on them, but those guys have like the full control of building those fault-tolerant applications. Even like, we could show some more, like we could do some more publish subscribe at that point in time, for example. But you've seen that there is that on the graph, on the Cilium graph, that it forwarded the traffic. So even if I now did some messages, and we look into the logs from the application, we see here's 555. This was the last one we did. If hello console. No. If we look into the log here, there we go. We see the others, right? 444, 222. So it really, like, requests will land on both clusters again, and all super transparent at that point in time. Thanks, demo gods. I was expecting something to screw up, but at least this does not happen for now.
Just your desktop.
It's just the desktop, but that's okay. Because usually I use it in list view, right? So it doesn't matter how many items are stacked on each other.
So I guess just like to close, if you go back to the architecture for 1 sec, just to close on the architecture, right? Like, so what you kind of saw today, in case that was all a lot of K9S, the front end, again, was running in this case on GKE. This was, again, completely Dapper, transparent, not necessarily, had no idea that Cilium exists, but we are calling into one of the AWS clusters because we have Cilium multi-cluster mesh running there. It is acting as if those two, in these case, K3S clusters are the same. And then we have Redis only running on one cluster there, being used for both the Dapper state and PubSub APIs as the message broker, as well as the storage key value store. And then, yeah, that's kind of it. And you can intentionally run this on any cloud. So you could swap out one of these AWS clusters or GKE clusters just by swapping out those components, those Dapper infrastructure components, as I talked about earlier.
The fun part?
Okay, yeah. And that was mostly it. We just wanted to say, come by. We'll be at KubeCon all week. Come by the Diagrid booth if you want to learn more about Dapper. Or we also have a Dapper booth, many booths that we'll all be wearing Dapper shirts. You'll see us. And we also have a party on Thursday that we're doing with Upbound, which is a Kubernetes arcade night. So if you want to join the Boom Battle Bar, I'm not sure why it's called that. I didn't choose the name. But yeah, stop by. And thank you so much.
Thank you so much.
A lot to digest. Great talk. Questions? Okay. No questions.
So either I was expecting something from you.
Yeah.
Do you need a mic?
I don't actually need a mic. It's okay. For the stream. Oh, you need it for the stream. Okay, then. So first off, thanks very much for the talk. It was great. I'd be interested in your take on building a multi-cluster between two different data centers, because I mean, if you're just using AWS, it's fairly simple with VPCs and everything. What would your take be to gain local visibility, which as far as I know you need to build multi-cluster? If you're building it, say, between GKE and AWS, what would you use as a tunnel?
That's a good question. I think it depends on what kind of environment you're running in then, right? Like you will need some sort of layer in between. What I see if customers that I work with do is they use WireGuard to wire the nodes together, like to allow for the private IP endpoints and stuff like that. So far, that worked pretty well, at least in the examples, or what in the examples, in the clusters and environments we are running. But I would not go for this is the golden bullet. Like it's one solution I saw working. There's probably more. I would also be curious to see them, but like my first experiences so far is with WireGuard as the foundation, and that worked pretty well.
I've also had a few customers using an open source tool called Scupper. This was like very Dapper specific, yeah. And there's a full Dapper community call on this. It's like SKUPPER. But we have a couple users that are using that for Dapper cross-cluster communication, but it doesn't have to be Dapper specific. It's just an open source project. Yeah, no worries. Good question. Happy to answer questions after too.
So I'll catch up with you and Maurizio sometime this week to talk about how you could integrate Dapper and something like Kratix for doing opinionated provisioning on multi-cloud, multi-region, multi-cluster.
Yeah.
How to do that. Is, high level, is it possible?
From a provisioning perspective, there's really good integrations with Crossplane. Like we work a lot with Crossplane for the provisioning perspective, because Dapper doesn't do any of the provisioning, right? It's just the connectivity. Yeah. But like totally, it's very popular. I would say there's also some integrations with the Humanitech product, Score, and the open source one there. That's not a provisioning. I believe that also has to be provisioned, but it has the whole app package definition, description there. But as far as Kratix goes, I don't know. I haven't come across that in terms of my customer work. Yeah.
Thank you very much.
Cool. Thanks, guys.
You are the next, right? Faika? one talk, then lunch. We have 3 minutes. We have 3 minutes. You take your time. Okay. Is it working?
This is the other thing. How can I drag this to the...
You just click on the bar.
Not this,
Not this one. Which one is it? Sorry.
This one.
Working? Okay, perfect. We have 1 minute. We have 1 minute. I will introduce you, okay? And then you can just continue. Before that, I will ask some questions.
I just need to know how do we drag it. So I'm trying to drag this again.
So actually, you can't overlay in MacBook. So
Oh.
hello. Okay. Hi everyone. Just one more talk before the lunch. Okay. So the talk is the hidden brains of Kubernetes meet controllers powering the cloud. Okay. Before starting the talk, just tell me how many built-in controllers are there in Kubernetes. Tell me the count if anybody knows, and I will give you a CKA pin. Okay. So how many built-in controllers are there in Kubernetes? Anyone? The count? No. That's way too high. Anyone? Yeah? No, no, no. 4? No. It depends. It depends. Yeah. Anyone? Yeah, exactly. I will give you the CK pin tomorrow. I don't have it. So, okay, let's welcome Faika Ansari from India. Clap. Okay, let me ask a couple of more questions. How many controls have you built in your entire like experience in Kubernetes? How many controllers? No one? Have you built? Yeah. 2? Anybody more than 2? Any bid for 11? 12? Okay, closing at 10. So let's start, Faika.
Yeah, that's awesome, everyone. Thank you so much for coming. So today my talk is about controllers because the day I started my journey in Cloud Native, I got used to so many controllers because almost every single project that I ever used was it itself a controller. So controller is like no big thing. It's like everything, almost everything, every project we see has an operator, has a controller behind it. So I really wanted to talk about it. I wanted to highlight the power of controller and talk about how it has actually done so much for the whole cloud native thing and extended Kubernetes beyond just Kubernetes. So before starting, a little about myself. I am a software engineer at Acuity. I am also a CNCF ambassador and a certified Kubernetes administrator. If you want to connect with me, there is a QR code right there. Oh, I'm also a GitHub campus expert, so which is basically like representing GitHub and being a leader for GitHub and things like that. So if you all are interested in any GitHub education benefits, it's something that I generally do. Now I would quickly take a brief of the agenda that we are going to go through today, which is why Kubernetes controllers are the magic glue of the ecosystem, of the CNCF ecosystem. And I would also go through the problems that Kubernetes controllers are solving, and we'll see a live demo of how you can build one Kubernetes controller very much easily without much hassle, and you can just keep building stuff, and maybe one day you'll come up with something that becomes in itself a big solution. And we will then have a quick dive into some of the project code bases who are using controllers internally. So yeah, before getting started, I'm quite nervous. This is one of my first technical talks, but I'm really excited and I'm really happy that y'all showed up. So the big picture about why Kubernetes controllers are the magic glue. So we know that in general, in Kubernetes, there is a misconception that Kubernetes is an API server. It's all about an API server because sometimes we often end up calling Kubernetes an API server, right? So people who are not very much into Kubernetes things, they don't know this, but technically a lot of people know that the Kube API server is sort of referred as Kubernetes. But do you know that Kubernetes in itself is a collection of controllers? So when I say that, everything, almost everything that is managing Kubernetes on top is a controller, be it a node controller, which is basically managing the health of the nodes, replica set controller, which is ensuring that pods are correct, then the job controllers, which are running bad jobs and things like that. HPA is a controller, ingress controller, scheduler, which is again a special controller assigning pods to different nodes. And of course, not just this, we have custom controllers. So I think everyone who's working somewhere is familiar with some of the other projects in Cloud Native, which in itself is a custom controller, which is an extended version of controllers. Like what I have here is Argo CD, Cargo, Kiverdo. These are some of the projects which are just giving extensibility to Kubernetes and extending the solution in general. So everything in Kubernetes is managed and controlled by controllers. What controller is doing is something we are already sort of familiar with. What happens if I delete a pod? So if I delete a pod, does Kubernetes know how to recreate it? Of course not. Kubernetes knows how to do things on top level, but controllers is what gives it the manager. So what keeps everything running very smoothly is a Kubernetes controller. So like if you see the diagram, the controllers are automating things. We define a desired state. A user defines the desired state, but maintaining that desired state is the job of a controller, as we know. So what controller does, like for example, here we have a replica set controller. What it does is it keeps watching the actual state, which can be mismatched, which can be correct. It always keeps matching it, checks if there's a difference, and reconciles, or what we call runs a control loop to make sure that the actual state is equal to the desired state. So that's a simple control loop that helps Kubernetes have the property of self-healing. That's one of the properties. Now, this is also, we know that controller follows a very similar flow or what we call as a loop, control loop, that is watch, reconcile, and act, which we also call as keep watching the resources that you have defined, and then reconcile, or basically check the differences between the desired state and actual state. And if there is a mismatch, then just act on top of that resource. So that's what we are doing here. We're observing the desired state, we are comparing it with the actual state, and then making necessary changes. And that's the job of the controller. Now, this feedback loop is what is making this particular system very reactive and self-managing. Like a user is defining the desired state, then Kubernetes API server is basically storing that desired state to etcd. And now, if there is any deviation, like you see that crooked box, controller will make sure that it is reconciled and presented to you in a correct form. Hence, Kubernetes is not just an API, is what was the context of these 5 minutes. Kubernetes can automate, scale, and self-heal because of controller. Controllers make them do all of these things. But now, done with all of these heavy lifting, what are the extraordinary problems that are solved? We know what Kubernetes is doing, but what ahead of it, right? So let's look at some of the real-world power of controllers that I am so amazed of, because almost every Kubernetes cloud native project that I go around contributing has these controllers, and I'm so excited to see them and how the whole architecture is nothing else but a controller's architecture. So that's very cool. So about this, Kubernetes controllers, as we know, are the backbone of solving problems. And I think in next few slides, we will see and explore how these controllers are solving some of the extraordinary problems. But before that, do you know what happened if there was no controller in Kubernetes? A user would have basically applied their specifications or their configurations, and every time they apply their configuration, the Kube API server would have done its job, that is, store it in the etcd. But what if later on, who ensures that it is stored in the etcd in the correct form? Nobody. So maybe the user would have never come to know that the configuration that you applied is in the correct state. But with controller, the controller knows and knows how to update you with the correct state of your specification and of your deployment. And with that, this is one of the internal things that Kubernetes is doing, the Kubernetes architecture that almost all of us are familiar with. And if you see, this is so much a collection of controllers in itself. The whole architecture is representing a controller. So if you see, there's a kube controller manager, which is basically the manager for the core clusters. Example, the nodes, the deployments, and the replica sets, job controllers, all of those stuff. Then we see there is a cloud controller manager, which integrates Kubernetes with cloud providers like APIs and load balancers and all those stuff. Then Kubernetes has a kube scheduler in its own internal architecture, which is not strictly a controller, but it is also sort of doing the same thing, which is scheduling and updating the pods. But let's get outside of Kubernetes now and see how controllers can be used outside of Kubernetes and how we can do more stuffs. And that is where we introduce operators. So controllers are like control loops that runs against your resources, right? So controllers run against your resources, but operators runs custom control loops against your custom resources. So everything is now customized. Now it's all in your hand. You can define custom resources, which we call as CRDs, custom resource definitions, and controller, which is, again, your custom controller. You can define how you want the controller to automate things or how you want it to manage your deployments and everything. So you define a custom controller to run a similar control loop as Kubernetes was doing for itself in the core cluster, and that is how we move. Now, I obviously had to list all of these crazy projects that I've been looking at, I've been contributing to. So these custom operators are almost everywhere in Cloud Native. Like, all of these projects are at some point using these custom operators and are built on top of it. Like, operators are solving the problems of GitOps and CI/CD, where Argo CD is like a declarative GitOps-based solution, which is sort of like continuous delivery tool that user uses to manage their deployments and all those stuff and make sure that the desired state is there from Git to clusters. Flux is, again, a similar solution in GitOps. Then controllers and operators are also solving the problems of multi-cluster and infrastructure orchestration. Like you see, Crossplane is one of the examples, which uses these controllers, and it provisions the cloud resources like databases and all of those things, manages things around it. Karmada is, again, one of the similar examples as Crossplane, and Cluster API, which is, again, internal to Kubernetes, is also something doing the creation, scaling, and all those stuff. Operators are also in storage and data management, which is using Rook in itself, which does those things. Networking and service mesh, that is Istio. Also one of the project where I was an LFX mentee, uses operators, and of course, the Cilium, storage and data management, almost everything uses an operator at core. So all these projects at some point is leveraging controllers to automate their reconciliation loops and ensuring that their actual state is equal to the desired state. But let's see one clear example of how it flows with, say, one of the examples, Crossplane. So I just came up with Crossplane because the architecture was very much easier to explain how operators are doing its job. So now that we have seen how simple controllers make your work, let's zoom out and look how the same controller model can scale up to solve extraordinary real-world problems. So today I'm here to talk about the architecture that represents the core ideas behind controllers, which is how controllers will watch, reconcile, and then act across complex environments. So this is Crossplane's architecture, and Crossplanes does not reinvent Kubernetes. It is just extending the existing solution and with additional CRDs and making more things like connecting with external cloud services like AWS, Azure, and all those things. So if you see the left side of this diagram, where developers are interacting with a Kubernetes, which is the CLIs and tools, developers and admins interact with Crossplane exactly as they do with Kubernetes, which is using CLI tools, kubectl, and client libraries, or even the user interface, that is the GUIs. Now that means you don't need tools or a different set of workflows to create operators and make operators work with your system. Now this controller includes specialized resource controllers. Now, like you see here, there is a custom resource controller, which is basically has a PostgreSQL instance in case of Crossplane, and then it reconciles data based on the information fetched from AWS, Azure, GCP, and things around it. So by exposing all of these cloud services and resources as CRDs, this particular controller is able to define everything in a simple YAML file or a JSON file, obviously, and version it in the Git and apply GitOps principles and GitOps automations to the deployments. So there is also a workload scheduler in this architecture, if you notice. This is also a part of this controller, which is basically intelligently placing these workloads across different clusters or clouds. That's the job of that particular controller. And the magic behind this particular architecture is that it is continuously reconciling the loop. As you see, the same pattern that we see in Kubernetes' core project is seen here. So if someone changes a resource directly in AWS, or someone changes a resource directly in, say, Google Cloud or Azure, this YAML file will basically detect that drift and then correct it, hence ensuring that the desired state is maintained. So honestly, this is so self-healing, and this is so cool that everything is just automated, everything is washed after, and you don't have to do anything. So controller is basically allowing this particular project, which is so famous right now, to act like a universal control plane, and it is also enforcing all of the policies and all of the things that you want, and into different environments as well, automatically. So obviously, since this is so interesting, do you not want to build one of your own controllers? Of course we do, because now that we have learned so much about controllers, that was some of the first things that I wanted to do when I realized the power of controllers. I also tried to build some controllers and do things around. But building controllers is definitely not that easy. So far we have seen how Kubernetes controllers powers everything from infrastructure to cloud to storage to networking and all of those things around. But how do we build one? So yeah, writing controllers by itself is super complex, of course, because as you see there on the screen, manually writing controllers is like writing so many stuffs. It's like writing Dockerfile, Makefile, managing dependencies, adding so many files like controller and all those things. But this can be sort of automated by some really cool operator frameworks that we'll come forward with. So yeah, but first let's understand what a controller does. So a controller initializes the API client, which is basically it handles authentication or any of the role-based access control stuff. It also monitors the API server, which is where it sets up the informers and watches, and changes to maintains local cache of the object state. Thirdly, it handles the events, which is like adding, updating, or deleting the events, or work queues, or rate limiting, and all of those things is done by the controller. And of course, the reconciliation loop that we've been talking about for this whole time. And glad we have operators framework, which is something that is going to help us build this controller and avoid all the mess that we had to create here, because manually writing it means defining your make file, which is basically having all the run commands, which will generate your YAML and CRDs and all of the other stuff. Dockerfile to build your operator's container image and all of those things. So let's see how operator frameworks helps us with that. So currently we have three different, in this presentation I have chose 3 different operator frameworks which are really good. And we have operator SDK from a very long time, but now we also have KubeBuilder, and then there is also Meta Controller. So to talk about this real quick, KubeBuilder is like a general purpose controller development, which you can use any day just because you just woke up and you're like, oh God, this is so difficult to always keep looking at this part of my cluster. I'll just go build a controller that will do this job for me and I'm done. So it's as simple as that. KubeBuilder makes your things very much easy, but on a very ground level so that anyone can any day just build it. It's not very production ready stuff. On the other hand, operator SDK is more like it needs lifecycle management. So there is something called as OLM, which is operator lifecycle management, and it is highly used in production-ready software. So we can use that as well. And then there are meta controllers, which are very much like lightweight and very webhook-driven controllers. So you just add a webhook to your existing project, and you don't have to do the very heavy coding stuff, right? So we will be using KubeBuilder because it is like very fun to build, and it's like it scaffolds your controllers, and also it makes sure that your controller has all the best practices, and it is built on top of our very own controller runtime from Kubernetes, so it is best for custom controllers. Okay, moving on to KubeBuilder. So KubeBuilder, as I said, is very, very flexible, and it is widely used. So let's jump into scaffolding a real Kubernetes controller using KubeBuilder and see the magic. This would be a quick demo of how I have built so many controllers and how you all can just start building controllers and what all we have to do. So before getting started, we might need Go to be installed. It will be great if we have the latest version. We will need Docker for containerizing the controller. We'll need kubectl to obviously interact with Kubernetes. And then we can particularly start. I will quickly share my screen. Okay. Yeah, I think I have it here. So I have quickly recorded it, although if there are any doubts, I can particularly do it because it might take a lot of time. I was taking much time on my PC, so I wanted to avoid that overdue. Yeah. Okay, so this is controller. Let me. All right. Yeah. So this this time we're gonna start with installing KubeBuilder first. So that is a simple command that I have used here to install KubeBuilder, which is doing the installation of KubeBuilder. I am trying to install the latest version of KubeBuilder. I just did it a while ago, so this is the most compatible way to do this demo. And then we are making it executable, of course, and moving KubeBuilder to my local binary. And from there, I would quickly So next step is I am creating a project. So when I say I create a project, I'm just creating a directory, project directory, and initializing KubeBuilder itself. So when I say that I'm initializing KubeBuilder, here I am initializing the project with the domain and the repository link, where it'll basically push all the scaffolding of my controller. Awesome. Once I have done this, once the creation of project is done, it was pretty quick. I created the API. So the Kubernetes the API code will be generated using the KubeBuilder create API command, which creates the API and links it seamlessly, which would have been very difficult without KubeBuilder. And there we use the KubeBuilder API command. I am creating the custom resources. I'm trying to create the controllers, entering yes, yes. And it just quickly does that for us. So this way we have the custom controller here. And now we're using the make command. So make is again something that helps us generate all the YAML files, generate all the CRDs and things like that. So we're using the make manifests to generate the manifests for this code. And as soon as we do that, we have things working, and there we have it. And now, let's test the controller. We use a make install command to run the install command of this controller. I'll quickly go through the make version of it as well. And make run. So now this will keep running the controller in the background. If you see, it is basically running the main.go, which is the main page where controllers are situated. Awesome. Yeah, I think that was it. That's particularly how controllers work here, but I think it wasn't very clear, so I would take you directly to the thing that we have just created using these commands, which is this code. Okay, I think it's just running out of my screen. I will make it full screen and then shift it. Got you. Yeah, so there we have the code base of what KubeBuilder just did for me. So I will quickly run through what we have done in this demo and what has KubeBuilder done for us. So let me quickly come back here. Yes, so if you see here, there is a makefile. Yeah, I'll rather come here. Okay, so we have a makefile generated, which has all of those custom targets, like you see, make install, make target, all these things around. And we have a Docker file, which is again for building the operator's container images right over there, which is again generated directly by KubeBuilder. And we can obviously customize it later on, but the heavy lifting is already done. Then there is a main.go file, which is basically the main file that allows you to immediately launch your functional operators. But currently, it's like a no operational function operator, but you can obviously add your custom logic to it. And this file, the main.go file, is what will serve as the basic point where you start your operator to work. Then there is a configuration folder, which is again that contains a lot of customized manifests. So what I mean by that is it is used to manage and deploy the operator's configuration. Then there is also a hack folder, which the makefile is obviously using, and it includes all the boilerplate source code, which is useful for inserting licenses and all those things. There is go.mod and go.sum, which is, again, dependency management, which is, again, done by KubeBuilder itself. There are CRD definitions, like KubeBuilder simplifies the creation and management of CRDs using the CRDs, as you see there. And there is a controller logic, which is a controller folder, where you will be writing the logic for what you want KubeBuilder to do. Awesome. I think we have very less time, but I would quickly want to go through what we just saw. And this is obviously what we just saw right now, which is the process. And KubeBuilder is the most flexible and what we call it is a widely used thing. And this is what KubeBuilder is basically doing under the hood. What it just did was this diagram. Let me quickly. Yeah, it created the process, which is the main.go file. It set it up the manager, which is basically the controller to use the watching resources. And then we have controller, which is what you see on the screen as SIG-K8's controller runtime, which we're using, where each custom resource has its own controller. I just have 1 minute left, but I would really want to take this up. So we're using caching clients, reducing API calls, and doing all of these things. This is the architecture which this controller is following. The reconciler, which is, again, the reconciler library from Kubernetes, which is where the core logic goes. And webhooks. Webhooks, again, you can modify or validate resources using webhooks. And all of this entire architecture is done by KubeBuilder itself. A quick overview of Cargo, which is, again, one such similar project, which is Kubernetes native progressive delivery tool. And it also uses a similar architecture. So now, next time you ever go to any cloud native project, you'll find a similar architecture where there is API, where there is CMD, makefile, internals, and what is it exactly? It's a controller in hand. So I always have a saying that if you know the power of controllers and you always keep building controllers, at some point you will eventually end up building a big solution, which probably all of us will end up using, just like Argo CD came into existence, or Captain, and all of these projects came into existence. So Kubernetes controllers are not just about automating Kubernetes itself, but they are a way to automate the entire cloud natives ecosystem. And with the right idea and tools, you can build something that transforms how we operate in the cloud. So who is building next? That was it. That was for my talk. Thank you so much, everyone, for attending, and thank you so much.
Any questions?
First of all, very much thank you for your very enthusiastic and inspiring talk. So really love that. One question, because you use now KubeBuilder actually to put out a lot of boilerplate code and that kind of stuff. My question actually was, where do you bring your own, in this case, logic to the mix? So you have this guestbook and that kind of stuff. Where do we actually define what the guestbook should do? So we define, in this case, the guestbook CRD, for example. Then we deploy the guestbook CR. Where goes the logic, in this case, to do something with that CR in your process?
Sorry, if I get your question correctly, where do you find the custom resource?
Yeah, no, actually, where do you put your own logic, in this case, to the mix?
Oh.
So the strategy actually to deploy it. So you deploy, in this case, a guestbook. That guestbook actually needs to result into something into the cluster.
Oh, yeah. So basically, the controller logic that goes inside the controller folder itself. So when I deployed the guestbook, what it created was a controller folder and a config folder. And the controller is where my actual logic will go inside. And the main.go will just take reference from controller. Main.go is just like the entry point. It links to the controller folder, and that is where your custom logic and everything goes inside of. So if I take example of another project like that I was showing, I don't think I have a Brave here. Okay, yeah, we do. Yeah. There you go. So if you see, all the controller logic, internal logic, and everything goes inside the controller folder in itself, which is where you define the things. So we have a controller here, if I'm seeing correctly. And there we go. Was that the question? Yeah. Okay. Yeah. So I think KubeBuilder right now works only with Go language, but if you use operators SDK, that also works with Helm and Ansible, Go language, and there are also some operator builders for Python, things like that. For what? Oh, Rust? Yeah, so I think meta controllers can help with that. It helps you build your own webhooks, and that way you can use Rust and all those things. Yeah, thank you so much for your question.
Any more questions? No? Thank
That's
you.
really cool. I'll see you around at KubeCon, and thank you so much for attending my talk.
All right, so are you? So I know that you have lunch, so you may be tired. So I will try to make it engaging, so then you're not sleeping. Otherwise, it's going to be painful for me, to be honest, to see you sleep. So are you ready for the service mesh? 1, 2, 1, 2. You hear me? Okay, is it better? No? They don't? It's better? Okay. So are you ready for the service mesh wars, the new hope? Yeah, okay, awesome. Okay. So, service mesh, yeah. So my name is Henrik Rekstedt. I'm a cloud native advocate working at Dynatrace, a bit 4 years now. I'm also an observability geek. I love observability in general. I'm a CNCF ambassador, and prior to my experience with Dynatrace, I've been spending my career doing performance engineering, so testing, breaking, tuning, having fun. And that's why I still love the performance engineering practice, because I think it's an amazing practice to learn things. So I try to produce content when I have time on a YouTube channel called PerfBytes on the bottom. And otherwise, I started 3 years ago a channel called Is It Observable? Everything about observability in general. So check it out, it's there. And it deserves feedback. If you don't like it, let me know, so that I can improve my content. So let's start. Small disclaimer. A long time ago, in far, far away, in the galaxy, there was a lot of service meshes doing war. They only want to control the networking in our Kubernetes environments, but we didn't know which one we should trust. So this presentation here, I made a lot of tests to test it out, their solution, and I can guarantee that I didn't break any Gorilla, any boats, any cube were destroyed. I was very gentle with them. And the intention of this talk is to not blame any of the project. It's on the opposite, give feedback to these different projects that are under the CNCF umbrella, and also give you some tips about their solutions. All right, so let me introduce the different clan in this presentation. So we have Kuma coming from the Kong, has been doing a lot of things on the gateway side, and they have a service mesh called, under the CNCF landscape called Kuma. We have the Linkerd team. It's the company behind the scene is Beyond. So they do mainly HTTP and gRPC. It's the bounty hunter for HTTP Go requests. Then we have Cilium. So they drive pretty well. You'll see that I put it this pilot because you'll see there's something behind why I choose that character. And then of course we have Istio. The Y is Istio, that we've been out there doing great things, so we can trust him. He has good reputations within the Jedi. And we have his young Padawan, ambient mesh. So the idea here is that we're going to compare those solutions and figure out who is the best one, depending on our needs and our implementations. But there's a new hope. I don't know if you followed. Pretty sure that you followed, everyone. There's a new hope in the galaxy. Then it's the Kubernetes, the Gateway API. The Gateway API is there to simplify our journey, providing CRDs that will be common to all those solutions that then we can configure only using those CRDs, and we don't have to go through those specific CRDs of each individual solutions. So they do, of course, mainly today ingress, load balancing, traffic splits. There are a couple of service meshes features, but you see that not all of them are is on the way. There's a Gamma initiative behind the scenes to add more features on top of that. So let's be very patient, and in the future, we would have more options to configure all those rules and those policies using the Gateway API. So just for those who have never heard about the Gateway API, there's the gateway, and then you define an HTTP route, or gRPC route, TCP route. Depending on the protocol you use, you will use one of those CRDs. And then, of course, when you use them, similar to the ingress that we used to use in the past, there's a gateway class where you say, oh, this is going to be handled by Nginx or Istio or Kong or Linkerd. So this is how it works usually. But, so it's very easy to configure, nothing special. But you see that there's a but, there's a no. Why a no? Because you see that a couple of features are not there, not implemented, so you end up doing part of the configuration with the Gateway API, part of the configuration with the custom CRDs of the service mesh. So it's a bit inconvenient as of now. So you need to know both worlds, which is kind of a bummer. So if you stay with me, I hope, during the next 20 minutes, 25 minutes. So we're going to first cover what do we expect from a service mesh in general. And then we're going to compare each of those solutions, looking at the components that they use, the design experience, because we'll see that we will have to design, of course, different policies, and the observability that they bring, and how complex it is or easy it is to configure the observability. And then I've did a benchmark, so I will share some results about how much latency they are adding in our applications and the CPU or memory consumptions that they need. And at the end, I will give you some conclusion. So you have to stay until the end to get the conclusion. So don't try to run away. Wait 20 minutes before run away. So let's start with the components. For those who never heard about a service mesh, well, it's super easy. There is a control plane where you're going to basically configure, and the control plane will reach out to proxies, because you need a proxy at the end, and to define the different policies that you have defined, so ingress rules, traffic split, whatever you want. And then in the bottom, your application plus the proxy are called data plane. And then which is great is the proxy is going to be handling the traffic that you have with your workloads. And they are providing out of the box telemetry data, so logs, metrics, and traces. So without doing an effort, you get some details about what's going on under the hood on the traffic level. And then, of course, you need a proxy. A proxy you need, and there is two models in the market. There is the sidecar model, which is the most well-known format because it's been out there since many years. And now there's the new model, sidecar-less, where you don't need a sidecar. So the sidecar model is, I would say they have some downsides in the sense where you need to add an extra container to your workload. So your workload has been mutated. They add a container, sidecar container with your proxy, which means at the end, if you need to have the service mesh, you need to restart your workload. Transparent routing without any restart. And then you have the serviceless, the sidecar-less, sorry, where here you have two types of proxy involved. Usually there's a layer 4 for TCP communications, and then you will add another probably proxy for the layer 7, so HTTP, gRPC communications on the top of that. So if you go to those solutions, we have, of course, solutions that are sidecar-less and others that require a sidecar. So Kuma, Linkerd, and Istio requires a sidecar. And they use, for most of them, Envoy, except for Linkerd that has their own proxy, supporting only HTTP and gRPC traffic. On the sidecar-less, so I would say Cilium, they have a Cilium mesh, and ambient mesh. It has defined a new ambient as a new proxy called Z-Tunnel that is mainly designed for TCP communications, so layer 4 communications. So let's cover the force that you expect from a mesh perspective. So there are a couple of features that you need when you're handling microservices in general. You don't want to handle those type of rules in your code, so that's why you rely on a service mesh to do that. So you want to basically handle the incoming and outgoing communications or egress communications. You want to have a mutual TLS, so encrypt the traffic between the pods. You want to have the retry logic if in case there's a problem. Any security, so authorization policies involved, rate limiting, circuit breaker, and of course observability. So that is basically what we expect in general from a mesh. And in those solutions, most of them, at least the sidecar one, they support all the features that you have in the, I would say, the force of the mesh. The sidecar-less doesn't have all the features as of now. They have few of them that are covered. I think I made a mistake on the timeout. Timeout is supported with the HTTP route from the gateway API, but the other one doesn't have the full-fledged features, which means you have part of the features, not everything. So depending on your needs, you have to consider that aspect as well. Now, let's cover the design, because those features require some specific design. So you need to understand how those solution works. Starting with Kuma. So Kuma, if you never touched a service mesh, Kuma has advantage. It's super simple. You have a CRD for each features. I want to do timeout. I'm going to use the mesh timeout. I want to do traffic split. I'm going to use. So it's super simple in that sense. And the way it works, you have a gateway on top. So either you use the gateway API, if you want to use it, of course, or you can use their CRDs. And they have this concept. There's a mesh In the mesh, you have a data plane, and then in the data plane, you have services. So then, when you apply a policy, you say, where do I want to apply it? In the mesh, data plane, or on a service level? And then to add your application in the mesh, as expected, you just simply need to add an annotation to your workload or your namespace, and that's it. You're part of the mesh, and the routing will happen. Linkerd is support, of course, the gateway API. It has different type of concepts. It has this notion of server, so you need to define exactly all the routing of your application, which is make the experience more difficult. That's why they have a CLI called Linkerd, where you can inspect. And by inspecting, it could guide you and create those server objects, which is interesting, again. And on the most of the mesh perspective, you can configure the load balancing, the traffic split with those objects. So it's very simple. And then on the bottom, on the proxy level, they have specific objects that will touch the Linkerd objects, Linkerd CRD, so then you can configure the proxy locally on the workload. To add an application on the mesh, you don't add an annotation on the namespace, because for some reason they don't support it. You have to add it at the workload level, which is kind of a bummer. That's why they have this feature with the Linkerd CLI called inject, so they can basically add on the fly those annotations to your YAML files and apply them. So I think from that perspective, it would be so much easier to have it on a namespace level. Cilium, so Cilium, I would say I have added them in the list because they have Cilium mesh, they call it mesh. But you will see that the way they're handling it, it's mainly through their networking features that they have with Cilium, using eBPF, so very fast. You can do Cilium network policies to authorize traffic or not on layer 7, layer 4. They have this integration with Envoy, so you can add also an Envoy, so it's add an extra daemon set called Cilium Envoy. And you can do most of the configuration using the gateway API. But for the rest, there's almost nothing. They have this notion of Cilium Envoy config, where technically you can configure similar to other objects the proxy, but maybe I didn't get it, but I never succeed to do it. So if you succeeded to do it, let me know, because I would be very interested to know how to do this. Istio has very well-known objects, so, destination rule, virtual services. You need to define the virtual services, the destination rule or service entry, but you can do everything with the gateway API. Most of the features of Istio is configurable through the gateway API, which is nice. And then on the proxy level, they have this Envoy filter, where you can configure the proxy level from the Envoy filter. And it's quite easy. I didn't find any problems for this. To inject the workload, to inject your workload into the mesh, you need to add a specific CRD, specific annotation, sorry, called Istio injections enabled. You can add it on an namespace or on a workload, and that's how you add the application into the mesh. Ambient mesh is going to be 100% configurable the same way as Istio. So if you have experience with Istio and you want to move to ambient, there's nothing complicated. And they have this notion of Z-tunnel that do as a daemon set that will manage all the TCP traffic of your node. And then you can add, if you need to have some layer 4 rules, for example, request timeouts, circuit breakers, like this, you can define a waypoint. So in a namespace, it will add an extra workload in your namespace to manage that type of communications. So it's very easy. And then similar to the other product or solutions, to add something in the mesh, you simply need to add a notation. So one is just to add the actual namespace into the ambient mesh. And the other one is you can define at the workload level that, oh, I need to use this specific waypoint. So then the application will know that you will use the Envoy to manage the layer 7 rules. So at the end, if you look at this, I would say I looked at the documentation perspective and the experience to design things. I think from just easy of use, Kuma is just wonderful. It's so easy to do it. I'm not saying it because there's someone from Kong in the room. Not at all. But from a documentation perspective, it's easy to use. The feature coverage is perfect. And the gateway API support is here. I think Istio, because it's been out there and I'm used to it, for me, it's kind of obvious. an ambient mesh transition from Istio to ambient mesh is super easy. The only thing is it doesn't have the full fresh coverage. If you have some policies in Istio and you want to move to ambient, consider that you will have no support. Now let's move on to observability. So observability, where the service meshes in general, like I said, they provide lots of data in top of your application, which is wonderful. So let's see how you can configure that. In Kuma, you have dedicated CRD, like before, mesh traces for traces, mesh metrics for metrics, and mesh access logs for the access logs. The control plane by default will produce metrics, and you can also configure it to emit traces, which is fantastic. And then Kuma provides a UI, so if you want to see if your configuration is done properly, you have this UI, which is kind of nice. And the great thing is they support OpenTelemetry. They are not saying that we support OpenTelemetry, but they do partially. They do OpenTelemetry for metric traces and logs. So then you can use it, and you can get you can trust that you will get data to your collector or to your backend. Linkerd. Well, Linkerd here, by default, they will expose some Prometheus metrics, but they have extensions called Linkerd Wiz. And when you enable it, then it's simpler to collect the data. They provide a UI on top of that. Then if you want to do traces, they have another extension called Linkerd Jaeger. But they don't do real OpenTelemetry. They don't do OpenTelemetry logs. They don't do OpenTelemetry metrics. And they don't do traces with W3C trace context. They use the Open Tracing trace context, B3. So if your application is fully fledged OpenTelemetry ready, then the traces will never be attached, which is kind of a bummer, to be honest. And then control plane, they expose metrics as well, but they don't expose more data. Cilium, well, Cilium, like I said, they don't do traces. They only do metrics and logs. And if you want to have a full-fledged details of what's going on the network level, then you need to add Humble. Humble provides so much details, very related to the networking side, more than their service mesh, I would say. But, and they don't generate traces. So you have to use their UI, or you have to expose metrics. So you have some observability, but less compared to the other products. Then I've grouped Istio and ambient mesh, because at the end, the logic of configuring this exact same thing. You have the telemetry objects to configure traces, metrics, and logs. You can also do it using their mesh config when you deploy it. You will also configure it automatically. The control plane expose a lot of metrics in a Prometheus format. And if you need a UI, they have an extension called Kiali, where you can see the traces, the dependency of your meshes, and it gives you the right details. And again, similar to Kuma, they provide real OpenTelemetry support. So which means if you enable OpenTelemetry traces, then you will get the traces in your app from each proxies. So at the end, on the observability side, I would say the two solutions that are a bit limited, I would say it's Linkerd and Cilium, because first they have a limited support of OpenTelemetry or no support, and the configuration aspects is more complicated compared to the other solutions. All right, so now let's cover the most important piece of this presentation, which is performance. So when I started this I did that benchmark, I said I would be really interested to get the actual weight and that those meshes is adding to your applications. So how much latency do I get when I add an application to the mesh? So here, I'm not going to measure every latency on every single microservices. What I'm doing is I'm sending an HTTP request to an application, and then I measure how much latency added when I have 11 or 12 proxy involved in the transactions. So you will see that I will provide those numbers. And then the other aspect is resources. We mentioned there are sidecar and sidecar-less. How much resources would I consume? That would be interesting to get those numbers. So to achieve this benchmark, then of course I had to, so there's a QR code, so if you want to rerun it, this benchmark in your environment, feel free to do so. So to measure the actual difference between having no mesh and a mesh, I did a test without any agent, nothing, no mesh involved. Then I did one test with Kuma with no policies defined. then Kuma with some policies, and I decided for this benchmark to use 2 policies, request timeout and rate limits. And then I did the same thing with Linkerd, without any policies and with the policies. And then I did same thing with Cilium. So I removed the line with the policy because it didn't work. So there's no support of rate limiting with Cilium, so I decided to drop this test out of these results. Istio, I did the same thing, so with the policy, without the policy, and of course ambient, I did the same thing. I removed the line because they don't support also rate limiting. And that's why I decided to remove the line. So in the architecture, you have, of course, it's going to be, I don't describe all the architecture of every single test, but there will be, of course, the mesh involved. And then I've added the OpenTemperature demo. So that will be the main application used with the benchmark. And I do a normal test with the load test as well. And then I'm adding 2 extra applications, the Hipster Shop, Easy Trade. So then there's traffic, and those proxies is actually used. And then, of course, to collect the data, the metrics, the traces, I use the collector, OpenTemperature collector. And I use the Dynatrace operator just to get the actual memory usage of those workloads. All right, let's start with the results. So I did a constant load, which is 30 minutes of test with 50 users on each of those applications. And then I've done a load test, which is 2 hours, where I have 50 users added every 30 minutes. So now I didn't add here, sorry, it's another benchmark. I added the load test so you see the results. So if you look at the numbers, so here the numbers are basically from the front end. The front end in the OpenTemperature demo, you have 10 microservices. So there's a lot of microservices with a lot of proxy involved in those response times. And if you look at the numbers, Cilium, if you use the BPF routing, they don't provide any latency, 0. Linkerd, I was surprised, honestly, for a proxy model service mesh, they're only adding 2.55 milliseconds, which is kind of low. And then you have, of course, ambient mesh with 3.69, and then Kuma is going to be faster with almost 6 milliseconds. And last we have Istio with 6.5 milliseconds. In terms of resources used, so I have on the bottom here the proxy. Of course, the solution using a sidecar will consume more because it's the sum of all the proxy involved in the tests. So the one that is consuming more is Kuma in terms of memory. And then, of course, Istio. And then down on the line, you have Linkerd, Cilium, and then on the lowest line is ambient mesh in terms of memory usage. And then if you look at the CPU utilization is Istio, the top layer, and then it's going to be Kuma, Linkerd, Cilium, and then ambient mesh. And then if you look at the control plane is Linkerd. Linkerd consumes most of the CPU and most of the memory at the end. Now, if I do a load test without any policies, then there's a slight difference in terms of latency introduced. So Cilium add a small amount of latency in the transaction, and then you get the same order. So Linkerd at the same level as ambient mesh, and then you got Kuma, and of course, last is going to be Istio. And then the similar behavior that we had before in terms of memory consumptions and CPU consumptions on the proxy level is the same. You can of course see that the sidecar model is consuming more CPU depending on the load. Of course, no surprise. And on the control plane level, we start to see that Kuma is having spikes of CPU. I have no explanation why, but you have those spikes of CPU during the tests. But otherwise, Linkerd is still the most expensive control plane. Now, if I add those policy, what will be the impact? Well, on the response times, the order is still the same. We still have Linkerd on the second position, still ambient mesh on the third position, and still Istio on the last position. And on the behavior of the proxy, it's the same. We still have the same type of behavior. I can see that Istio is consuming the same amount of CPU compared of Kuma, but for the rest, it's the same. And now if I do the load test with the policies, same results, I would say, nothing special. The order in terms of transaction, we still have Linkerd and ambient mesh at the same level. and Kuma always better than Istio. So if I have to conclude, I would say from a latency perspective, Cilium is the top, Linkerd and Ambient Mesh is the second, and then we have Kuma and last Istio. Proxy usage, I would say that the proxy CPU, I made a mistake here. The proxy CPU is consuming a bit more on the Kuma side and on Istio side, which so there's a small mistake on this line I figured out. So at the end, I would say, depending on your need, there's no clear winner. I would say the only conclusion I would say that if Ambient Mesh was supporting all the full-fledged features that we need for service meshes, then clearly in terms of response times delivered, in terms of features delivered, in terms of resource they use, it's the best. In terms of experience to start using a mesh, I think Kuma is nice because it's very easy to configure. You get everything without any minimal effort, so I think it makes sense. You know that you will have some extra milliseconds added to your transactions, but it's acceptable. Linkerd, I would say, even if it's quite efficient in terms of response times, it's just that the configuration perspective is painful. I didn't enjoy configuring Linkerd from my perspective. And from the observer perspective, they don't add so much detail. So again, it's a balance for you. If you use only HTTP and gRPC, then maybe Linkerd could make sense. But again, my conclusion says if Ambient Mesh was supporting everything, then go for Ambient Mesh. Small teaser to the channel. I did some content about Kuma, Istio, Ambient Mesh, Gateway API. It's out there. I may produce a content where I summarize those results. Again, if you don't like the content, let me know so I can improve. If you like the content, let me know as well, so then I can be proud. And yeah, if you have any questions, I will be very eager to get questions from you guys. No questions? As Cilium is doing is, so first, I didn't say that on the conclusion, but from, yeah. So why Cilium is not adding latency? Okay. So first of all, one thing before I answer the questions, I didn't say on the conclusion, I forget it. So for me, Cilium is not really a mesh. It's more a networking component. I think they have a mesh feature on their documentation, but they don't have the full-fledged coverage. I think they are really good on I think it's a complementary solution for your mesh to secure a bit more than really using just Cilium for a mesh perspective. But to answer your question, why they are so efficient, I think they are not using IP table anymore. They're using the eBPF to do the routing, and I think that's how they are getting better zero latency to applications.
When you increase your service depth calls, like when that service path is significantly larger, do the results change at all?
I only use as a reference the OpenTelemetry demo that has 6 or 7. So that was the actual results. It could be interesting to test it out with a application having 3 workload to see if it has less impact to the transaction. That is a good use case. But yeah, I never thought about this feature. Yep. So the Gateway API works with Cilium, yes, but so it supports with the Gateway API. I think the mesh support from Cilium is only with the component provided by the Gateway API. If you have a feature that is not supported by the Gateway API, then there's nothing behind the scenes. Compared to the other solution where if it's not supported, you still have a workaround with another components. That's the main difference, I would say. One thing also, if you enable observability in the meshes, it's awesome. You get a lot of details. But just keep in mind that it will add one span for incoming and outgoing communication of each individual services. So you may start to think about, I should maybe sample a bit more because I will basically double or triple the number of spans that I produce. So if you're very worried about the costs and the volumes of observability that you will get from your applications, then consider that the meshes will probably multiply by 2 the volume of spans that you have in your own environment. But yeah, that's a small note because I didn't mention it. Any other questions? Okay, yeah, did I kill you or? Yeah, I'm sorry. All right, so then if no questions, thank you.
Welcome, everyone. My name is Qasim, and today I'm going to talk about understanding and debugging DNS in Kubernetes clusters. Before we start, I'm from Lahore, Pakistan. I currently live in Hamburg, Germany. I work as a software engineer at Microsoft. I'm one of the maintainers for the project called Inspector Gadget, the project I'm going to talk about in this presentation. I also maintain Core DNS header plugin. Apart from that, I like to contribute to different open source projects. In terms of the agenda for today's talk, I'll first talk about understanding different DNS components and request flows. Then we'll deep dive into different request flows using Core DNS log plugin, Hubble, and Inspector Gadget. Then we'll try to test our understanding using different debugging scenarios. At the end of this presentation, hopefully, you'll have an understanding of how request flows work and how they help you debug DNS issues. So to debug DNS issues, the first thing we need to understand is that there are different components. So we have an application pod, we have a node local DNS, we have kube DNS service, we have core DNS pod, and upstream DNS server. In terms of the request flow, you have an application pod making the initial request. If you have a caching agent like node local DNS, then it can answer the request directly. Otherwise, the request is forwarded to core DNS pod. If the domain you're trying to resolve is an external domain, it'll forward the request to an upstream DNS server. Otherwise, if it's a Kubernetes service or a pod, it'll be answered directly. This kind of, the flow of the request already kind of showcases different challenges there are with the DNS debugging. There are too many hidden systems. We see there are like 4 to 5 components involved, and the request can fail at any one of them. It's not easy to trace DNS request flows across the cluster. You may ask which tool to use to deep dive into these request flows. We have TCP dump, which is great for deep diving into request flows, but it lacks cluster-wide aggregation and has no Kubernetes enrichment. So let's try to deep dive into these request flows. So the first tool I'm going to talk about is Core DNS log plugin. So it's like the core DNS plugin, so that means you don't need to install anything. It just needs a keyword log in your core file, and what it does basically is dump all the requests to standard out. In terms of the format for the plugin, you have the log keyword followed by some names, since it has some performance hit because you're trying to dump all the requests, so you can filter, for example, by specific domains, for example, example.com. And then you can also filter by certain classes. So for example, I only care about certain, if there are some errors, then I can also filter by that. Let's try to analyze the output from one of the requests being processed by Core DNS. So in the log line, we have the client IP, which is actually my pod. You have the query ID, which the client said when making the DNS request. You have the response code, and then you have the response duration. This logging format, you have an option to configure it. So in the bottom, I have different things that you can adopt based on your use case. So the next tool I'm going to talk about is Hubble. So it provides network service and security observability for Kubernetes. It is built on top of Cilium and eBPF, and you install it as a Kubernetes daemon set. In terms of the interfaces, it has matrices, it has service map UI, and then it has flow inspection using Hubble CLI and JQ. In this presentation, I'm going to focus on Hubble CLI with JQ. In order to use Hubble, we need to install Cilium with L7 proxy support. And to enable the DNS traffic visibility, you actually need to configure a couple of Cilium network policies. One for my pod, which is like the application pod, and then one for the core DNS. Let's try to understand these network policies. The first thing I want to do is that I want to put some labels on so that this policy really applies to the pod I'm trying to observe. And then one thing to keep in mind that these policies, they also block traffic. So you need to make sure that you need to open the traffic you're interested in. So for this demo, I opened everything, but you are free to choose a stricter policy. Finally, the important thing is that you have to have some rules so that the DNS traffic will actually go through the NY proxy, so it will have the L7 information. Similar to my pod, we also have a policy for core DNS pod, and it just has a different label, but other things are pretty similar. Once you have configured everything, then at this point, you can use the Hubble CLI, the observe command, and then in this case, since we're only interested in DNS, we can pass the protocol to be DNS and then follow the trace. Let's try to analyze the output. The first line is actually the DNS request going from my pod to core DNS pod. See, it has all the query information. We're trying to resolve example.com here. Again, the domain I'm trying to resolve is an external domain. So core DNS has to make an upstream DNS request to the upstream name server. And the second line actually contains the DNS request going from the core DNS pod to the upstream DNS server. The third line is actually the response we get back from the upstream DNS server back to the core DNS pod. And then eventually, this response gets back to our my pod. This already gives a really great overview of the flow of the request, how it starts from the application pod and how it ends up then upstream DNS server and back to the my pod. One other thing I really like about Hubble is that you can run these queries with --since flag. So in this case, I'm running it for the last 5 minutes. I'm able to get a JSON output, and then I can use JQ to actually check if some pod had an issue with DNS in the last 5 minutes. Finally, the last tool I'm going to talk about is Inspector Gadget. It is a set of tools that empower users to inspect a Kubernetes and Linux system. It is also a framework that allows you to build and share custom gadgets. It can be used in Kubernetes as Kubernetes daemon set or using kubectl debug node. The core idea of Inspector Gadget is actually the idea of a gadget. A gadget is actually a shareable and runnable unit for debugging and observability. Some of the examples could be to trace DNS events, to examine drop reasons for TCP connections, or to watch which processes are being executed in your cluster. The shareability aspect of gadgets comes from that they live in an OCI registry. So you build them and then push them to different OCI registries. It has different components that include eBPF programs or WASM modules. As a user of a gadget, you don't need to care about building these gadgets because we, Inspector Gadget, maintain an official list of gadgets. You can discover them at artifacthub.com. We have our own kind there, so you can filter by Inspector Gadget, and then also filter for official and CNCF gadgets. This is the list of gadgets we maintain, and you can see already we have some other use cases here in order to detect deadlocks or similar things around that. But for this presentation, I'm going to focus on DNS gadget. What it does is it actually traces the DNS request and response using eBPF. It does the post-processing of these events using WASM. And I also have the source code for the gadget here. You can, if you have a custom use case, you can modify the code, push to the registry, and give it a try. Let's try to see the trace using trace DNS gadget. I'm using kubectl gadget, which is a crew plugin. And then you can pass it a gadget instance manifest. We'll get into the details of it later on. But once you run a gadget, you're able to trace the DNS request for a specific pod. So in this case, we are again making a DNS request to example.com. The first line actually contains the query being made, and the second line is actually the response. In terms of the definition of the gadget, like gadget instance manifest, the most important thing is the image we're going to use. So in this case, I'm using trace DNS image. Then I can have some filters. So in this case, I'm only interested in demo namespace. Just to clarify, this filtering is being done in the kernel, so it is super optimized. And then I'm trying to do some user space filtering. So in this case, I'm only interested in example.com. Lastly, the DNS gadget supports a list of fields. So I'm specifying certain fields I'm interested in. Let's try to expand the scope of the gadget, and we want to trace the DNS request not only at the application pod, but also at the core DNS. So again, I run the gadget, I pass in the gadget instance manifest, and then I generate some traffic. In this case, we can see that we have, again, just like Hubble, two requests, one from actually my pod to the core DNS, and then from the core DNS to an upstream DNS server. You can see two IDs there. Also, we have some extra information like the latency here. So you are able also to actually see how much time it is taking to different DNS requests. Again, just to give an overview of the gadget instance manifest, we have the image. We can actually name these things. And in terms of the namespaces, I'm interested in demo and the kube system namespace. And again, I include the list of fields. In this case, I include the latency here as well. So to try to summarize it, these are the different tools I personally use to debug DNS in Kubernetes clusters. You are free to choose any tool depending on the use case. But for me personally, Core DNS Log plugin, it's great for ideal inspection. However, the scope is limited to Core DNS, and it requires configuration changes to use. Hubble provide compact overview of request flows and enrichment with retrospective analysis, but it requires Cilium CNI and specific policy in place for L7 flow visibility. Lastly, you have Inspector Gadget, which offers rich DNS traces with enrichment and filtering. It is extensible through custom gadget images. Currently, the TCP support is limited, but it should cover the use cases for node local DNS, which requires DNS over TCP. Now that we have an overview of kind of different DNS components and requests, I want to try out some real debugging scenarios to try to give a better idea. So the first scenario I want to talk about is to verify health of an upstream DNS server. In order to do that, I need to generate some traffic. So I have here a Minikube cluster. And what I'm doing is that I have a pod that is randomly generating some DNS traffic. So let's quickly try to see what this pod is doing. Okay, so it's a pretty simple pod that's just doing a lookup for example.com, sleeps for a bit, and then it actually does another lookup for unknown.example.com. Luckily, it doesn't exist, so we'll get an error. So now that we are generating this traffic, what I'll do is that I want to, again, use a gadget run. In this case, I have this gadget instance manifest that I named it as upstream DNS server. It has some filters in place, so it only cares about the responses, and only the response coming from a specific IP, which is actually my upstream DNS server IP, and then I have some certain fields in here. Let's try to run this gadget. So you can see that once I run the gadget, it's just streaming all the DNS responses. In this case, it's only putting out the responses from the upstream DNS server. And also we have here the R code, which actually helps us to establish the health of a specific domain. So for example, unknown.example.com gives a name error, and then the example.com actually gives us a success. Similarly, if you have like some issues with the upstream DNS server, you can get a server failure or something like this. So this is kind of one way to establish health of an upstream DNS server. The second scenario I want to talk about is identifying slow DNS requests in your cluster. In order to showcase that, I need to be able to simulate slow DNS requests. So what I do here is that I configure my core DNS. Just quickly. This is the core file I got. And I have here, I'm using the erratic plugin. It's also one of the core plugins. What it does is that every request that goes to slow request.org will be delayed by 1 second. So now that the core DNS, I've already configured it, what I'll do, again, I'll take a gadget instance manifest. So it's similar to the previous one. It's only looking for the responses, but it is also filtering. It only cares about the requests which are taking more than a second. Now, in this case, I don't want to just attach to the gadget run. I want to be able to observe it. So what I'll do is that I'll again run the gadget. And I'll run it in a headless mode. So that will actually you'll start to observe this gadget run. Let's quickly see if it's running. That's great, it's running. Now I need to create a dummy request. So you can see the NS lookup is taking a bit of a time. That means that the erratic plugin was doing the trick and it's slowing down the things. So now let's exit it and then let's try to attach to our gadget run to see if it actually so it actually indeed collected the any slow requests that are taking more than a second. The output is kind of a bit of crazy right now, but you are able to observe on long term, like you can run it for a day or something to kind of see if in your cluster you have any slow request. So the last scenario I want to cover is tracing DNS requests using Emperor containers. In this case, what I want to showcase is that you don't need to install anything in your cluster. So you don't need to have like inspector gadget deployed, as a daemon said. You can directly use kubectl debug node to trace things. And for this demo, I'm going to use K9S, which is a TUI to help you with Kubernetes. And I need to, wow. I maybe need to restart my terminal. Okay. So here we have like a okay, great. So we have like the K9S here, and what I've done actually is I'm using the trace DNS plugin, which is actually one of the plugins in K9S official repository. So you can go there, copy it to your K9 configuration. What it allows is that it allows you to trace DNS request by using a shortcut. So in this case, I can see different kind of pods here. So I'll just go to my DNS request pod. I can do Shift-D, and then I'll just start to trace DNS request. So this is kind of how you easily integrate tracing DNS requests into your workflow. So if you're already using K9S, you can just copy this plugin and then trace different DNS requests. Just to showcase, this is essentially using Infer container. So it just creates a container, runs IG in it, so you don't really need to kind of deploy a daemon set or anything. Again, you can head to the node for this thing and trace all the requests for the node as well. To conclude, the first step of debugging DNS is understanding the request flows. And for that, you have Core DNS Log plugin, Hubble, and Inspector Gadget. This was based on my personal debugging workflow, so feedback is highly appreciated. Finally, if you have any questions or suggestions, I put here the Slack for all these communities. You can reach them out, and they are really awesome communities. Finally, thank you so much for being here. If you like the talk, Inspector Gadget is also at the CNCF Project Pavilion in KubeCon on 2nd April. And then we're also doing a session on April 3rd on Microsoft Azure booth. And finally, we have a hands-on lab on Kubernetes Observability Simplified in KubeCon on April 3rd. That's it. I have the slides with all the policies and all the Gadget instance manifests on the QR code if you're interested. And thank you so much, and feel free to ask any questions. Yes. Is there a way to use any other logging stack to collect information to centralize the logging stack? Yeah. So. Yeah. So Core DNS. The question is more like right now I'm more doing the troubleshooting and just outputting everything to the terminal. But if there is a way to put that somewhere else, for example, into some matrix collection or something like this. So in general, Core DNS has a way to enable matrices. So you can do that for that. Hubble also gives you a way to do it. But in case of Inspector Gadget, we also support OTel backend. So you can generate OTel matrices for the failing DNS request and also create OTel logs for it. So we do support that, so for long-term observability. You? Yeah. Yes. So when you do normally you have a first step to install the daemon set. You can do that using Helm. But we also have this kubectl gadget deploy command that can install the daemon set. So it's not like you can do the things independently. But when you do a kubectl gadget run, it actually pulls the image from an OCI registry, unpack the eBPF program, and then runs it. And the last demo I showed, I'm actually using kubectl debug node in the backend. So that's more for kind of a single node or single pod use case. Yes, it works, but right now we only we don't do TCP reassembly. So if you have a DNS request spanning over multiple segments, it won't work, but I really hope that won't be the use case. But we do support parsing TCP, DNS over TCP. Any other questions? Okay, great. Thank you so much for being here, and I hope this was really helpful.
Hello, hello. Okay, time for the next talk. Who cares about Kubernetes and security? Raise your hands. This is the talk for you, Ben and Henrik.
Thank you. 1, 2, you hear me? Yeah, okay. We're on. All right, so you ready for the Kubernetes Guardians? Woohoo! Come on. No? Come on, yeah. So just a small introduction. So I did that talk, this version of a talk, slightly different version of a talk at KubeCon Salt Lake City. And Ben was in the audience, and he was asking security questions, and I'm not a security expert. And I was lost. And at the end, we met, we discussed, and say, why don't we run the same benchmark, but he's bringing his own expertise, so he will cover the security aspects in this benchmark, and I do cover the non-security aspects of this benchmark. So if you're up for that, and you want to figure out who is the best security agent, then this talk is for you. So let's introduce ourselves. So we are in a very nice venue. So my name is Lord Observable. I'm a CNCF ambassador.
And I'm just a caretaker here, so I don't know, Ben.
So because the talk is about Avengers and heroes, we had to put our shoes into a hero character. So this is my hero face. I look so nicer in a hero face. And you too, by the way.
Yeah, I love the abs.
So we same things. If you were there a few minutes ago, I did a benchmark on service meshes. So here it's the same, but with the runtime security agents. You need runtime security agents because at the end it's like a security cameras in your environments to detect suspicious events. So it's very important to have them. But the question is that in the CNCF landscape, there's so many solutions out there. So which one should we pick? So we're going to try to answer that question. So we did it similar to the previous talk. We did lots of benchmark. So disclaimer, nobody has been hurt. We were very gentle with the solutions. And we are not here to criticize the solutions. And the opposite, we want to just figure out the downsides, the good sides of each solutions. And here it's more about sharing you the feedback and how useful they would be. So do you want to, let's introduce the various characters of this movie. We have Falco from the SysDic, with the flying runtime agents that is saving the world since many years. Then we have the bees, Cilium, that is well known on the eBAPF landscape. We have KubeArmor, with the shields, it feels that he's going to protect us from dangerous events. And last, we have the wizard, KubeScape, which is Ben. So what are we going to talk about? A couple of things. We're going to see what we expect from those agents. What do you expect really from a security agent? And then we're going to compare similar to player stocks on different dimensions. First, we're going to compare it on the design experience, the components that are involved, the observability they provide, and of course, the security angles. And then, of course, at the end, we will share all the results, and we'll have a small conclusion at the end. Are you ready? So this time, I want to have you telling me the chapters. So step 1. Oh, come on, guys. Step 1.
The powers!
Gosh, I prefer that. All right, so what type of power do we need from superheroes? We need a couple of things. We need to be able to capture things. Then we need, of course, components to make that agents runs on the environment. They will provide observability, so we need to make sure that they are healthy and running properly. They need to be performant, because we don't want to have extra latency involved in our applications. And last, they need to do the job, so they need to be secure.
Yeah, at least.
So the components. What do we need? All right. So like every runtime security agent, you need something that detects events into your Kubernetes environments. And for this, of course, the best technology out there is eBPF. So all those solutions will, at the end, have in minimal a daemon set that will deploy eBPF probes. So if you look at the landscape, Falco has a daemon set, the eBPF, and it has the Falco server. We'll touch base why they have it, and it has a specific reason for that. And then there's an optional component called Falco Sidekick, and we'll see that we're going to use it when it comes to observability. Tetragon is similar daemon set. It has an operator, meaning that there are CRDs, and those CRDs will help us to configure the actual security policy that we need. Then we have KubeArmor, daemon set again, the operator, and then it introduced more workload. It has a controller, and it has a relay server. I'm not sure why they have this, but they have it. And then they have a lot of CRDs. Maybe they have an advantage in terms of performance, so let's see if it brings value. And then we have KubeScape. KubeScape is not doing only runtime. It's doing so much more. That's why those components, you have more things because you're not doing only security runtime. You have the operator, the daemon set, of course, the node agents that will do the runtime threat detections. They will do vulnerability scans, detect CVEs. It will also have security posture management with KubeScape. So it has so much features. At the end, it doesn't have the same feature coverage than the other solution that we're going to present. And of course, it has tons of CRDs, and we'll see it brings a lot of value behind the scenes. All right. Oh gosh, the energy is very low here. All right. So we need to capture. So we need to capture things because when you have an attacker, he will probably take control on your container, launch some processes, so spawn some processes, access to files, capture, change privileges. So things like this, you need to capture them. And you need to add, on top of the events capture, some metadata, so like Kubernetes, the path to the process, stuff like this. And when you capture and filter, you are maybe not experts that I am in security. I mean, I don't have the expertise. So having predefined roles is kind of a must. Because at the end, we don't have to go through this complicated journey of configuring everything. And then be able to react, block, stop things. That is also a feature that we expect. So let's cover Falco. Falco is not, it's a rule-based engine. By default, it's just a set of rules going through Falco. Falco looks at the rules. Yes, it matched the rules, then it's throwing events. So only throw events when they match the rules that you defined. And because it's well known, they deliver by default a kernel agent that will inject eBPF probes that will capture those processes and files and so on. It has also an SDK, so if you want to, for example, create an SDK that will listen for announcements on the White House at the moment and go through the Falco runtime agent, you can do that because you have an SDK to do this. So Falco capture everything that you need. It has predefined rules, which is kind of easy way of starting. And the difference from the other, it's not an operator, so it loads the rules at the startup of the Falco engine. And then if you need to change any rules, you have to stop the engine, add your extra rule, and then restart the engine. So not having an operator may be kind of a bummer. The structure of the event is well structured. The event structure depends really on the actual rule behind the scenes, so it's not really standardized. So processing those events could be kind of a bummer as well. Then you have Tetragon. Tetragon is basically following a lot on the eBPF side. So it's capture everything that goes on eBPF, process everything. By default, if you deploy it, it will capture every process execution and process exit. And then if you deploy a policy, then it will throw events extra on top of those process executions. The way you configure it is through trace points, kprob, so kprob kernel functions, trace points, kernel events, uprob, user functions, and LSM. So the way you do it is like you have a tracing policy. So this is where you need an expertise on the kernel. So which functions I want to capture, how I'm going to parse it, so which index of the functions on the C level I want to parse. So if you don't know that, then it's kind of difficult. They don't have any predefined rules, so that is also kind of complicated. And then they have the options to block or react. So at the end, Tetragon is very, very advanced. You can do tons of things, but you need a certain level of expertise to handle it. KubeArmor is not producing any events by default. So if you want to have, it will only produce events if you deploy a policy, and if the policy detects something related to that policy, then he will throw events. But by default, if you want to configure the policies, it's quite complicated. So that's why you have the options to turn on events. So you have an annotations from the operator where you can say, oh, I want to have details about the file, or the processes, or the network, or capabilities. And once it's enabled on a namespace, then it starts producing events. So, it doesn't come with predefined policies, so you will have to configure everything by yourself. It has a repository with predefined policies, but again, there's so many of them, you're a bit lost. Which one should I pick? Which one should I customize? This is the big questions. And then they have lots of CRDs, so the KubeArmor cluster config for the cluster, the KubeArmor policy for the namespace or the workload, and you can also define one specific policy just for the host. Maybe one CRD will be a bit simpler for the user instead of having all of them. One advantage I would say from a KubeCon perspective is that the event produced is super well structured. Every event will be the same way, so parsing it is super simple. And then defining a rule, then again, you need to have a certain level of expertise to see which process should I pay attention, how should I filter, and so on and so forth. Then you have KubeScape. KubeScape is completely different from the other vendors. They took a different angle, and I think when Ben reached out to me and explained it, I said, wow, that's so smart. So the way it works is that it will only produce events that is suspicious. And when you deploy it, you don't have to configure. Everything is already enabled. And the way it works, it has a learning phase. So the node agent that is deployed, that has the eBPF probes, will learn the application, which processes is used, which capabilities, which user, everything that you know, and then keep track on this. And everything there's a change, oh, something is different. There's a new process in the container now. It sounds suspicious. So he will basically raise an alert, say, hey, that doesn't sound normal. So that I think is a smart way because you don't have to go through this painful configuration. And then the other thing is what I like is that there has this runtime rule alert bindings where it's just toggle which rule I want to enable or disable. By default, you have every rules enabled, and it doesn't just capture the suspicious events on your runtime. It does also detect malware scanning, also any well-known security vulnerabilities that could happen in your cluster. So it does a lot of things behind the scenes. So in terms of user experience, you just deploy it, and you know that you will have alerts produced when they are dangerous. So for this, I would say from the summary of this, only KubeScape and Falco has the default policies, which is great. They, of course, capture everything that you need. The only one that's able to react on something is KubeArmor and Tetragon. And the only one that can customize, I would say, is Falco because they have an SDK. And Tetragon, you don't have SDKs, but the way the policy works is so advanced that you can do tons of things. It's impressive. And I think you have an SDK, no? Or?
Yeah. We do have an SDK, and you can go packages and so on. So you can customize rules, but you have to write code.
Yeah. All right, so that's covered the first piece. Let's move on to okay. So what do we expect from observability? So those solutions capture events. So by default, it extends the observability. You know problems, so you can collect those events through logs or open telemetry. You can parse those logs easily. They are going to be very noisy, depending on the solution, so you need to limit them somehow. You need to throttle, because if you have thousands of events, and it's going to be just putting a lot of noise everywhere, so you need to be able to throttle. And then the last piece is that you are deploying something, you want to rely on it, so you need to make sure that they are healthy. So I need to know that those operators are running smoothly and properly. So Falco has, they produce not the events on the agents, they produce it on the runtime server, so you have to parse it from there. The events is not structured, that's why you need to deploy Falco Sidekick that will pre-parse the rules. And then it also exposes a lot of metrics about the health of the agents, of the operator, and so on. Then you have Tetragon. Tetragon has, of course, the events is super rich. You can throttle, you can do whatever you want behind the scenes. And the operator exposes tons of metrics about the agents, about the operator, so you know that it's running smoothly or not. You can at least figure out, put alerts, and react. Then you have KubeArmor. Because KubeArmor, it doesn't produce logs at the agent level. It does it only on the relay server, so you have to collect it from the relay server. They have also an open telemetry receiver, which is nice, but it's not been maintained, so it's a bummer. So it would be great to maintain it, for sure. But then, in terms of how healthy the operator is, you don't know. There is nothing exposed. And I know that the project is running on adding that feature soon. KubeScape, on all the features covered, not only in runtime, they produce OpenTelemetry logs, metrics, traces. They have metrics on the node agents. They have tons of things. So you can know exactly everything without any major effort. They also have CRDs with all the scans that they're doing. So if you want to have the details, you can just do a describe on those objects, and you got the full-fledged details. So it's amazing. So in terms of observability, I would say that except KubeArmor, everyone has the right things. KubeArmor doesn't have metrics about your policy that you deployed. It doesn't provide any health metrics about the operator, so the only ones that do that is the other solutions. And now,
security. Thank you. Thank you that I didn't need to do this, like helping me. So, so again, I want to reiterate from a security perspective, like the major differences between these libraries. Like all, as Henrik said, like all of these are great open source projects, and we are providing feedbacks. And as a maintainer of Kubescape, like obviously I might not be objective here enough to like make claims. But having said that, since I also contributed to Falco in the past, so I really love all of these and projects. So I do want to point out the differences in the design concept. So one, again, Falco is the oldest from my perspective. It has a lot of mileage. It's deployed in a lot of places. A lot of rules being developed. Great. You know, KubeArmor. I really love about KubeArmor the option that you can really define prevention rules. It's super cool. Also, you can do that to some extent also with Tetragon. But one of the greatest things about Tetragon is that you are able to do rule evaluation within the eBPF itself, which also helps from a performance perspective, as opposed to Falco. Falco is like super doing all this processing in the user space, and it costs a lot of CPU and memory to like transfer this information to the user space and do the decisions, and Tetragon is doing back in the kernel. And Kubescape really took a different approach, like in trying to like adding the idea of like learning and profiling applications and using them in detection is a really different approach from the others. So what I'm going to show you today is a command injection attack, where during the, when we talked about the test methodology, we said, okay, we are going to test all of these projects through a specific attack. In this attack, we've spun up an application within a container Kubernetes cluster. It receives the traffic through an ingress, and the attacker is exploiting a vulnerability in this application, which enables the attacker to inject commands into the container and execute arbitrary commands within the container. It's a vulnerable application we've developed for this purpose. And to show you how it works, this is the application. You can just like ping IPs with this application. Super cool, very useful application. Now, what you can do is, like as any security engineer would do, as the first thing it tries to do is like a command injection, like putting a semicolon and an ls. And when I'm trying to ping, it turns out that actually the ping itself is, the ls is concatenated, and you can see that it was executed within the container. Again, this is a deliberately vulnerable application, but this is actually copied through a real vulnerable app. Now, we are going to do something more interesting, and instead of just doing an ls within the container, we are going to steal here the service account token within the container. Now, just like cutting it out and getting the response. Now, the reason for doing this test, because it emulates a real attack on a cloud-native application. And we expect these components to detect something on these. And we've tested all 4 projects under this attack. You can see that here we've been able to extract the service account token from within the container. So, and now I'm doing like a side note here, because most likely I'm going to be killed if someone loves Falco or KubeArmor. What I did is I've installed everything and used the default settings, default installation. Okay, now you can say that, well, you can fine-tune everything. And I have, it's hard to admit, but I have like 20 years of experience in the security field, and every project and every security detection agent will claim to you that had you did this configuration, I would have detected the attack. I myself claimed the same thing a few times. But it's really hard to compare these projects if I'm starting to fine-tune each of them just to detect this thing. So I've used the default configurations from each of them. So for Falco, we got 6 detections on a shell that was spawned by untrusted binary. It wasn't completely clear for me why untrusted binary, but in general, it indeed detected that there was a shell that was spawned, which is okay. Unexpected connection to Kubernetes API server. It was in this very specific case, it was true. To tell the truth, it's not really, it's not a very good rule in my perspective, but in this case it worked. And critical executing a binary not part of this image base was true because I indeed run application executable outside the container, and it's a great detection. But I also got 900 unrelated alerts. So if I'm looking at the signal to noise ratio, it is okay, detected the right things, but I get a lot of other detections. So regarding KubeArmor, again, default settings, I didn't really get, like, except of detecting all the exec events, which were either true or not true. They weren't really good. And I got 486 alerts, a little bit too much. Tetragon also detected exec events and exit events. Not real good. Again, sure, I could start to fine-tune Tetragon, but it was like, you know, it's a different project, like when I start to configure each of them. So within KubeScape, we really detected, you know, the exec binary, which was not part of the base image, the service account token access, which wasn't expected, and all of these. Note that the unexpected word in these alerts means that it was, the behavior was not part of the learned behavior of the application, which is, again, a way for us to filter out false positives and try to point into real positives in the environment. And from my perspective, there were no false positives, which is kind of cool. So the conclusion on the security side is that there is like an obvious difference between how Tetragon and KubeArmor is working and how Falco is KubeScape. Falco and KubeScape, from my perspective, are more security engineering oriented. In order to, as a security engineer or operator, in order for me to use Tetragon, I need to learn so many things about Linux and policies and stuff, and also about KubeArmor, that it's a lot of things to ingest for someone who is not in this field too much. Tetragon and KubeArmor are able to block system calls, while Falco and KubeScape cannot. And we have, in Falco and KubeScape, obviously, we had a lot of detection rules. From a noise to signal ratio, I don't really want to talk about KubeArmor and Tetragon, I guess, because I don't feel it's fair with them to talk about this when I didn't do any fine-tuning in the configuration. But KubeScape's really the concept of using application baseline profile is really helping to filter out irrelevant alerts in our case. And as a summary, from a security perspective, again, when installing these vanilla things, I think that Falco and KubeScape were the leaders from this perspective.
Okay, cool. So to measure the performance, same thing. I wanted to measure the latency that they introduced to the applications, and then the actual resource usage, so CPU usage, memory usage, and then because it happens on the kernel side, and if you just look at the user space, you don't know actually what happens. So that's why I also measure the ABBF footprint of those agents. To achieve that, I did the default settings from Falco and KubeScape, and then I deployed some policies for Tetragon and some policies for KubeArmor. I did a lot of tests, so no agents, like before, and then Falco with policies and without, they have the policies, so you don't have to do this. Tetragon without the default events, then Tetragon with the events and policies, and I did the same for the others. KubeScape I didn't have to do because it has the default policies enabled. Here is the QR code to the environment. I have different applications that make suspicious attacks, plus the OpenTerm demo that will be used to measure the actual latency. And then I have Inspector Gadget to measure the eBPF footprint. So let's look at the results. So I will only show the constant load because I think the load test doesn't bring any difference. So I have two types of tests, so constant will be only used. In terms of latency introduced, the most efficient one was Tetragon without any policies deployed. And then it's going to be Falco, KubeArmor, and KubeScape. But here KubeScape, remember, they don't only do runtime, they do more features in the security space. In terms of usage, memory usage, the KubeScape does, of course, consume more because it has full-fledged features enabled. And from the CPU, it's Falco consuming the most. On the eBPF side, it's going to be the CPU is going to be KubeScape on the higher end, and then KubeScape as well on the memory side. Now let's enable policies without events. So here you have, you can see that KubeArmor is the same response times with only doing runtime detections. Tetragon, same thing, and then Falco is still at 3 milliseconds. And then from the CPU usage, you can see that now we start to see KubeArmor consuming a bit more. On the eBPF side, it's basically changed as well. We start to have what is this color? You don't see that color. That's true. It's a good reference. So it's it's Falco that consumes a bit more, and the other one is still Tetragon. And then if I start to introduce events, because you can enable events in those products, then you can see that KubeArmor suddenly starts to consume way much more. And then if you look at the eBPF probe, the usage of the actual eBPF probe starts to do more things in the kernel. So that's why you have impact on our application. So in terms of conclusion, in the latency, Falco is a beast, 3 milliseconds. But then you only do runtime, where KubeScape does more features coverage. In terms of CPU consumptions and memory consumptions, I would say that Falco is consuming a bit more CPU. And on an eBPF side, KubeScape is consuming more, but again, it has more features involved when you enable it. So in terms of conclusion, I would say KubeScape, without any effort, gives you the full-fledged features, and it covers pretty much everything. I think Falco is doing a great job, but if you're looking for solutions doing blocking, it's only the engineering side of the game, which is KubeArmor and Falco, who is providing those features. But I would say if you don't want to go to the easy, complicated route of configuring everything yourself and learning all the kernel tricks, then I would recommend using Falco and KubeScape for sure. That's it. And again, it's small teaser to the channel where there is an episode on KubeScape that are released a few weeks ago, episode on Falco and each of those solutions, and I may probably update this benchmark soon as a video as well. If you have any questions, we will be very eager to answer your questions.
Would it be possible to use multiple of these products at the same time?
I think it does. I would say those products are injecting eBPF probes and they are consuming more things in the kernel. So you should be cautious about the number of probes that you put on your system. I think if one is doing a great job, then let's use one solution. What do you think?
Yeah, you can do it. Like, there is no technological limit to that. I would say it's not really, like, useful. Like, most likely you won't need, like, big organizations I've seen using eBPF at scale, they are like maybe one thing for security, maybe a second agent, an eBPF agent for networking / maybe one for, but no one will be ready to like do like 2 agents for security, or you maybe get away with like if you're labeling one thing for security, one thing for observability, but that's all.
So in your example with the vulnerable application, all you did was to...
Can you just speak up a little bit?
Yeah, so in the example with the vulnerable application, all you did was to output the token, the service account token, But then in the words we saw some DNS requests and binary executed, so what did we didn't see?
So, I would love to show the whole test to you. I was thinking of just like it was too complex to explain the whole thing, but as, beyond only like stealing the access token, I've also downloaded a kubectl into the pod, do the chmod plus X to make it executable. Then I started to do get pods through the command injection, and this is why you've seen like multiple things in the environment. If you want to try this, I can show you where it is in GitHub, and you can. It's a public attack.
And then the same thing here. The Goat app here is doing also same thing. It's trying to access a container, do some process spawns and everything.
Yeah, thank you for the interesting talk. It was a very nice comparison. I was wondering, yeah, there are other open source tools doing similar things, for example, NeuVector. Do you have any experience with NeuVector?
I just used Tracy from Aqua Security, but I don't know this product.
I know NeuVector to some extent, like a year and a half ago. I don't know what new things. So NeuVector is, I would say, is also able, if I remember correctly, NeuVector is also able to block due to policies, different things. NeuVector is also had a learning period, if I remember correctly. But I think it was introduced like a half year ago or something, maybe, if I'm not mistaken. I don't know it real well. So we didn't have a chance to look into NeuVector more deeply. It was something of an outlier for us because we tried to focus more on CNCF stuff.
Thank you, Ben. Thank you, Henrik. Anybody else?
Great, awesome. I love questions.
Are there any tools here or highlights that we should be aware of in trying to learn in one cluster, in a staging cluster, and then use those rules in a production environment?
I love this question. It wasn't premeditated, though. There is usually there is a problem here sometimes because it's not easy to do this kind of learning and configuration and then moving from one cluster to another, because there are sometimes differences of how the dev cluster operates and how the prod cluster operates. Now, again, I'm subject. Don't take my word. But from Kubescape, we designed Kubescape. And everything is a CRD in Kubescape. So when we learn a behavior baseline, when you configure a rule, everything is CRD. So you can just push it to your Git after you learned, and just roll it out together into production. And actually, it's working. So it's working more or less nicely. Obviously, there are caveats here. For example, endpoints, DNS endpoints, which are different from dev to prod, and there has to be a few things that have to be updated manually if you want to do these things over the top. But I would dare to say that 90% can be simply just rolled from dev to prod.
And it's time. So if you have any other questions, go ahead and bug Ben and Henrik.
Thank you very much.
Thank you. Yeah.
Okay. We have more Falco. Are you guys ready? Are you guys ready?
I think we're ready.
Okay.
So you're all ready to go? Okay, so thanks again for joining today's session. We're going to talk through API-driven security automation, specifically for AKS, and we're going to use two tools, Falco Talon and Retina. So I'm Nigel. I've recently joined a company called Cloudsmith, but before this, I worked with Joseph on the Falco project, and before that, we worked on Project Calico, the CNI for Kubernetes. So without introducing Joseph here, I'm just going to let you jump straight into what is Retina.
Right. Thanks, Nigel. Hi, everyone. I'm Joe. I'm a product manager on the Azure Container Networking team at Microsoft. And one of the nice and cool projects that we have been working for some time is Retina open source. So simply, Retina is an open source project developed by Microsoft team for container networking observability. It's eBPF based, and it's just to help users, Kubernetes users and container users to observe, debug, and analyze workload traffic. Yeah, I think it's important to highlight that Retina is powering one of the enterprise product in Azure, which is Azure Advanced Container Networking services, which highlights the reliability of the product and the trust it has earned to power and to observe networking in a product and large environments. So going in a very high level architecture, simply Retina collects metrics from the node where it's running on and send it over to another tool to be visualized using whether it's Prometheus, Grafana, even we integrate with Hubble, so we have Hubble UI. And so this data gets collected by running a program on the kernel level using custom APPF plugins. And this, so simply Retina designed to be very pluggable. Like if you have a use case that is not really there in the product today, you can develop your own plugin. Some of these plugins that we have today, things like, network drops, where you can visualize or get packet drops and the reason behind these drops, or another plugin for DNS, another plugin for network forward. And and then this data gets enriched with a control plane part, which relies on Hubble open source developed by Cilium. And then this forward to observability part. So that being said, I think these three pillars define and differentiate Retina. First of all, it's an APPF base. That means that it's run the kernel, high performance, minimum overhead. We also integrate with open source projects like, as I mentioned, Hubble and mainly Hubble. And the other thing is it's a platform agnostic. So Retina designed to run on any platform. We have a demo on Wednesday if you visit the Microsoft booth, where we will show some use cases for running on different clouds, on Amazon or Google Cloud, in addition to Microsoft. It runs on-prem, on Windows and Linux. That means that you will have a single pane of glass where all your clouds connected or your environments connected to the same observability tool. And lastly, it's a CNI agnostic as well. That means whatever the CNI you have, is it Cilium or Calico or Azure CNI, AWS CNI, it doesn't matter. It just works, and you don't need to change anything in your networking stack. And I think it's a good example of this is we have Hubble today that gives you the network flow logs, and with Retina you can run it anywhere. You don't need Cilium CNI to get Hubble. So once you have Retina enabled, the first thing you get is different layers of metrics. It's all powered by predefined Grafana dashboard, things like DNS dashboard, you will be there, connection drops, TCP connection status. And the other thing is because we use Hubble for the data enrichment, we also make the network flow logs, the Hubble flow logs available. And again, that works in Cilium or non-Cilium clusters. And the last thing is the packet capture that we make it available with on demand for nodes and for any bot. So yeah, that being said, that was kind of the fundamentals of open source project right now. I'll hand it over to Nigel to talk about Falco, and then we will see it in action with a demo.
Amazing. So look, I don't want to bore anyone with presentation, but I do think there's a necessary to introduce what we're talking about here. So most people are already aware from the previous session what Falco was, and it's a detection engine for Kubernetes. But what people don't always know is they think of it as just that thing that detects threats and sends metadata or something, an event, off to one of these endpoints. It could be to Slack or syslog, wherever you want to send it to. And that was addressed in the previous session. But then some people are aware that you can plug into things like Falco Sidekick, which is an automation engine, which is a way of, you could use it for automating with functions as a service, or you might want to use it for the graph ability to have a dashboard that's port forwarded. So that's how people use Falco Sidekick today, but it kind of has a gap, and that gap is we want to be able to respond to threats in an appropriate manner. So we decided we had to create a response engine for Falco, and that is where Falco Talon comes into it today. So as you can see here, this is just a general install of Falco, and I'm just saying create a namespace, make sure it's TTY set to true, so it's real-time detections are coming through, and I've enabled that component called Falco Sidekick. I've enabled it, and I've configured the config to say basically I just want to say like a post request. I just want to send whatever to that HTTP endpoint to Falco Talon on 2803 port number. So in that case, it's sending to Talon, but Talon isn't deployed. There's nothing here called Falco Talon. So we have to introduce what it is and what the problem was initially. So with Falco Sidekick, yes, we could, as an automation engine, send all this data to these general services like Lambda, or send it to Tecton or Knative or whatever it is. And that only went so far because, again, you'd still need to do the scripting on your side to know how you're defining these function service, infrastructure as code, automation scripts. Now, there's great benefits in building out your own solution, of like basically having control over defining the actions that you want to build. But when it's building your own solution, you've got to maintain it, and it needs to be standardized of which it is, and if you're building something custom yourself. So there's all these drawbacks of building your own response engine, and that's where you need a kind of a standardized approach. And we wanted to build an API-driven response engine that basically aligns directly with Falco and takes the benefits of Falco, which is taking all that associated metadata and basically using existing API actions so that it's somewhat standard. And that's where we get Falco Talon. So the idea, as we said, there's all these APIs in Kubernetes. Kubernetes is effectively just a giant API engine. So we said, why not just send that metadata to one of these APIs? So you could populate, for instance, an action to take on. So it could be network policy. You could talk to network policy and populate the pod and the associated context. We'll go through this in a second. But that, in short, is what Falco Talon is. It's a no-code, and what I mean by no-code is we're going to write it in YAML the same way we write the Falco rules, so that when an associated rule is triggered, something will happen and you can configure that. So as you see here, we're just going to continue adding response actions, but we've basically looked at all the existing APIs and said, whether it be, as you can see, most of them are Kubernetes. So we talk to the Kubernetes API, it's already there by default. And we can say, if you want to do sigterm action, then you talk to the terminate API. Or if you want to labelize something, when you say kubectl label pod with whatever label you want to add to it, yeah, it's going to do that. So as a response action, you could say, if I get a detection and I detect a pod from whatever namespace, give it a label. Or assign it a network policy and tell it what you want it to do. So this way it's, rather than manually creating network policy and hoping that it ever matches, you'll have it match basically in direct connection with the Falco rule. And then as you can see here on the right side, we're saying we can strip all the data from that output, so things like priority, tag, source, whatever the pod, the namespace where it generated, take that context and populated that into response action. we're constantly working on making this more reliable solution. So again, sequential actions, making sure it runs in a sequence and making sure there's deduplication so we don't have like things that are going to break our system. And then also generating trace IDs. So again, this can tie into your solutions where you want to look at all of the associated action from that. So, you know, on short, and I'm just going to show you this bottom action here, is this was a long version of installing Retina. So we install Retina, we install Falco, we install Falco Talon all via Helm. And when we install this version of Retina, we basically set this annotation set to true. And the reason for doing that is we wanted a response action initially based on annotations. You know, if a certain annotation was assigned to a workload, which could be done as a response action of Talon, then Retina will do a thing. That was basically the idea behind this. And this could all be API driven. So as you can see here, as I said, it's all YAML, so you can define in a rule. I've got on the bottom right corner, I've got a Falco rule out of default, so this looking for terminal shell into container activity. If someone was to shell into that container, a output comes from Falco. We showed earlier that we send it to that endpoint, so we send it to that webhook, and then we want to populate annotation with Retina SH observe. Basically, if it has that annotation, something's going to happen. You could do label as well, and we'll show that in the demo in a second. So in the bottom, we have a Falco rule that says terminal shell and container. In that scenario, anything that isn't in kube system or in the Falco network namespace, it will get this action of annotation of a pod, and that at the top, the annotation pod is basically talking to that API Kubernetes, to the annotation API, and basically populating it with that context. So this is why we talked about annotation. If we look at the Retina documentation, they have this simple example here where it's basically saying if you have an annotation enabled set to true, then we will do the, the advanced observability on pods in those given network namespace that you scoped. So that's just an example of a simple automation process. But the beauty here is rather than you going manually and adding it, which you would never really do, you can have it so that when a security incident happens, specifically on network security incident, which we can detect in our system calls with Falco, then we want to say, give it the annotation so we get that deep visibility scanning through Retina. And that's what this ecosystem starts looking like after a while. So you have Falco, the plugins, you have Falco Sidekick as the automation engine, and then Talon as a response engine where you can send out API actions to things like AWS, Azure, in this case, annotations, labels. You can integrate with just about all your endpoints with the right context. So let's just jump straight into the demo. I think that's probably the best place to go. So we've got a simple AKS cluster ready here. We should have, feel free to go ahead on it. So we should have 3-node cluster. What we're going to try and simulate is a very simple example that I showed there a second ago. We're going to create a pod, and this pod is going to be created into the default network namespace. Actually, it's this TCP client pod that's being created. That should have like no real labels associated. I mean, just a default label that's assigned to it, nothing really interesting. And when we trigger the terminal shell, when you say kubectl exec into a pod, when that happens and we shell into it, it should trigger Falco rule. And in real time, we're talking milliseconds, not even a single second. It will add the annotation, it will add the label. You could even assign a network policy. All this can be done instantly. In doing so, and we'll try to do two things. We'll show you, okay, we terminal shelled into that container now. If when you exit, just type in exit now, and then we check for kubectl get events, or if you want to, exactly describe the pod, or get pods and just show --show -labels. We can see, just labels with an S. Then you can see at the bottom it's got that suspicious equals true. That wasn't part of the deployment. That actually was assigned instantly when the detection happened with Falco. So again, you're talking to an existing API. There's APIs for labels. There's, you can see here, we even assigned the annotation for Retina SH observe. So doing that, while we don't think about it, Retina's been installed via Helm, Falco's been installed by Helm. That annotation alone has triggered Retina to do all this deep scanning. Basically, think about even the legacy world of Wireshark. You always had to run a capture to get your PCAP file. Well, in this scenario, you're getting your deep capture of all the surrounding context for whatever that time period is in response to a security detection, which is the only meaningful time you want to have that capture. As you can see here, we've done basically get the event output, the log output for Falco Talon. And as you can see here, it's doing, you can actually see the full trace output. So you can see annotate pod, label pod as suspicious. Those are the notifications that are coming out telling us it did something in Talon, and it did it in response to something else. So Falco triggered the event, and then the associated Talon action is shown in here. So for instance, if it was an incorrectly formatted response action, it didn't work, it would throw error or failed because, you know, you tried doing something that's not formatted correctly. But in this case, it came through okay. You can see the actioner, it talked to the Kubernetes exec action, and you can see it talk to, for instance, the Kubernetes label action or the Kubernetes annotation action. All three of those actions actually came in response to one single action. So we can have multiple response actions. So in a real world scenario, what you would probably do is say, you know, we've seen something happen, label it with whatever label so that network policy is enforced. So therefore, like, outbound connections don't happen if we see a suspicious connection to a C2 server. And then you might also want to have, you know, some form of security observability so we can see when this happened, you know, so we have the surrounding context. Is there anything else you want to add on to that demo? Or to
All right. So yeah, once so basically what Nigel did now, he adds 3 actions. He adds the label, he adds the annotation, and the other thing he created exec a command into the pod where he creates some IB tables, so to block the inbound traffic. So if we check that, you will see that a table rule has been added to drop all the inbound traffic. So if we go quickly, if we go quickly onto, just need to port forward our Grafana dashboard and Hubble flow. All right. So in this environment, this is a non-Cilium cluster, and we have Retina enabled, and we have the annotation in place. So once we can simply use Hubble CLI to observe the network flows in this environment, and we'll start to see the drops that you can see it now. And with the table, with the drop reason, IB table rule has been dropped. So that's the result of the policy that Nigel had just deployed. We can also go to the Grafana dashboard and see if we go to local host, that's fine. So yeah, some of the nice dashboards here, if we can go to the Hubble one, and this is our pod. You start to see here that there is forward traffic has been started to drop, and the drop traffic has started to increase. And that gives you an idea about, okay, what is if there's any drop traffic. So probably you start here with this dashboard to understand if there's any spikes, if there's any change in the behavior of your application in terms of the inbound or outbound or outgoing traffic, if there's any packet drops, and you take it from there. You can visualize, you can do a further analysis with Hubble CLI. Another thing that you can use Retina is one of the nice things is a DNS dashboard, and DNS has always been one of the main issues in Kubernetes world. With this dashboard, you get the most important thing from this dashboard is the DNS errors. So yeah, this cluster needs a lot of fine tuning. So I didn't do anything special in this cluster, but you can understand the different errors you have in the environment here, top DNS queries and top DNS responses from with pod name and deployment name. And one of the good things here is the DNS response table, where you can understand where the errors are coming from. So you can simply understand that there's some misconfiguration in my core DNS that is trying to add maybe the service.cluster.local to any external address I'm trying to resolve, and this is a kind of a known issue that needs some fine tuning in the cluster. The last example I have in this demo is packet capture. So in this environment, we have Retina CLI installed, so we can simply just with one command, let me clear this. So yeah, it's just one command, kubectl retina capture, and you define whether it's a pole selector, or even you can define the whole node. Destination could be host path, could be external storage, any persistent volume, and then you add the duration. There's a lot of other options. You have it in our documentation. But once you have this, you can simply just download it and use Wireshark to analyze this in your environment. Yeah, probably the job is not completed. But I think that was it. We are happy to get your questions if you have any.
Any questions? Going once? Going twice? Think about it. I have a question for you.
Okay.
In the beginning, you talked about Retina and that it hooks into eBPF. And I think you said it's pluggable, and there was Inspector Gadget there. Yeah. Can you expand a little bit on that?
Yeah. We use an Inspector Gadget underneath to collect some of the metrics, or to some of the plugins use an Inspector Gadget. So at the moment we have a couple of plugins, like the ones I mentioned, like packet drops or packet forward DNS. We have a specific plugins to integrate with Hubble and with Cilium. But yeah, an Inspector Gadget as an open source project we use underneath as well to collect some of these data. We use the binary of the Inspector Gadget, but because we use it, we have to just declare it. Yeah.
And does it mean it's the only eBPF source that you're gonna use?
No, no. You can. It's very customizable. You can build your own eBPF library and you just use it to hook to any part in the kernel and get these data.
Have you looked at using Tetragon, for example, also mentioned in the previous talk?
Yeah, it's it's one of the things that for runtime security, we don't have any plugins yet, but yeah, we are happy if anyone wants to write a plugin or contribute to the project. That would be great, and we can help as well.
Sounds good. And if anybody has questions, how to use it, how to set it up, how to get it up and running, where do they go?
Yeah, they can go just to retina.sh or GitHub Microsoft Retina, and they can reach out directly if you want on LinkedIn. We're available during KubeCon and Boost in 150. So yeah, that's how to reach out to us.
Sounds like you can do more demos there, right?
Sure.
Okay, awesome. Any questions? Any additional questions? If not, thank you, Nigel. Thank you, Joe.
Thank you.
And it's another break. Are we good to go? Okay, sounds like we're good to go. Are we ready for the next talk? I think we are. Running LLMs can be fun and expensive. And here we have Preet, who will talk about it.
Hello, am I audible? Okay, room is empty enough, so doesn't make any sense. Okay, so the talk's title is Wolf of Wall GPU, Profiling and Tracing Street. So what does come to your mind after reading this talk's title? Tom Cruise? No. Annabelle? No. Mr. DiCaprio, right? So it was just to add a pinch of fun and humor, but you didn't laugh, so my joke went wasted. So what's the most valuable thing that Mr. DiCaprio talked about in the movie? It was cash, right? It was money. It was green cash. So the green cash in today's scenario is GPU. Okay, the most expensive thing that one can really afford is GPU. We all know about NVIDIA's stock price. Now it's plunged, but everything the GPU and AI race. So we all know about that. And one thing about GPU is that, okay, I misclicked. Okay, that every minute counts. That is the agenda of this talk, that how to make your GPUs count every minute. Okay, every minute of your inference pipeline, every minute of your training pipeline, every moment your product is up, you need to make that minute count. Now, let's go. Again, you had to laugh. So, Rejekts describe the speaker. I'm the CTO of KubeCloud and Infra1. I don't like to actually promote my company in events, but this is how our company looks like. We have a couple of tools in the cloud native space. We have Sketchpad, so you can actually design your architecture. Okay, this is the free version, so you can actually design your architecture, and my products do have working live demos, and you can easily get the Terraform code in the, okay, it's not working, just kidding, my internet is not working. So you can actually just, we have a lot of tools. So Sketchpad, Lemon is a cost optimization tool. Headlight is more of, again, things are not loading because of my bad internet connectivity. Headlight is a tool for actually modernizing your documentations. We have Nuts and Bolts, which is an automation center. You can, in no code, you can actually automate any kind of stuff. We are still building, so if you really want to join, do join us. And in Infra1, which is a sub company, we are actually building AI suite for observability. So 4 agents, one for monitoring, one for logging, one for profiling, and one for tracing. The talks, this particular talk is a case study about the product that we are building. It is not a theoretical talk or not actually a talk that I'm reading from a notebook or some textbook. It is real life scenario. Coming back to my slides, my name is Prerit. I am the CTO and co-founder of KubeCloud.tech and Infra1.io. I love adventure in all sense. Do you know what the stone is? Anybody knows? Yeah, Stonehenge. So I went there yesterday. So it is lovely. You should actually go there. And so do you know the reason of Stonehenge? No? So prior to going to Stonehenge, I thought that, okay, humans wanted us just to tell the future us that we were there in the past, right? So they were just actually telling their significance. But these stones in the Stonehenge actually say, tell you about the time, the seasons. So you can actually see sun going. There are 4 seasons, right? So you can actually go and see the sun going from one stone to the another. I love adventure in all sense, so I just went for a skydive, and it was lovely. I run a YouTube channel, Tech with Prerit. We have the most viewed Kubernetes series in Hindi, which is a regional language of India in 2024. I like to write a lot of glue code because that's what real engineering is. On an average, I get 13 million plus eyeballs on LinkedIn. So yeah, eyeball is pretty scary. So on LinkedIn, so if you need any help about content, about lifting your LinkedIn, free of cost, again, friendly advice I can give you. So coming to the agenda is pretty simple: when and what, why, how, and what thread. Again, agendas are pretty simple. First we talk about the problem, then we talk about the solution. So prior to starting this talk, I just want to say that day one is not meant for optimization. This is a story. This is our real story. So we actually optimized our infrastructure on day one. The reasons are the following slides, but you shouldn't be optimizing on day one. Just after hearing this talk, you just go to a CTO and tell that, okay, that guy did some profiling on their GPU inference pipeline. I just want to do that. Some backstory. This is the reason. Actually, we were hit by a crypto mining attack on January 2024, which costed us over $1 million. The video is on HashiCorp's YouTube channel. Do you want to know about this attack, or should I continue? Yes? Okay. So very short talk because I'm already running late. In January 2024, we had a B2B deal. What we do actually, prior to dealing with cloud native stuff, we used to have multi-tenant platforms. So we used to offer sandbox environments to the end user, and what we were doing was we had a lot of Google Cloud projects. We used to flush them, we used to renew them, and then we used to give them to the end user. So users could actually come in, use our email ID, like your name is q@kubecloud.tech or kubecloud.org, and you could just spin up your sandboxes. So one of our client came in, they booted up the maxed out virtual machine. So they were very clever enough. They actually figured out, one thing to note here is we used to do cleanups in Google Cloud with shell scripts, okay? So every moment when the sandbox ended, we used to boot up a particular shell script based on one particular set of regions, because there are a lot of regions in Google Cloud. Our infrastructure was just meant for US Central 1. So the crypto miners actually came in, they figured out that, okay, these guys just have the shell scripts in the US Central 1. So they had 10 days of pre-workout before actually doing the stuff. So after that, they came on one weekend, and they actually, so it was mid kind of 20th, because our billing alerts are approximately 80% on the 20th kind of thing. We had a couple of alerts, but we thought that, okay, it might be because we just cracked a couple of deals, so it might happen that they are overusing the product. So we actually took it very leniently, the next Monday, then when we woke up with a $1 million bill and a notice from Google Cloud that they're suspending our Google Cloud account. So technically we were doomed. We had nothing. We had nowhere to go. But again, then we actually did some root cause and RCA, and then we figured out how they actually did. So they booted up a lot of big machines. They took the RDP access, and then they started the crypto mining thing. The next thing, there are 23,000 plus metrics in Google Cloud, and in any cloud, in AWS, in Azure, we have over 20,000 or 25,000 metrics according to each zone, each region, and each service. So technically it is not possible because we were a very highly multi-tenant kind of platform. Technically, it was not possible to tweak the organizational policy because it would have affected all the sub-projects. We wanted to be a very customizable kind of metric platform system, so we used Terraform. Terraform has actually a beta feature which you can actually use to customize your particular metrics. So it took about 2 months, and we actually did that particular stuff. For that, we were invited to HashiCorp Sydney to present this use case. I highly recommend you to watch this particular video. Now, this was our chat. Again, these are AI generated. These are not reals because we used a lot of cuss words. So I didn't want to blur or that kind of thing. So after this attack, we were actually going to launch this AI suite thing, okay? So we were trying, because AI race in 2024 was good, people were actually building vertical agents, people were building a lot of things, wrappers, a lot of things on top of foundational models. So we also thought of actually building some stuff, and finally we got some GPUs, because in 2024 things were really hot in the GPU space, and because I have a good LinkedIn, so we got some GPUs from Google Cloud and on-premise, some of the providers. So the next thing, we were secured with GPUs. I told you what we were building. The next thing was we wanted to be damn sure, because prior to building the agents, we already had a $1 million bill in our accounts, which Google Cloud actually waived off. They were very, very generous in that, because anyway, we are a startup, and no startup can afford $1 million in cloud. Will not even, I think good enterprises can afford that. Instead of paying $1 million to a cloud bill, you should actually go and buy a good data center. So, so the next point was we wanted to be very sure that we are observing the agents, and the similar thing don't happen to the AI agents that we are building. So we had to be very, very secure with the observability. And when we went to the CNCF landscape, we were really, really shocked, because observability, Ollie, is the most trending topic in CNCF. So even there are, I think, 100 more tools which are not even registered by Google Cloud, by CNCF, and still a lot of tools. But none of these tools can actually do anything with GPUs. So there is no tool in this CNCF ecosystem which can actually do the GPU thing, which can observe the thing. Ideally, GPUs and CPUs are same, but in terms of profiling, they are much different, because underlying technology is very, very different. We'll be coming to that part as well. So we had to also, we had a prior good experiences with many enterprises where, like, I can't name them, but they build for every single thing, egress, ingress, every kind of thing. So we were also not in the financial capacity to go for a enterprise deal, okay? So this is our architecture, okay? So we use Pixie, which is an eBPF based monitoring tool to actually observe our services, to monitor our services. We have OpenTelemetry for tracing, Loki for logs, and Pyroscope for profiling. So we wanted to be very lean in our cloud tooling, or CNCF tooling, or open source tooling. Our infrastructure is primarily based on GCP and some of the on-prem servers that we have. And yeah, this was it. So this is a pretty, so do you know what is inference means? Do you know? So it is a process when you tell the LLM to give you something, and the process when the LLM gives you the output, that process is called that. And this is a simple pipeline where we used Redis queue to store the inputs and give the outputs. Now the problem here was on day one, not on day one, but month one, there were actually a lot of failures. And also I'm not a GPU expert, and nobody here is, because first of all, GPU came in the boom when we were not ready, right? There are very limited architectural deep dives. We tried a lot of documentation but couldn't find any. And also we had a problem of inefficient batch processing. We already had 50K in cloud bill, which was actually kind of what we were expecting in the middle of building. So we had one pivot. So in the previous ideation phase, we were actually thinking of building a foundational model just for this troubleshooting and observability stack. Then we saw Claudes and a lot of other, even Mistral AI. Now Mistral AI is launched, but at that time also we had something. So they were very good in actually doing the troubleshooting after just fine-tuning them. And also we
had some kind of, so it was costing us $1.2 per million tokens. I can't recall, but it was quite huge. And we also didn't have any clue in the latency breakdown. We were just running in the wild. Okay, so we had no metrics. We were just relying on the GPU, on the GCP's entire observability stack. It has, I think, Hotel integrated into it. So the need here was to have CPU level observations. We used Go in our backend, so we wanted thread as well. We wanted Go routines as well. We also wanted, because in the problem, we were not having actual clear error messages. Though in logs, you can actually go and see what things are not working, but logs are not meant for that, not actually meant for that. Okay, so logs is just your history, right? So it doesn't have that technical deep dive of what things went south. So we wanted to have things regarding memory, things regarding logs, things regarding exceptions, and errors. So just to be on the same page, this is what profiling looked like. Okay, so for example, your entire day is 8 hours of work, and we segregate into 45 minutes of email, project work, meetings, coffee, and strategy work. So after actually observing, and this is the thing that activity or monitoring tracking softwares actually do. So they are going to actually create a timeline for all your activities and just stitch it into one. So here optimization opportunities is that reduce meeting time by 15 minutes. And you shouldn't be spending a lot of time on meetings, and add 30 minutes of deep work block, because right now we can't see any employee efficiency. Are we good with profiling? Yeah? Yeah. So yeah, it is another joke, but we are not going forward with it. So this is how actually profiling works. So let me play it again. Okay. So at the top, we have the base function, and then we have the hierarchy. The longer the horizontally, the longer the line is, the more longer time it will take. The vertically, more nodes are there. That means the function has more function calls or more hierarchy, and it shouldn't be there. In some cases, it should be there. In some cases, it shouldn't be there. So totally dependent. Again, I think most of us are pretty much known to profiling. So 3 things that offers is: first, cost cutting; second is latency reduction; third is faster debugging and incident resolution. Because in the end, you have a very deep dive view of what your products are, what your actual software components are consuming, which software component is consuming which, how many number of CPU cycles and other stuff. Just an activity, I think we have some time. So can you tell me in example 1, what things can you actually optimize? Is it visible? I think it is. Let me, I can't increase the, I think. So anyway, in example 2, what do you think you can optimize? Anyone? Okay, this is a homework. So you can optimize anything. So at the so the most recent is compute product is taking 18% of the time, and it shouldn't be taking, because the more hierarchical you go in the flame graphs, it is bad. It is bad for end user latency. And also these are some of the charts that you can look after the session. Now, the next closest thing that we actually were dealing with was Pyroscope. So at that time, Pyroscope was not part of Grafana family, but it got acquired one year ago. I acquired, or they joined voluntarily, I don't know, but they are Grafana Cloud now. So when you go to Pyroscope's cloud, it will take you to Grafana Cloud. So it had everything that we wanted. So it offered CPU time, memory, input-output operations, and that's what we needed. It offered continuous profiling. So there are 2 kinds of profiling: continuous continuous and non-continuous. Continuous is good. I still remember back in 2021, we were heavily invested in non-continuous profiling, so we used to instrument manually, and suddenly in 2022 or 1, Google Cloud actually retarded that service. So the service name is Cloud Profiler and Cloud Tracer. So at that time, we had to manually implement the things. Coming back to the topic, so the good thing is, it is due to continuous profiling, it is not going to add that much latency to your or CPU overhead to your particular application. So at about like in the frequency, do you know anything about clock cycles? Okay, no, it is not relevant. Joke. Okay, I tend to I tend to crack a lot of lame jokes in my presentation. So in every 15 seconds, it will be sending periodically the data to a server, and it is very, very good at compression. You can add S3, GCP bucket, and other things to store your profiling data. So very, very good tool for profiling. I don't think any tool is better than this particular tool in profiling. This is how this particular tools. Okay, there is a suspense in the end. Okay, this is how the profiling dashboard looks like. You can also have tracing into this platform. So because eventually everything is a part of Grafana family, so you can actually integrate a lot of stuff. But after instrumentation, we realized this is not enough because CPUs and GPUs are different. CPUs, you have, if you don't know how profiling works, so there is some symbol table, there are programs, there are particular set of files, like due to Linux, a lot of things are standardized. So we have a lot of files in particular format. We have a symbol table, we have a process table, but in GPUs we don't have. Okay, not actually Linux, but in CPUs, they tend to have a process table, a symbol table, due to which that's how your profiler is going to work. But at that time we realized this is not enough. Then another tool came in, and the only tool as of now which can actually profile your GPUs is Intel Tribe AI Cloud kind of thing. Intel Tribe, I guess, AI is their add-on word. So this is the only tool which can actually instrument, which can actually differentiate between your CPU calls and GPU calls. So everything that you see in the green, they are CPU calls. The gray one, so this one, this blank line is when the system switched from CPU to GPU. So the above one are GPUs, so the blue one, and then the thing came back to CPU. Now the thing is, this is the core logic or core learning for us from that particular instrumentation is that once that execution begins in GPU, the memory might not be in even the main memory. Okay, it cannot be even in the accelerator memory. Okay, and that's the reason it can't be available to the OS profilers, because OS so the thing is, in GPUs, in CPUs we have process table and other stuff, and we have taken them for very granted. In GPUs we don't have them, so there is also no proc representation of this program either in GPUs. So there, in short, there is no direct way to even tell you what is running and what isn't, and only this particular tool is very good at it. I think the only one. The tracing part is exactly the same as of CPUs and GPUs, so there is no single difference. We are using OpenTelemetry for tracing, and there is no single difference between tracing, because eventually tracing is about identifying the bottlenecks, which service is causing which, how much and which delay, and what we can optimize it further. Before we had a average GPU utilization of 34%. We have P50 of 850 ms, P99 of 2300 ms, error peak rate of 2.7%, which is fine enough. cost per 1 million token is $1.25. After actually doing the profiling thing and doing some magic in our batch processing and in our inference pipeline, the average GPU utilization went straight up to 78%. P50 went to 450, P99 to 905. Error peak rate is 0.5%, and cost per 1 million token went straight down to $0.75. But again, cost was not, even 1.25 was manageable. But yes, without profiling and tracing, we couldn't have actually reduced these kind of numbers. So we also observed 0.8% of additional latency due to profiling. But 0.8% is fine enough because we were actually blind before the implementation, and after that we were totally fine with it. And also it takes quite some memory, so 2 GB per day for full trace retention. Again, in any way, if you're building any product, it is going to take some storage, and storage is pretty cheap in cloud, in any hardware world. So you can easily get an NVMe 256 gig for I think $100. That's it. And after that, we were less noobs. We had a lot of information about our particular tools. So we are actually running a cohort. So let me go back to this website. So we are actually running the cohort, and we are currently doing some beta tests on our particular tooling. So our front-end engineer is very much creative. So you can actually come in the cohort and you can actually test these tools, and we're going to open source it. So yeah, you can sign up for them. And coming back to the slides, because as of now they're pretty much good. They can troubleshoot it. They can, again, monitoring and logging, I think monitoring and tracing and profiling, they should be just one click of it should happen like a magic. Nobody should invest a lot of time, money and resources in just instrumenting the things. They should happen in just click of a button. You should, anyone could just click a button, software could tell you that this is the bottleneck, this is the thing that you need to improve. So was it worth it? Absolutely yes, because before this, our CPU time was quite high, due to which our resource efficiency was very less. It was costing us more, and being a startup, money matters a lot, more than ideas. So yes, it was worth it to actually instrument the things. And yeah, this was it. I couldn't do a demo because the thing is GPUs are costly, and right now we don't have any, like everything is consumed, so we couldn't. And also there is one implication that you need to do a lot of stuff with VRAMs, with a lot of tweaking with batch requesting, batch, even the queue size, everything you have to build on your own. If you are building something very good on top of foundational models, and actually you want to be profitable in a longer run. So yeah, that was it, and I will be there at KubeCon tomorrow. I have a talk at KubeCon Platform Engineering Day and Open Features Summit, and looking forward. If you have any idea about, if you really want to build such kind of systems and you're really into it, and if you know how to build these, I would love to have a conversation with you. If you have any doubts, I would love to talk.
We have a little bit of time for one question. Anybody? Okay.
Thank you for the talk. Can you return to the slide with the Intel tool profile flame graph?
This one?
The Intel for GPU. You shared
this
the
one.
only tool that does GPU.
Yeah, this one.
Yeah, I noticed that there is some mention of i915 something in the stack tray. Yeah, the gem do exact buffer thing, and that leads me to a question: is this tool capable of profiling different GPUs or just Intel GPUs?
Just Intel GPUs.
Nice. Thank you.
So yeah, one catch. Thank you. This tool can only, because the name is Intel Tribe, so it can only do the Intel GPU kind of thing. You can't actually implement this tool in the NVIDIA stack, and that is perfectly fine with us. So previously we had a couple of H100s and T4s, and then we opted for the Intel GPUs, and that is perfectly fine. They're even cheaper. Yeah, that's it. Thank you.
Thank you. Are they good? Okay, I guess we can get started. So the last talk, this talk, is about Envoy, WebAssembly, and security. All cool things. So welcome, Dan and Mikhail.
All right. Thank you. Okay, so welcome everyone to our talk. WASM, Envoy, and Hyperlight walk into a pod. No vulnerabilities allowed. Today we'll talk about a couple of things, starting off with cloud security. That's just sort of setting the tone and getting us all on the same page about a couple of concepts that we'll talk about. Then we'll do a series of 101s covering a couple of technologies like Hyperlight, WebAssembly, WASM, and Hyperlight WASM. Then we'll go over a use case of customer-provided Envoy plugins, discuss a couple of things there, and then finish off with our summary and plans. But before we begin, I just wanted to introduce ourselves. I am Danilo, or Dan. I'm a software engineer at Microsoft. I'm a core maintainer of the Hyperlight project that I just talked about. And I'm the author of Manning's server-side WASM book, also a champion of 7 WASM WASI proposals, and a big Star Trek and Smash Bros. Fan.
My name is Mihail. You can call me Mike if it's easier. I'm also a software engineer in Microsoft, mostly working on service mesh, things like Istio and Envoy. SRE in previous life, and I guess a fun fact, I spent my free time educating my little puppy to not bite my hands off. So that's it.
Cool. All right, so now let's get into it. Or rather, before we get into sort of the meat and potatoes of this talk, this is sort of that cloud security section on our agenda, covering some background items. And in particular, I want to talk about isolation. So when you think of running apps, there's 3 sort of methods of high-level isolation that you can think of. The very first one is, well, the absence of it. You can think here, you just have a couple of apps running on your own on one OS. These can be sort of process isolated, so sure, they have some sort of isolation, but nothing specifically isolating them that's dedicated to that. Next up, we have weak isolation. So right here, the apps could be leveraging kernel features to have that isolation that could be, say, C groups, namespaces, sort of how containers run. And then we have strong isolation. These apps now are leveraging something like a hypervisor or some other similar technology to be fully isolated from one another and potentially even have their own OS. But let's dive a little bit deeper into that weak versus strong isolation with a containers versus hypervisors face-off. With containers, between 2022 and 2024, we had 7 reported container breakout vulnerabilities. These are vulnerabilities stemming from the use of those kernel features that give them the weak isolation. And what this implies is that then containers are not really suitable for multi-tenant architecture, so where customers are sharing infrastructure. Hypervisors, on the other hand, like KVM or MSHV, provide a different API to create isolated memory, configure a virtual machine state, create a vCPU, and run a vCPU, and they do that through harder virtualization extensions like Intel VTX or AMDV. So they're not using those same kernel features that create those vulnerabilities. And that's where Hyperlight comes in. So Hyperlight is a library that allows you to leverage underlying hypervisor technologies like KVM, MSHV, or WHP, the Windows hypervisors, to create micro virtual machines to execute some untrusted or potentially malicious code safely. And what's more, Hyperlight was recently donated to the Cloud Native Foundation, and we're just accepted as a sandboxing project. Okay, let's take a look at a quick Hyperlight Hello World application. What does it entail to use Hyperlight? First off, the very first thing you have to do is create a uninitialized sandbox. What you do here is you have some sort of potentially untrusted code that you load onto the sandbox. This can be a native ELF binary, it can be JavaScript, it can be WebAssembly. We'll show examples in this presentation running WebAssembly, but we also have blog posts, shout outs Ludwig, for running JavaScript that you can Google and find. Probably just like a Hyperlight JavaScript will find you that blog post. Once you have that guest loaded, what you can do next is register host functions. This is important because by default, Hyperlight guests don't have an OS. So the APIs they can access are available via host functions because they don't have access to syscalls and an OS that an OS would usually provide. So once you have the guest loaded and you have host functions registered, you can evolve your uninitialized sandbox into a multi-use sandbox. This is essentially just a initialized sandbox that you can then use to call guest functions. In this example, we're calling a guest function called print output. This function here, all it does is it goes into the guest, and then it exits the guest to call a host function that prints output on the host's standard output, and then will return to the guest. But say that you're running some sort of application that you want to allow user plugins or some sort of architecture like that. You could have your plugin API be that the users define a run function, and then this call guest function by name would call that run function to execute that code within that hypervisor partition safely. Okay, now let's talk about a different isolation technique called WebAssembly. We talked about a bit about it previously as a binary format, as one of the things that we can run in Hyperlight. But it's a little bit different than just your ELF binaries, because for once it's architecture independent. So as you can see, this figure to my side, WebAssembly, it's not specific to say x86 or ARM, and instead it abstracts over those architectures, sort of this harder abstraction layer, or HAL. And it's also safe by design. It's designed to be executed within this sandbox environment where you opt into specific capabilities. So in this example, we have capability 1 and 2. Those are explicitly granted to an application, and then the application can make use of those, but say some sort of capability 3 cannot be used. Those will correlate to syscalls. Now, comparing the two, they have a lot of similarities, right? WASM and Hyperlight. On my right, we have the native OS WASM runtime sandbox as the isolation method. On my left, you have the Hyperlight with the native OS, Hyperlight as the sandboxing method. And then you have that same API to opt into capabilities. But the difference I want to highlight here really is just that difference in isolation method. On WASM, sort of the new kid on the block, right? You have the WASM technology, while in Hyperlight we're leveraging, hypervisor technologies that have been used for a while and are oftentimes a requirement for running third-party code in public clouds. But what if we combine the two? That's where Hyperlight WASM comes in. Hyperlight WASM was just announced a couple of days back on March 26th with this blog post if you want to read more about it. But what it promises to do is bring this defense in depth, where we have not just the WASM sandbox, not just the hypervisor sandbox, but we have the hypervisor sandbox with the WASM sandboxing running then your WASM component. Now for a demo. Okay, so in here, hopefully this is big enough. What I'm doing, hopefully I can move my mouse, there we go. We'll go into more detail about this API a little bit later with Mihail's section, but in this example, we're creating that uninitialized sandbox with some specific configuration, sort of like heap size and so forth. We're registering host functions, just like we saw in that previous Hello World example, except in here, instead of registering a specific host function, we're leveraging something that WebAssembly has, which is WIT, WebAssembly interface types, to create those bindings specifically. So in here, you see the WIT. It has the definitions for start bind, finish bind, subscribe, and these would be host functions that a guest would be able to call that can be registered like so. For Hyperlight WASM, you have an added step other than just initializing your sandbox, which is loading the runtime. That is what's capable of running a WASM component, and then you load a module. You notice that this says echo.bin instead of echo.wasm, and that's just because we ahead of time compiled that WebAssembly component. And then you're ready to run. And now you may ask, what are we running? And this is it. So that's that echo.wasm application. This is the application that was compiled to WASM. What we do is you bind to a socket. We start receiving packets on a loop, sort of just hanging forever. And then when we receive those packets, we just echo, and hence the name of the application, then back to the sender. So now, demo gods be with me. If I cargo run, okay, perfectly this hangs. And now I can go in here, run NC, and now whatever I send it, send a hello, should send it back out. Cool, so I get a hello. I can say world, and there we go. We get a hello world back. So I guess to summarize here, what we're doing is we created an uninitialized sandbox on the host side, we rendered on the host, and then in C, it's calling all the way into the guest, so doing a VM, going into the VM, executing the guest code. The guest code can call host functions, do VM exits, and then resume guest execution, going through that barrier, of the WASM sandbox, the Hyperlight sandbox inside of the hypervisor to execute this code and output that back out. Okay. And with that, I will pass it off to Mihail to talk about a different use case.
Thank you, Dan. And that's where Envoy gets into a pot. Let's take that echo example that Dan just showed and put it inside Envoy. What is Envoy? So before Envoy, a little bit of background. This work came out of a 2 weeks hackathon project, and when I started, I didn't know anything about Hyperlight and knew very little about Envoy, so I hope it will encourage you to try on your own. It's not super hard. But what is Envoy? To put it simply, it's a configurable proxy. It's configured through a set of plugins, both built-in, and you create your own plugins in Go, Lua, anything that compiles into WebAssembly using a thing called proxy WASM. So those plugins expose callbacks, and Envoy calls those callbacks during certain events, like new connection established, or data arrives on these connections. Envoy calls into a plugin tells Envoy what to do. So plugins basically decide everything that Envoy does. And for this example, I would like you to keep in head a hypothetical, so not hypothetical anymore, example, use case where you run a service built on Envoy, right? And you want to expose this customization feature to customers. So customers create their own plugins, give it to you, and you run them on their behalf. Since it's not your code, you probably don't want to fully trust them and want to consider some protection mechanism, like some defense in depth, and that's where Hyperlight wasn't come into picture. So what I want to demonstrate is an Envoy network filter that instead of doing logic itself, will call into Hyperlight WASM, into WebAssembly model running inside it, that will actually do all the processing and return back to Envoy. A bit of background here. What is Envoy network filter? It's one of the simpler filters. It basically tells Envoy how to handle a TCP connection, and it has a couple of callbacks. One is on new connection, self-explanatory, and on new data. Again, self-explanatory. Just wanted to get out of the way. Now, reiterating a little bit what Dan already showed, what do we need to do? Well, we need to create a configure Hyperlight WASM sandbox. We need to provide pointer to a WebAssembly model. We need to define an interface between host, which in our case Envoy, and the guest, which is Hyperlight WASM with a WebAssembly model inside it. And yeah, that's it. For the sake of example, I will only show the interface required for the echo functionality, but it could be arbitrarily complicated if you want. Well, let's dig a little bit deeper into setting up the sandbox. You saw very similar code already. So what does it take to set up a sandbox? Well, that's pretty much it, right? There's not much to it. You configure the sandbox, what kind of parameters you might consider configuring in a real life example. Well, if you're running somewhat untrusted code, right, you don't only worry about the code escape in the sandbox. You also might want to put some constraints so that it doesn't use all the CPU available on your machine or all the memory available on your machine, right? Well, that's pretty much what you set up here. You set up limits on the WebAssembly runtime inside Hyperlight. On the Hyperlight itself, you set up limit on how long does you allow it to run before you start worrying and interrupt it. And the last part is just give it a model to run. That's all it takes. I skipped a bit here. You will see it a little bit later. For completeness, this is the Echo WebAssembly model. It's even simpler than Dan showed earlier. It basically exposes one function on data. That's what Envoy will call when data arrives on the connection. And this function doesn't do anything except like calling back into the host to say that, well, send it back. Like I don't want to deal with that. But obviously the model may implement a more complicated functionalities just for the sake of the example. Now, let's take a look at the interface between the host and the guest. So guest call, right? That's when Envoy will call into the Hyperlight. Well, it's not significantly more complicated than just calling a function, right? The caveat here is you call it by name, like in this case it's on data. You have to encode parameters of this function in a certain way, and you declare the type of the returned value. The reason you call it by name is because when Hyperlight guest starts inside Hyperlight, it normally registers all the functions that you should be able to call, and that's how Hyperlight knows the available names. When it comes to parameters, well, obviously there is some like serialization, deserialization going on when you cross the boundary from between the host and the guest, so you have to encode those parameters so that Hyperlight can understand them. Hyperlight has like relatively simple but reasonably complete type system that contains all like integers, floating point numbers, like vector of bytes, strings, whatever really you want. In this particular case, I'm passing a vector of bytes and the size of that vector of bytes. It's a little bit of quirk just for people who read the slides carefully. Vector of bytes already contains its own size, so you shouldn't really need to pass it, but it will go away in the future versions of Hyperlight WASM, so you don't need to worry about that. Now, host calls. With WebAssembly and Hyperlight, they do not really provide you with facilities to interact with external world. So if you want to talk over like networking connection, that's not like a part of WebAssembly. All of that functionality has to be provided by the host. In our case, the host is Envoy, and that's like just how you send data back. It's not super interesting. Let's just assume that we have this functionality implemented in the guest or in the host. How do you expose it then to Hyperlight? Well, that Dan already showed you just register this function with a name and callback, and that was the part that I skipped in the initialization. And that's basically it. At this point, your sandbox, Hyperlight WASM sandbox is created, and you can use it. One thing, sort of a practical aspect, right? You can circumvent a little bit the Hyperlight type system and use vec bytes for everything and use things like protocol buffers, flat buffers, whatever your preferred tool for serialization, deserialization of data, and just pass it in. And you will get whatever interface you want, and you wouldn't even need to think about like the Hyperlight somewhere there in between, right? So that kind of simplifies your work a little bit. Now let's take a look at the demo. The magic hand gesture. Yes, here we are. Connect. So I will show you now Envoy with a Hyperlight plugin that doesn't do anything. It just like loads a WebAssembly model that implements the logic. I will just start Envoy. It started rather quickly. Let me show you the config. It's relatively simple. The relevant part is the Hyperlight at the very end that just basically tells Envoy, please run the Hyperlight plugin. And that's it, right? The only configuration parameter in this case is just pass to WebAssembly model, and that's it. And now, when we have Envoy running, I can connect to it. Yep, I can. And it speaks to me, which is good. So that's basically it, we can see that there were some logs here that show that plugin actually got called, but that's basically it, right? We now had a case where WebAssembly model running inside of Hyperlight did something like when Envoy asked it. And coming back. Now, some integration challenges, like hopefully I will make you believe that it was super easy to integrate Hyperlight into Envoy. I ran through that pretty quickly. What didn't work well, that well at least? One of the more obvious things is that Envoy is mostly C++ code base, for better or worse. Hyperlight is like pure Rust. So you have to deal with a few things there, like you have to provide some boilerplate to be able to call Rust code from C++, and vice versa, like C++ code from Rust, because host guest calls go in both directions. It's not insignificant amount of boilerplate, but it's also not particularly complicated. So that's not a big problem. One thing that kind of caught me by surprise, but shouldn't have, is Hyperlight is multi-threaded. So when you call into Hyperlight, when you make a guest call, the thread that called into Hyperlight will get blocked, and all the host calls will come from another thread. That was particularly difficult for Envoy to handle because Envoy, as many other networking applications, is like sort of asynchronous, callback-based. Most of the processing happens in the same thread. And because of that, they actually don't need to lock much. So if you start calling into Envoy, like accessing Envoy data structure from another thread, like it's not prepared to do that. And sometimes it just doesn't work because they heavily rely on thread local memory, thread local storage. So you wouldn't be able to access those structures anyway. You just get nulls or whatever. So I had to like add some boilerplate to handle that, to return all those callbacks to the Envoy working thread so that it can access actual like Envoy data structures. So that's one thing to keep in mind. And the last one is not really an integration challenge. You might easily miss that, but it's important to understand that Hyperlight wasn't, at the moment at least, does not preserve the state between guest calls. So you call into guest, your guest worked something, like initialize some pieces of memory, some structures and whatnot, and then guest call finished, you call again, all that state will be lost. That limits somewhat functionality of what you currently can put in Hyperlight WASM. And as I said, you can miss it, so saying it now. Now, the interesting part. We created our like defense in depth, like what did it cost us, right? So let's take a look at some relatively simplistic benchmark that I did. So the idea of the benchmark, like I run this echo functionality, so very minimal logic. I sent a request, fixed size, random data to Envoy, get a response back, measure how long it took. Right, and repeat it multiple times to get an idea of what the average value, what the variability is. And I also change the amount of data I sent, like just to see if it affects something. What do I compare here? I compare here Hyperlight, Hyperlight WASM. I also implemented a native Hyperlight guest without WASM that just implements the echo functionality, but there is no WebAssembly runtime or anything of the sort involved. And I'm also comparing it to proxy WASM implementation of not exactly the same, but equivalent. It also implements a echo functionality, but like proxy WASM is a different thing, so it's not exactly apples to apples comparison. So I think like people who look at the slides kind of picked up on the, and Ralph also forced me to say that performance of Hyperlight sucks. Done. Yep, it is where we stand now, but it's not where we want to be, and there are definitely some low-hanging fruits there. I did some initial profiling. I was able to actually optimize Hyperlight native. When I mentioned earlier that Hyperlight WASM kind of loses the state between the calls, what I actually meant is that it goes and actively wipes it out, and that's not for free. And Hyperlight native actually allows you to like skip this bit, and it saves like 15% of like runtime, easily. There are some other low-hanging fruits that can be optimized as well. And I'm pretty sure that my integration wasn't the best ever, so there might be some overhead there as well. An interesting part is, like, as you can see, like on the left, we like sent 128 bytes, on the right 4 kilobytes. So it's like 30x-ish difference. And if you like squint, you can see that there is like a trend there. The more bytes you send, the more time it takes. But compared to the rest of the overhead, it's kind of lost there. So yeah, that's where we are at now. So where are we going in the future? Before that, let's summarize quickly. We achieved defense and depth. Cool, well done. It was simple. Cool, well done. Performance could be much better, put it mildly. So yeah, that's the summary. Where do we go from here? Some obvious things to get it out of the way. There is an ongoing work to provide some kind of C API to make it easier to integrate into non-Rust code bases. Well, that's out of the way. We want to integrate Hyperlight WASM as another proxy WASM engine. Proxy WASM, to remind, is an Envoy native way to run WebAssembly plugins. It supports multiple engines already, like V8, WASM time, whatever. Hyperlight could be one of those as well. Performance will become a focus area. As I mentioned, there are a lot of low-hanging fruits. There are some problems as well. Like, for example, it's not currently super easy to profile overhead happening inside the guest because, like, profiler just doesn't see it, right? We need some tooling to make it visible, like, or to make Hyperlight transparent. But, like, it's going to be also pretty important to optimize performance even beyond the low-hanging fruits, because the idea of, like, and the use case for Hyperlight is to put relatively small computation inside a sandbox, and the smaller computation is the more significant relative to this computation the overhead of the sandbox becomes. One cool thing to mention, and then said earlier, like WebAssembly is like architecture independent. Yes, Hyperlight doesn't support ARM yet. There was some work done to make ARM work, but we are not there yet. So something to tune in for future updates. Hopefully, it will be great. And on this note, I will probably pass the mic to Dan to tell us about his awesome book.
Yeah, this is just a bit of a shameless plug before we pass it off to questions. But like I mentioned in the beginning, I am authoring this book at Server-Side WebAssembly with Manning. It's currently in early preview, but if you want to check it out, you can use this QR code to do so. Oh, and also for questions, I have some free books to give out, or codes to get the free book. So I guess maybe 5 first questions, you get a free book. Okay, and I guess with that, we pass it off to questions.
Mikhail, I was going to ask you whether one of the things that very much interested me was the lack of state retention. And when you mentioned that, so I was going to ask you about your experience with Envoy. Are there, what kind of situations occur where state retention is actually something that in Envoy network filters is used now?
Envoy is like very much stateful in this regard, but like to conceptualize where do we need it, right? Imagine this, like if I return a little bit back to the interface of this network filter. Sorry. Yeah, here. So on new connection is called once, but on data is called like multiple times. The data may arrive to you in arbitrary chunks, right? What you might want to do is, like, for example, if you want to build like HTTP interface out of it, you take and incrementally parse it, and for that you need to preserve the previous state. There's like a bunch of other examples, like maintaining counters of different type, or like for example, if you process an HTTP request, you do something when you get the headers, you calculate something throughout the body, and then like append some trailer in the end, right? This would be an example where you kind of have to preserve the state between like various calls. To be honest, like you don't have to do it this way, right? You in principle can imagine a different architecture where you kind of maintain the state throughout somewhere else, but it will be relatively complicated and will complicate the plugin architecture, right? If you ask Envoy to like maintain everything on your behalf, right? That will just make the plugins less powerful.
Any other questions? I actually have one. So you talked about defense in depth as the reason for putting WASM inside of Hyperlight. Can you expand a little bit on that?
Yeah, sure. So you want to know, I guess, the security aspect of it, or?
Yep.
Okay. So, well, one thing, you have, hypervisor technologies that have been used for decades, and we accept the security of them with KVM, MSHV, WHP. Then on the other side, you have WASM, which has a bunch of other benefits that we might want to use, like it's language agnostic. I guess maybe the architecture-independent bit gets a little bit lost if you're running it with Hyperlight. Doesn't support ARM, like Mikhail mentioned. But there's a bunch of benefits with language agnostic and so forth that you might want to leverage with Hyperlight and still be able to run with some sort of third-party cloud, or that perhaps wouldn't run just the WebAssembly runtime by itself. So putting that within Hyperlight enables it to run in that scenario, and you can still use the cool new modern bits that are coming out today.
So it enables a lot of interesting use cases where you use the WASM interface and you get the value of the hypervisor.
Yeah, that's right. Even the example that we saw with the WIT, right, and being able to use that WIT interface to register host functions, using core Hyperlight, that will look very different with just registering a bunch of host functions that are specific. While on the WebAssembly side, there's a bunch of those interfaces that are standardized, and that can then have also standardized host implementations that you could then just get sort of out of the box SDK free.
Thank you.
Just a bit of like Envoy context in this. When proxy WASM was introduced, one of the things that they like, how they pitched it, why it's useful, why do we want to introduce it, was that Envoy internal like APIs are not going to be stable, but proxy WASM APIs are going to be stable. And that's why, for example, proxy WASM is actually not just for running WebAssembly inside of Envoy. You can actually use proxy WASM to run native plugins inside of Envoy because it provides a stable interface. So that's kind of WebAssembly kind of indirectly created a stable interface for extending Envoy that wasn't there before.
Great. Thank you, guys.
running up and down. I don't need to be on the live stream. I don't need to be on the live stream.
Oh, okay.
Is everybody that's giving a lightning talk feel comfortable and have tested their laptop? If you could sit in the front row, that would be great, so that we can make this nice and fast. Where are my lightning talk people at? Raise your hands. Okay, cool, cool, cool. Hopefully the rest will wander in. Good. All right, so thank you all for sticking around for the full day of rejects. We are now starting our lightning talks. My name is Lori. I was one of the program committee members. I am head of community at Percona, and you got to give it up to Benazar for like putting on a stellar show yet again. I don't remember what number this is, but it is a freaking kick-ass way to start our KubeCon week. So without further ado, let's kick it off with running Kubernetes on your workstation with Kind and Podman with Alexan.
Thank you, folks. So now the rush starts. I have 5 minutes, so I'll be real quick, okay? I have a bunch of slides for you. I'm kidding, it's just this one. I'm talking about running Kubernetes on your workstation with Kind and Podman. If you were here yesterday, there was a talk from 2 colleagues of mine from Red Hat. They talked about Podman Desktop, the benefits of it. So I recommend you to watch the presentation again if you didn't watch it, okay? So let's go for the demo, because as Yoda says, show me the code you must, right? So, Podman Desktop, this is the interface that you're going to use. Right here, you have a bunch of options, okay, to create lightweight Kubernetes clusters. You can create Minikube. Soon, you can create microchip as well. But right now, we have these options here. And out of these options, I selected Kind. Why? Because it's a lightweight cluster, and it has this concept of installing a cluster using container as a node, okay? And also, it's real quick to spin up a cluster, and to put your application to work with it. Using Podman Desktop as the GUID, you're going to see that it streamlines the process for you. You don't need to like type any command or stuff like that. This is especially helpful for the ones that are not developers, okay? So let's create our cluster, but first, let me show you that I have no cluster installed yet. Okay, no cluster. So let's create our cluster using the Create New button. And I'm going to expose my 80 port and 443, okay? And now create. While it's being created, you can see here at the Show Logs button, all the logs of the process going on in the background. Also, I can click here and type get pods to see all the pods being created. In a few seconds, you're going to see all the pods being created here, okay? And for this specific demonstration, I also selected the Envoy as my a way to expose my application externally using Ingress, okay? The community is thinking about using other tools for that, like Nginx, for example, is not available right now, but it's possible in the future. Right now, we have only Contour that uses Envoy for that. And now my cluster is being bit up, and it's ready now for me to use. As soon as it's ready, you're going to see that Podman Desktop selects for you automatically the context. In this case, Kind Cluster is the name of my cluster. And if I check here now, you're going to see that it created all the default pods for my infrastructure, for my control node here. And also it's creating now the Contour, and soon it's going to create the Envoy pod as well. It's creating now. While it's creating my default pods for my control plane, I'm going to create a container here, okay? So I can click here using Podman Create button, select an existing image, and I'm going to select, for example, this one HTTPD. It's very simple. I'm going to put a name at this container, HTTPD as well. I'm going to expose the 8080 port. I'm going to click here at Advanced, and I'm going to select to automatically remove the container as soon as I delete it as well. In the networking part, I'm going to put the host name of my container, HTTPD as well. And in security, I'm going to turn off security for this specific container. Simple as that, my container, it's going to be up and running now, as you can see here in the summary. Okay, I can check the logs for the container specifically. I can use the inspect button to see, using a Kubernetes manifest, all the information about my container. And if I go back here at my terminal and I run podman ps, you're going to see that I have a local container running in my machine, okay? So what I'm going to do now is deploy the same container that I have running in my machine into Kine. As you can see here, Kine is already working. Okay, all the pods are available now, and I'm going to expose my container to my Kine cluster. Just click on this button here and select and create an ingress specifically for this container. And as soon as I click deploy, right here down the bottom, you're going to see the log and the manifest of this pod that is being created in my Kine cluster. Also, I can follow up here. The container is being created now, my HTTP pod container. And boom, it's running. Okay, now I don't need my local, I don't need my local container. So I can simply click here, delete it. So I don't have my container locally anymore. It's only available through my Kine cluster. And I can click here in this Kubernetes dashboard. What I can see some information is about my cluster. How many pods it has, how many nodes it has. For example, if I click here nodes, you're going to see that there is a node specifically related to this cluster. By default, it creates this default node as a control plane node, okay? But you can create multi-nodes. You can create control plane nodes, you can create worker nodes, and etc. And now, as you can see here, my application is up and running. So just to show to you that I'm not joking, I'm going to curl my local host, and it works, okay? So if I don't need it anymore, what I can simply do is just go back here, delete everything like this. For example, I delete my ingress, I can delete my service, I can delete my pod down here as well. And finally, since I don't need this cluster anymore, I can delete it for good. So I can go back here at Podman Desktop, Settings button, Resources, click at the Kine cluster, stop it. You are able also to stop and start your cluster as many times as you want. And finally, as soon as it stops, I'm going to delete it, okay? So as it's stopping, this is the demonstration real quick just to give you an overview on how you can work with Podman and Kine, okay, to streamline your process to create your application and test it on your own machine. That's it. Thank you.
Well done. A live demo in 5 minutes, and it worked. Cheers to you, sir. Next up, we've got Thomas. Okay, so Thomas is going to give us from black box to open book, leveraging open telemetry for auto-documenting distributed systems. Bum, ba-da-da. And we golden, yeah?
Oh, there we go. Okay, this is serious stuff.
All right, time starts now.
Okay, great. Where's my mouse? Uh-oh, okay. Okay, hi everyone. This is serious stuff, lightning talk. Okay, I'm excited to be here today. So first, quick question. Who here has heard of Observability 2.0? Show of hands. Okay, a few of you. That's great. Okay. A little bit about me. My name's Tom. I'm co-founder and CTO of Multiplayer. Multiplayer makes tools for teams that work on distributed systems. Many of those tools leverage OpenTelemetry. The goal of my talk is to spark conversation about how OpenTelemetry can be used to help teams understand their systems in new ways. I have two examples, auto documentation and platform debugging. As an industry, we've struggled to agree on the definition of the term observability. We tend to limit it to telemetry and monitoring. However, observability can be much more, and that's where the distinction between observability 1.0 and 2.0 originates from. Shout out to Charity Majors for coining the term. Quick overview, observability 1.0 describes solutions closely tied to APM tools. At its core, it focuses on operations, highlighting issues once software is in production. Developers don't really like using APM tools for things like system documentation and debugging. There's too much data, it's not in the form that you need. You frequently have to search for a needle in a haystack, and because of sampling, many times the needle isn't even there. The term Observability 2.0 is meant to move beyond the typical DevOps workflows to empower the entire team throughout the software development lifecycle. let's look at first example of how you can use OpenTelemetry with an observability 2.0 mindset. I'm sure we'd all agree that good system documentation is important, and yet we're still plagued by these problems. Why are we still doing this stuff manually? So here's a quick overview of a typical OpenTelemetry deployment scenario. We start with a platform. Once instrumented with OpenTelemetry, logs, metrics, and traces are routed through a collector to an observability platform. There are multiple ways to hook into this flow of data. You can generate trace IDs, specify span attributes, modify baggage. You can have a custom processor and a collector, and you can be a destination for the telemetry as well. For the purposes of auto documentation, we generate unique trace IDs, add information to spans, and we have a processor in the collector that makes us a destination for a small portion of the data. When we receive spans, we analyze them because there's a lot of interesting information. Where did my mouse go? Sorry. Okay. Anyway. Sorry. Whoops. I've lost my mouse. Okay, let's go back here, little guy. Okay, here we go. Okay, sorry about that. I can still make it. I know I can still make it. So the system is a source of truth, and the docs are up to date and trusted, and you can do the same. Okay. Let me give you another example. These are common pain points I hear from teams debugging distributed systems. Why isn't it easier to report and fix bugs? For debugging, it's the same thing. We generate trace IDs and add span attributes. We add data to spans that allows us to correlate all the traces and logs for a debug session. We have a processor in the collector that makes us a destination for the data, and we put all the data in a debug session in a single place, so it's easy for developers to fix issues quickly. No more manually writing down steps to reproduce bugs, trying to reproduce those steps, or trying to find the needle in the APM haystack. So just like Autodocs, this is something you can do as well. So just quick recap, Observability 1.0 and 2.0 are not mutually exclusive. They're complementary and serve valuable but distinct roles. Observability 2.0 represents a move beyond traditional DevOps workflows to include workflows for the entire team. And looking ahead, OpenTelemetry can be applied to many other use cases. We're working on others as well, such as automatic debugging. Think of this as like session sampling. And Debugger Gateway, which makes it easy for teams to develop and debug services in shared environments using just their IDE. If you're interested, let's chat more. Thanks for listening to my talk. I made it. There's a QR code. How was that?
You made it. You made it. 5 minutes. Boom.
Beautiful.
All right, so if anybody just came to the room and you're wondering what's going on, we are 5 minutes behind schedule with our lightning talks, but our lightning talks are hitting the 5-minute mark. So cheers to everybody thus far. So next up, we've got, how do you say your name? Alex? Oh, just kidding. We've got Alex with Myths and Truths about Observability Overhead. So take it away.
Okay, thank you. My name is Alex. I would like to talk about some myths around observability instrumentation overhead that I encountered again and again during something like a decade while working in the observability space. So first of all, what is instrumentation overhead? Let's say we have a function called process here that does some computing, and because of that, it causes some latency. Now we would like to measure this latency, right? So we would use something like OpenTelemetry that we just heard about, the de facto industry standard for instrumentation. For that, we would inject some code to measure the latency, to get some metrics, spans, tracing, logs, and so on. But executing this code will also cause some additional latency, right? So the overall latency increases, and this piece that is marked in yellow here is something that the users would experience as overhead. Now that we have very roughly clarified what instrumentation overhead is, let's talk about some myths. First one, instrumentation overhead is the same as latency increase. I mean, it's true that latency is one form of overhead, but there are definitely also other manifestations of overhead. For example, increased resource utilization like CPU, increased memory allocations, or also network traffic increasing. Depending on the instrumentation type, whether you're using auto-instrumentation or you're doing it manually, it can also have an impact on your startup time of your application. And finally, even the effort to put your instrumentation into your application can be seen as some sort of overhead, right? If you're doing it manually, it's more overhead than when you're doing it in an automated way. And the more important question is actually, or fact is that all these different dimensions are interrelated. So if you're improving one of them, you might be impacting another one. Let's come to the next one. Some people think like observability instrumentation can come for free. Actually, there's always some instrumentation overhead, right? It's like with Schrödinger's thought experiment with the cat. When you measure something, you also impact the system. So if you want a higher detail of instrumentation, that will come with a cost on the latency. If you want to automate instrumentation, it will very likely also impact the startup time of your application. And if you want to have reliable collection of your data without any loss, this very likely will also have some impact on memory or also network traffic. The more important question is, how big is the overhead? And is it acceptable for the value that it brings for your observability use cases? Let's come to the next one. Some folks think that auto-instrumentation and zero-code instrumentation is something like dark arts that will break and slow down your application. In reality, those agents and instrumentation agents that are used in the industry are being used by thousands of companies and millions of services. So those are battle tested, they are robust, and most of them are really designed for acceptably low default overhead. So it's usually quite safe to rely on auto-instrumentation and instrumentation agents. Yeah, my favorite myth is this one. One can make a general statement about the percentage of overhead that would apply to different applications. When you give a talk about observability, the first question is always, what is the overhead of an agent or something like that? Yeah, actually, the problem is it really depends. It depends on many things. First of all, something like the application size, the detail of your instrumentation, how you configure your agent and also your runtime, what is the load on your application, and what is the type of your application that you're running? Is it an e-commerce application or something like a high-frequency trading app? So there's actually no way to tell what is the exact overhead of an agent without knowing the very concrete context. And finally, there's the fear out there that auto-instrumentation is more expensive than manual instrumentation. I mean, that is partially true, especially when we are talking about auto-instrumentation that is applied at runtime. So this will impact your startup time of the application. But once this startup phase is over, basically the instrumentation stabilizes and yeah, the overhead is comparable between auto-instrumentation and manual instrumentation. Okay, finally, let's talk quickly about how you can control instrumentation overhead. First of all, you have tools like sampling that allows you to reduce the data volume, and especially with instrumentation agents, doing something like head-based sampling allows you to reduce the overhead. With auto-instrumentation agents, you can also disable different instrumentation modules that allows you to fine-tune basically what data should be collected, and that also impacts the overhead at the end. In general, it's really a good idea to avoid fine-grained instrumentation. So it's certainly a bad idea to instrument something like a getter method that is being called 1,000 times a request. If startup time is important for you, something like in an AWS Lambda function, then it's really a good recommendation to use manual instrumentation, as it won't impact your startup time that much as auto-instrumentation. And finally, also try to avoid complex payload parsing at collection time. For example, parsing a huge SOAP message to get some information out of it is definitely not a good idea to do it during instrumentation. So that's it. Basically, don't be afraid to instrument your applications and don't get misled by the wrong myths out there about instrumentation overhead. Thank you.
All right, we need our next speaker up. And can we all just again give Benazir a round of applause for getting champagne champagne to the lightning talks. I mean, what in the world? We get free coffee, like good coffee, right? Everyone saw the espresso machines. Water all day to keep us hydrated, for the champagne to kick us into the rest of the night. Not a bad way. All right, so next up we have Nicola, who's going to talk about deep dive into Gateway API backend TLS policy. And
I have to see where is my mouse.
are you?
Okay, I lost everything. Sorry. Okay, just it's not in the good way. Sorry.
Do we need AV?
It will be okay.
This is what happens when the demo gods win, the regular gods like lose. There we go. Yeah, they can't see me.
Oh, black magic, sorry. Okay, I will have 5 minutes just to extend my screen correctly. Sorry for that.
Everyone drink up. This is what, the champagne's for.
Just everything, okay. So let's do like that, okay. Okay. So hello everybody, let's start. So today I will show you in 5 minutes how to set up an end-to-end TLS connection with Gateway API resources backend TLS policy.
Good.
Yeah?
Oh.
Better like that. Okay, I'm Nicolas Mangin. I'm a maintainer of Traffic, the OSS Gateway Controller, and I'm working at Traffic Labs, the company behind Traffic. So what do I mean by end-to-end TLS connection? So TLS allows us to encrypt the data transmitted by the client, but where common architectures do the TLS termination on the gateway and use a non-encrypted connection between the gateway and the backend, an end-to-end TLS connection will ensure you that the connection is encrypted until the backend. It's very useful when you want to set up a zero-trust security architecture, because you will ensure that you prevent any data breaches even inside your cluster. And on top of that, TLS is required for HTTP2 and gRPC connections. So how to do it? If you want to keep all the HTTP capabilities, such as the HTTP filters, for instance, you have to stay at the HTTP level, and you will serve a certificate on both the gateway and the backend. But in Kubernetes, we're used to using an ingress object to expose our payload. And even if the specification supports a way to serve a certificate on the gateway, there is nothing in this specification to establish a TLS connection between the gateway and the backend. And we have to use a vendor-specific annotation. Like here, I'm using a traffic annotation and a traffic custom resource. This is where backend TLS policy and gateway API come. So let's dive in the recipe. First, we need TLS certificates. I've created an external certificate served by my gateway and an internal certificate served by the backend. Both of them are stored in a secret, and I stored the internal CA. It's a CA route I used to generate the internal certificates in a config map. After that, I installed a gateway controller, and I referenced it using the gateway class. So I'm using traffic. The third step is the gateway. The gateway allows you to define the entry point on your infrastructure. Here, I define a listener, an HTTPS listener on the port 8443, and I enable the mode terminate. It means that the TLS termination will be done on the gateway controller, and it will serve the secret external cert. The TLS certificate stored in the secret external cert. Next step, the HTTP route. The HTTP route defines the routing rules, and here, every request with the hostname wami.docker.localhost and the path /wami will be redirected to the service wami-tls on the port 8443. This service exposes a simple web server that is reachable in TLS on the port 8443. As you can see, we mount the secret internal certs to use the TLS certificate stored inside. And now, the backend TLS policy. Why? Because without this object, we will establish a TLS connection until traffic. Traffic will serve the service, but it will establish an HTTP connection to the backend, and it won't work. But the backend TLS policy allows to establish such a connection between the gateway controller and the backend. It required an host name. The host name is the SNI the gateway will use. Okay. And of course, it could fit with the domain served by the domain the certificate on the backend can serve. I set a CA certificate refs to set my internal CA route. You can use a well-known CA route instead. And the backend TLS policy can target either a pod or a service. Here, I target a service UAMI-TLS. Using a simple curl command, we can see that the architecture works. The client will establish a TLS connection to traffic. Traffic will serve the certificate, create an HTTPS connection to the backend, which will serve the internal certificate. You can find the slide and all the manifest flashing the QR code, and we can reach out during the KubeCon if you want. Thank you.
Hey, where's Yash? Oh, he didn't listen. It's okay. All right, how are you guys doing so far? Everybody good? Audience feeling good? All right, cool. So Yash is going to talk to us about multiplayer Kubernetes GitOps with friends. Everyone cross your fingers. Did somebody not cross their fingers? And we're money, sweet.
Hello everyone, I hope I'm audible. I'm learning British accent these days. I'm not sure how good I am. But yeah, this is first time in the London. So I have 5 minutes, I'll be quick. Today I will talk about the multiplayer Kubernetes GitOps with friends. The title is pretty, interesting. So So I'll talk about a little bit about myself. So I'm Yash, developer advocate at DigitalOcean, and a maintainer of a project called Mishri. Mishri is a CNCF project. It's a sandbox project right now. So what is cloud native management? So we have seen that from the past 10 years, we are writing many YAML files, right? And it's been so many years that it's a so tedious task to debug those YAML files and writing those complex YAML files, and we are moving towards more of UI dashboards. So what Mishri is trying to solve is for you to provide a platform with a better user experience where you don't need to write any YAML file anymore. You can just use the facilities like drag and drop and create infrastructure for your Kubernetes cluster and in the future for your cloud platforms as well. So this is something how it looks like. So in this screenshot, you can see that there is a platform where 2 things are connected with each other. This is what we call design. We have some edges, so we call these as a component where you can drag and drop the pod, connect them with each other, and visually see your infrastructure. You can also connect your Mishri with existing infra, and it will show the visual interface of your infrastructure right now. You can go and use the Mishri on canvas.new as well. Mishri is multi-cluster management, so you can collect multiple clusters with your Mishri, and it also provides the context-aware design. So what context-aware design mean? Like, Mishri is intelligent enough to understand if a pod can make a relationship with service or not. If it will show you in the UI itself. I'll show you the quick demo as well. So yeah, I hope I don't miss anything. It also supports 200+ integrations. So if you go into the CNCF landscape, you will find so many technologies, and Mishri connects with most of them. So you will find most of them in the Mishri playground. So I'll show you quickly how that looks like. So this is how Mishri looks like, where I have my Nginx deployment and Nginx service created. I was having some issues with my Kubernetes cluster, which I have created on DigitalOcean. So, but I was doing that, but I will not be able to show you how it deploys, but I'll show you how that works. So in this one, you can see there is a pod which I created, which is the Nginx deployment and the Nginx service. And it is showing how both of them are created. Once you create them, you can configure them by clicking on it. You can give some information. And after that, you can click on actions and click on deploy. And that's it. It will deploy on infrastructure. You don't need to do anything else. Like you can just click on this one, search anything which you want. Let's say namespace, I want namespace. Drag and drop, give the name for your namespace and hit the deploy button again, and it will deploy for your infra. You can use the operator mode where you can see the existing infra of your Kubernetes cluster as well. So for now, this is a design I created and published it as well, which you can use. So once you go to the canvas.new, you can click on the catalog and click on the most open one, which is the Nginx deployment, which is created by me. So you can go ahead and you will be able to see this kind of your design in your Mishri, and you will be able to deploy it in your infra. So yeah, that's it. I'll go back to my slide. Okay. Okay. How you can start? Like Mishri is right now in the incubating process. You can go ahead and check out the Slack channel of the Mishri. Do join. We'd love to have you there. We would love to talk with you. How was your experience? We are working on something which is great. We are working on towards solving the problem of complex YAML files. Do join us. Let me know. I will love to talk with you guys even after the talk itself in the Cloud Native Rejekts. Thank you, everyone.
Big ups to all of our speakers, just keeping on time. So next up, we have Paul. Very difficult name to say, Paul. And he is talking about scheduling complex deployments across large multi-cluster test beds. Perfect.
Is that showing? One second, sorry.
How many of you, this is your first rejects? Awesome. How many of you are local to London? Wow, so big ups to all of us coming from wherever to be here, and cheers to y'all for not having to come far. We're gonna make this work. Okay, how many first time? Hands up. Second time. Third. Fourth. Fifth. Sixth. All my 5-year people, raise your hands. It's awesome. Cheers to y'all. Are we good?
I'm not sorry, I'm having a bit of a blunder. Apologies.
No worries. This is a supportive room, and we had champagne, so nobody should care at this point. We are good. We are behind you.
Yeah. I can see my slides, just not my notes. And I've lost my mouse. There we go. Apologies, I'm sorry.
No worries. Note to self, you can do Google Slides on your phone, and you can get your presenter notes on your phone. Just, that's how I roll.
I'll make this in about 3 minutes then, just to catch up. So my name is Paul Power. I'm from Waterford, Ireland. I am in the EU research team. I'm currently working on EU Horizon projects. So the main project I'm on is P2 Code. So I'll just give you a little quick overview of what P2 Code is. It stands for Programming Platform for Intelligent Collaborative Deployments. So it's essentially a developer platform for integrated CI/CD pipelines for creating cloud-native applications designed for deployment on edge devices. So just a quick overview of our responsibilities then. So essentially we're just responsible for the scheduler, which I'll get more into a second, the resource manager, distributed storage, cloud controllers and drivers, create and shift, OpenShift as a service on demand and keeping it dynamic, deploying OpenShift in different infrastructures, and then pulling telemetry data through Prometheus, extended through Miramar, and then centralized in an AWS instance to report that runtime data out. So the main issues we were facing with scheduling and how to kind of tackle these complex test beds across various locations in Europe would be cluster growth. So if something is hitting capacity, we need the ability to spin up a new one dynamically but register it into the pre-existing test beds. Resource availability, we need to optimize resource management and scheduling intelligently, so it's not just going to bring up things constantly. Performance as well, ensuring clusters aren't overloaded while keeping energy consumption as low as possible and try to keep it green. And then within the application area specification requirements, so within the project there's 4 application areas and there's 2 use cases per application area. And some of them have very specific hardware requirements for each, so it's important to know what's where at any given time. The real challenge here is just managing the workloads in a multi-cluster environment efficiently, ensuring optimal resource usage and low latency and high availability. So the main way we're doing that is with custom annotations and with node feature discovery. So, sorry, I think I skipped the slide. I did, I jumped over OCM. OCM provides, it's a powerful tool for managing multi-cluster environments, but we need more than just the basic scheduling that comes in the box with OCM. So with this, we're using the custom annotation features that is available by extensions and node feature discovery as well. So with the custom annotations, we can guide the system to make smarter scheduling decisions, optimizing for factors like locations, resources, and health of each cluster. Custom annotations and node feature discovery complement each other very well. The annotations enable us to fine-tune placement strategies, while node feature discovery supplies essential node-level information, such as the hardware capabilities available at each node, and then aggregate it back up to a cluster, so we know what's available on each cluster all the time. It'll give updates. I think we'd said it's every minute, so it's constantly up, and we know what's where. So the key benefits then, this approach leads us to smarter and more efficient workload placements, reducing latency and improving overall system performance. And by integrating OCM with custom annotations and leveraging node feature discovery, we can create a powerful dynamic scheduling system that improves performance, resource utilization, and reliability that can be fully extensible. So that's just a quick overview of the design. I'm not going to go through all of it now because there is a lot in it, but essentially we'd have an OCM hub deployed on each of the application area clusters. Underneath that, then there'd be the managed clusters under it. And then it essentially takes in the manifest work at the top level, which is then read by another partner's component and broken down into a separate YAML that is pushed back in with the set annotations in it, and then it determines on where it's going to push it out to once we have all the correct labels added in on each node. And that's just a group of the other people we're working with within the consortium on the project. And that's it. Thanks very much.
Thank you, Paul. And for those of you that are just joining us again, we are a little bit behind on scheduling, not because our speakers have gone over, but just because of some technical issues. So we've got Ingi up next, and he is going to give us the wise way to YAML. Thanks. He's got a pretty good title. You'll see it when you can see it. And we are good. Sweet. Let's go.
Let's do it. Hello. What if YAML files could include other YAML files or JSON files, because you know that JSON is a subset of YAML, right? Or CSV or TSV, XML, whatever, or specific parts of those files. What if YAML files could include data from the web, from a database, or any data source anywhere? What if YAML would let you do all the programmery things that you do when you're programming in YAML and still be a data language? What if you could use external libraries from all kinds of places, including WASM? What if there was a YAML loader library, like PyYAML for Python, in every programming language that worked the same everywhere, had the same features, was the most configurable, most secure, and actually correctly implemented the YAML 1.2 spec, which almost none do? What if it was a drop-in replacement for whatever YAML library you were using now? It would have to have the same peculiarities so that you didn't, they're all different actually, and you didn't break your users' config files. What if the YAML dev team made a new YAML 1.3 spec in 2025, and there was a fully working YAML 1.3 library in every programming language as soon as it dropped? My name is Ingi.net. I created the YAML data language spec starting in 2001 with a couple of friends. I lead the YAML maintenance team with 4 new friends, and we are planning the next spec. In the last 2 years, I've created the WISE YAML framework. So WISE is the new YAML engine. It's pronounced WISE because it's the plural of YS, right? WISE addresses YAML's problems and needs for everyone, not just for Kubernetes, not for just for Helm, for everyone that uses YAML. Learn about it at yamlscript.org. Your current YAML is valid YAML script. It will load with WISE. You can make it functional by adding a special tag to the top. All WISE code expressions, the programming parts, are 100% valid YAML. They have to be. And you have full control over what capabilities you allow your users to use out of those functional. It could be none. It could be actually less than YAML supports out of the bag. Fine-grained control. Okay, so let's look at a contrived example of a YAML file and another YAML file. So the one on the left is assigning some variables, pulling data from the web, loading data from a file, and selecting a random true or false. And the next document might include this pair that says maybe this pair will be included, and it's going to take 5 names from a giant list and print out a little letter. So let's see what happens. Okay, it didn't print that possible thing, but it printed out the nice letter from Daniette. Random numbers. There we go. So that random pair showed up. What would Helm look like if it had, instead of Go templating, YAML script in it? Well, let's take a look. There's a web page at yamlscript.org that you can see controlled. It would look like this, about half the size and about half the width, and really tight. So everybody on the Helm team loves this, everybody in the last KubeCon loved it, and Matt Butcher personally loves it. He told me on the phone. Oops. I joined the Helm 4 team to make this a reality. So WISE loader libraries want to ship to 42 languages. That's my goal. 10 so far, but they're really easy to make. If you have a language that you'd like to see, let me know. WISE is also a complete programming language. If you go to exorcism.org, who's heard of exorcism.org? It's a language learning site for 75 programming languages, including YAML script. So, there's some. So you can learn it there. Let's take a look at an example, 99 bottles of beer on the wall. There's the YAML program that prints that, and it takes a number, defaults to 99. Let's run it for 3 bottles of beer, and it works. And this is another program that does an API call. Let's just look at it. So this is all of the code that will post the list of files that follow the name as a GIST file, a URL that you can click on and see those files. It's tiny, and that's the end of my thing. But my last slide is here. So that was all I could tell you about this vast subject in 5 minutes. I hope you have hundreds of questions, and if you go to yamlscript.org/rejekts, you can find out how to contact me and ask me. Are you all this week, please?
Thank you. Did anybody else not realize that we were with the inventor of YAML? Like, what? What? Y'all, clap it up. Like, 5-minute lightning talk. Like, thank you.
I think most of the Gen Zs didn't even realize it was ever invented, I think.
Us Gen Xers, we got to hold strong. Okay, cool. So, wow, that was eye-opening. Next up, we have Joaquim. Headlamp in, are you, oh, okay. And y'all, when I said sit in the front row, I was trying to make things better for all of us. Okay, we got you. Plug on in. Here you go. Okay, cool. All right, so Headlamp integrating external tools so you don't have to.
All right.
Well, maybe not. There we go.
Okay, thanks. Okay, so very quickly, I hope. CLIs are nice. I use them all the time, use them all the time, all that. They work in a very similar way, and every cloud provider has their own CLI tool, so you know that's very convenient. We can even say that it's the ultimate common interface, right? Because when you see some tool, you expect it to at least being able to run it in the terminal, if it's around, you know, our little thingy here. However, you know, they're not the most beginner-friendly choice. So they require the memorization of the commands, the syntax, how the parameters go. There's this lack of discoverability that you know that you have in these tools because you need to know what commands to use in order to use them, and it's kind of error-prone, right? So it's not a guided approach in conclusion, and you know, and I love CLI tools. I use them all the time. I never did anything like that. Yeah, so this is to say that we all agree that GUIs or graphical user interfaces are much nicer, right? So let's check Headlamp. So Headlamp is a UI for Kubernetes. It can run as a desktop application or a web application. It's vendor independent. You can run it with whatever flavor of Kubernetes you want. It relies on RBAC, so you don't really need to run it with a special permission, service account, stuff like that. And it's open source, and one important thing is that it's extensible through plugins, right? So what does this mean? And by the way, that's a whole video I'm not going to play, but what this means is that since the last version, you can also run CLI tools. So Headlamp has a, you know, it's a browser interface. If you run the desktop application, we still have like the backend in it. And now we open the possibilities for plugins to run commands. And yeah, and so, you know, we have several plugins before we had this possibility. One of them was, you know, sometimes it was even tools that you have to run in the command line, for example, Compose here. But we had to find a way to run them, for example, in the browser, in the cluster. In this case, I need to run Compose, so I would create a job, Compose would run, and interface with it like that, right? So the logic had to run somehow in the cluster or in the browser. This is the last version. This is the right slide that I was trying to get to. You know, we allow the desktop version again to run programs. So that means that sometimes you cannot run stuff either in the browser or in the cluster in this case. For example, let's say you want to create a Minikube cluster, right? You're not going to run that in another cluster. So right now you can do that. Of course, there's always a security implication to think of, and when you have a plugin that needs to run some tool, we do ask the user, do you want this tool to be run? Do you allow that? And so you can think that, you know, we do have a plugin for Minikube that provides Minikube, like I was saying. But the idea is that you can imagine like having stuff for example, cloud providers, so you can access, you can run their tools
locally, and you can expose that as a nicer UI for the users. And that will hopefully make the project, make those CLI tools much more accessible. And check out our website. That's all I got for you. Thanks.
Thank you. Okay, next up. I'm terrible with, okay, how do you say it? Engin. Okay, sorry.
Ingi, but Engin.
All right, Engin, yes. So we got a fan club. This is awesome. Fangirling, fanboying over here. MCPS in a DevOps world. Everyone, fingers crossed.
Yeah, let's see if it's working.
You got this.
Okay. Just a second. Sorry.
No worries. Did anybody catch my shirt? Like, what's different? Like, what doesn't make any sense? Can anybody? That's so wrong. All right.
Okay.
And here we go.
Okay, you see, I'm using PowerPoint, I'm still old school. So AI, yay, AI, it has to arrive also here. So depending on your stand, you are either this fraction like, yeah, AI, it's all snake oil sellers and it's not cool. And maybe you're also the fraction of, hey, AI is here to stay, it helps me so much and so on. So independent of what you're believing, and I just want to show you something from my perspective, which I found very interesting, because I'm also looking, I'm not really jumping onto everything which is new in the AI space, but I found this Model Context Protocol, MCP, very, very interesting, not only because of the way and the things they're going to achieve there, the possibilities we have now, but also seeing other people, the success. So for example, we saw some MCP servers connecting here to the Unreal Engine. I saw things with Blender, for example, so they connected the MCP server and then achieved things using natural language inside Blender or inside the Unreal Engine to create things. And then we saw also here with the releases here on the Cloud 3.7, the stars, if you take this as a vanity metric, but still it's really growing fast. And then also some random people on Twitter I just picked up who says, I'm going to build a PowerPoint automation for MCP. And now comes the biggest thing, which was for me an eye-opener when I saw the news from OpenAI when they say, hey, we're also going to support the MCP, which is, standards. I mean, I'm from Europe, we have USB-C and all the stuff and the plugs and the things. So getting standards is always difficult. And seeing here that OpenAI jumps also on the MCP protocol was really like, okay, that has to be. And then, of course, you have starting now seeing this GitHub repositories where people collecting some awesome MCP server examples. And then we see also that it's keep on evolving. So with the latest protocol version, they also tackle now things where we critical person are like, hey, how is it with security perspective and so on and so on. They're working also on this part. So we see OAuth authentication is there. So now I want to talk about MCPs in a DevOps world. So again, probably you're like, hey, what are MCPs? Okay, so that's from the official explanations say, okay, the Model Context Protocol is an open protocol that enables a seamless integration between LLM applications and external data sources and tools. And now we see with the DevOps world. So if you're really interested into this, I'm not that geeky enough to go through whatever lines of code for the JSON specification. This is the latest version. It's publicly available. Just quickly, how does it work? Yeah, we have our MCP host. It could be your IDE. It could be a tool. It could be N8N or Claude desktop. And then, depending on what you configured in your tool, it's going to start the MCP servers. There's a specification, SDK, how to build the stuff, and then interact with the systems behind through this unified protocol. So I can now talk with natural language with my Docker daemon. I can work on Kubernetes stuff. I can create GitHub accounts and all this stuff, commit data. Very interesting.
So MCP introduces 3 key interfaces for data interaction. So it's tool prompts and resources. So tools are standardized actions declared on the server. So you can say, hey, please use kubectl, use Helm and whatever. Prompts, you can define prompt templates to interact, and then also resources, this unified way to access resources, be it data, files, and so on. Okay, we now have a structured communication channel between AI agents and app and tools. So what are the benefits here? We can say, okay, we have now a discover capability of an app tool. We can interact with the app or tool through natural language, which is very, very interesting. We can retrieve informations from the app tool and execute commands. I always say app/tools because I'm more on the tools perspective as a DevOps person or platform engineering. So for me, it's more the tools perspective. How does it look like? If we have a quick demo. Where are you? Where are you? So I opened Cloud. I configured now a Kubernetes cluster. So you have to, on DigitalOcean, so if I say k get ns just as an idea, so to prove that it's working, hopefully, come on. Yeah, so we see that's the namespaces. So I can say, show me all the namespaces. And this is really a stupid example, but 5 minutes. So, thanks for not taking this. Show me all the namespaces. I'm very not taking care of my grammar when I talk with LLMs. So now it asks me, because yeah, it's here my demo environment, but here it goes now through the system, through the tool configured and create. So I could now say, create a simple Nginx deployment in a namespace called Rejekts. I didn't try this prompt, so probably it's not going to work. So it again. So it creates now the resource stuff. So let's say again, cloud get, yeah, we see the rejects one. And probably it's going to say car get what was it all? Yeah, we see also an Nginx services spin. No, it's not the one. So, okay. I'm horrible. I did this for the test, the commands with my muscle memory, and now I keep on forgetting them. So yeah, here is it. So it's spinned up. Okay, let's go back to the slides before I get the sign for 1 minute. So, okay, play from current slide. Okay, we talked about this. We saw the demo. So, I would say now in today's AI-integrated world, we have to accept the fact that we are now living in an AI-integrated world. So we should start off MCP-first approaches when we create new applications and everything. We should think about first make it accessible for the AI, for everything which is going to consume us. Before it was the human or it was REST APIs. Now it's AI systems which is going to consume us. And this applies also for IDPs. So here I pulled up the capabilities platform from the working group of the CNCF around platforming. So where I would put this in now, I would completely replace the overlay and say, okay, now we can do this all with MCPs, we can provide templates and all this stuff. So maybe that's a substitution. Maybe it's only the GUI, the GUI part. I'm from Germany, GUI. Okay, and as you can see, there are also some marketplaces, so you can see there's much work going on. People start to work because it's that simple if you really look at this, so feel free to play around. They created many, many SDKs. I'm a Go user, so some people in the community, props to him, created the Go SDK. Yeah, we also, as this is top secret, you see from the sign, I should not show this, maybe I lose my job, but we're also working on implementation. And as a takeaway, the IDPs must be AI compatible and MCPs are the way to achieve this, and hopefully you play a little bit around with this. That's it, thanks.
Awesome. Arik, see, I love this, front row, perfect. Everyone, fingers, please. So Kubenix, declarative Kate workloads. Boom, look at that.
Hello everyone, today I want to present you a tool called Kubenix, which allows you to declare your Kubernetes workloads fully reproducible. You can find the slides online by scanning this QR code. Let me briefly introduce myself. My name is Arik Grahl and I work as a senior software engineer at Sys11. If you want to reach out, feel free to contact me via any of these channels. In order to overcome limitations of flexibility and modularity of YAML, Helm templates those structures documents. However, this only mitigates some of its shortcomings while introducing other issues. I think this becomes pretty evident in this example. There's an awful lot of control structures here. There's even some validation going on during the rendering phase. You need to juggle with the indentation, and also the control structures span across many of hundreds of lines of code. I think we deserve better. So, KubeNix can actually streamline the definition of complex application stacks. KubeNix is built on Nix, which is a domain-specific language. It is a purely functional language, which is lazy evaluated. As a DSL, it is purpose-built, so you would not build like a real-world application out of it. Nix as a technology has the claim to enable systems which are reproducible, declarative, and reliable. Therefore, KubeNix leverages so-called NixOS modules to define arbitrary Kubernetes manifests. In doing so, it enables modularity through inheritance and composability. KubeNix basically implements an open API specification, so it brings additional type safety, during build time even. So let's have a small example of a web application. Since Nix is a functional language, every expression would be a function. This is how you would define a function in Nix, and with a let, you can bind local variables like an app, a version, or a host to a specific scope. You can also construct more complex types. Here we are inheriting the previously defined variables app and version into the attribute set labels. To define actual Kubernetes manifest, we are importing the corresponding KubeNix module. And we can start defining our resources straight away. Our web application consists of a deployment, a service, and an ingress, each named by the variable app. So in this case, Nginx. Now let's have a closer look at those three resources. To define a Kubernetes resource, we simply follow the usual structure of those resources. In this case, we define the spec field of a deployment. For the match labels, we can use the previously defined labels, very convenient. Those labels can be further reused by inheriting it into the template metadata field as well. So we now finally can define our container image, which basically reflects the app and the corresponding version. Let's move on to the next resource. The definition of the service is equally easy by simply defining its spec field. Again, we're using the labels as a selector, which ensures us that the service will always match the pods of the corresponding deployment. The pods are a list, which is also defined straightforward in Nix. We specify the protocol and port and are done for the service. Note that the port has a different type than the protocol here, which is a string. In contrast to Helm, this is actually type-checked. Let's move on to the last resource of our application. It is the ingress, and we can directly specify its spec rules, which is a list. We are inheriting the previously defined host from the variables and define the path as a list again. We want to match our request here, so we define the root path and use a prefix as a path type. Now we can select the backend service by its previously defined main, again ensuring that it will always match. And in less than 40 lines of code, we have defined a web application consisting of Kubernetes resources with minimal boilerplate overhead and additional type safety, ready to be reused elsewhere. Now, let's have a look how we can build and apply this. Here, we can simply use the standard Nix tooling and build the code, which I have just demonstrated. This gives us a V1 list, and those resources we can then inspect with any tool we actually want. So, or we can move forward and apply this to a cluster of our choice. So, wouldn't it be cool if we somehow could benefit from existing ecosystems dealing with packaging of Kubernetes workloads? Conveniently, KubeNix also comes with a Helm module, which allows us to consume arbitrary Helm charts. Again, we define a function, specify the version of the Helm chart we want to consume as a local variable. Now, we are importing the Helm module and can start defining Helm charts right away. Therefore, we are fetching our Helm chart specified by its version and a repo URL. We give the chart a name and specify a content-based hash in order to satisfy the reproducibility requirement of Nix. Then we can directly specify any values which are supported by the Helm chart. In this example, we are setting the replica count to 2. This brings me to the end of my presentation. If you'd like to learn more, feel free to approach me or scan any of those QR codes. Thank you.
All right, guys, holding on fast. We've got 2 more lightning talks to go and then our closing. So we have got Philip. I love that you ran up here. You're amazing. Siegel Stateless OCI Registry. You were so fast, we didn't get to cross our fingers for you.
Why doesn't it want to?
You've got this. So I will say other places, when they do lightning talks, they make you put them all on one computer. So I appreciate y'all letting us make sure we can have demos and live content from multiple computers and holding on through these little minute technical difficulties.
Do you have any?
There we go. It's popping up. Teamwork makes a dream work, y'all.
Resemblance of time. There we go. So I'm going to go really quickly now because we're over time. So yeah, I'm here to present Spiegel, which is a project that I've created about 3 years ago and I'm still maintaining. My name is Philip, if you didn't know. Yeah, so Spiegel is a stateless cluster local OCI register mirror. It's a mouthful and probably also very oxymoronic. So yeah, so out in the wild, we kind of see a lot of issues with image distributions when it comes to Kubernetes, especially it's more relevant now with rate limits, especially those like that have been introduced with like Docker Hub, but also like the K8s registries have like IP limits on like how many images you can pull with a specific IP. We see a lot of outages, GHCR, Docker Hub, Quay. It isn't really calling anybody out specifically. I think all registries out there are down sometime. Bandwidth limitations is also like a big thing, especially with like the free public registries. Docker Hub, I think, like limits you to like 100 megabits a second or something like that. But also like image removals. So we're building our cool applications. We're depending on images. Quay, like 2 years ago, had like a big cleanup of images where all of a sudden like Helm charts and images stored in Quay just like disappeared over the night. So about like 3-4 years ago, I had like a thought of like, okay, maybe there is like a better solution than just like running registry mirrors and like having all these stateful registries that we have to like deal with and like copy over images too. So I ended up building Spiegel. For those who don't know, Spiegel means mirror in Swedish. It basically just really allows you to pull images from other nodes. So what Spiegel does is it runs as a daemon set in your Kubernetes cluster and basically runs a local registry. It then piggybacks on top of containerd. So an interesting fact of like containerd is when you're actually running a pod, the image that is pulled for that pod is actually stored on the node. So the disk space is already used. So what Spiegel does is basically it runs a registry, reads the content that is already on disk, and then advertises it using a distributed hash table to all the other registries in the cluster. And then when a pod or an image needs to be pulled, containerd will first check with Spiegel to see, oh, is there another node that already has this layer, and it will just redirect that traffic to that other node. And obviously then if it doesn't, it will fall back to the original registry. So it's like mostly like a best effort kind of cache. I've built like a lot of benchmarks. It's to see like generally like what kind of performance that we can expect from Spiegel. Overall, like there are situations where Spiegel performs poorly, and there are situations where Spiegel performs like really well. Generally, I'd say somewhere between like 50 and 80% performance improvement is kind of what you see, especially with larger images is really like, especially with the AI craze and things, we see like larger and larger images. Yeah, like in general, like you'd see like a large performance like in pull time just because the locality of the images. So instead of going out to even ECR or ACR, pulling from within your like private network is always going to be faster. Yeah, so that's kind of it
thank you very much. You can check out Spiegel there. There's like the website to check out the documentation. There's also the GitHub repo. Yeah, thank you.
Thank you so much. Okay, so because it's lightning talks and things always go a little crazy, we are down to none. And what I want to say is we are about to thank one of our sponsors. What? What? We do, but that person cannot be here. Oh, yeah. So we're sorry that he can't make it. But what we are excited about is that one of our sponsors that made the champagne, the rooms, the ticket, the coffee, everything accessible to you for free is going to close us out. He is a CNCF ambassador. He's running KCD Sofia, and he's all kinds of community. Our man, Orlin from SUSE.
Is that going to work? I don't know. Okay. It's working? Okay. So, I don't know how that happened, but it was not planned that I'm going to close, but yeah. So, hi everyone, welcome to the last 5 minutes of Rejekts 2025. Some of you know me, some of you don't. So my name is Orlin. I joined SUSE as part of the Community Engagement and Technology Advocacy, super long name, group. I have my colleagues Divya and Rob here. So that was supposed to be thank you message from SUSE. I'm not wearing SUSE t-shirt, but I have SUSE slides. But it's about community, right? So I'm not a very smart person, but there are smart persons who said smart things, and they're on the screen. So if you're bored by what I'm going to tell you, just you can read. But I just want to say something about SUSE. I joined SUSE because those people who hired me saw something in me that I can do for the community at SUSE. Some of you may know that I'm engaged with the hardware community for I don't know, 5 years. I've been doing some other community stuff, as Laurie said. So I kind of took the wrong turn from technology, from technology to community, and now I live and breathe in community. So I believe that we can do great stuff with community, and that over here what's happening is a community effort from all of us. Thanks for the organizers, thanks for all the sponsors, thanks for all the volunteers who made that thing happen. Yeah, Linus Torvalds is very precise in that. So, thank you very much, everyone. Take a look at each and everyone in that room. You may not see that person in the next week, even though we'll be in the same room, like 20, was that 12,000 people? Yeah, so you may not see the person next to you in the next 10 days, 4 days? Oh, sorry. And just one thing, community, right? This event, I don't want to waste your time. I just want to say thank you. And take a look at your badges. It's names, no companies. So we are people here, no companies. We share ideas, we share passion, we share projects. Nobody cares where you work. If you talk about it, yes. But nobody generally cares here where you work. It's about us, it's about what we do and how we share it. So thank you very much once again. See you in Atlanta. And before clapping, have a drink and we have to leave. So thank you very much. See you next time.